Mhm.
Good morning. My name is Amy Kelly. I am Deputy Director of the National Institute on Aging and Acting Director of the NIA Division of Neuroscience. On behalf of NIA, I am pleased to welcome you to this
Hold on.
two-day
Let
workshop,
me fix on the
Dementia
phone.
with Lewy Bodies, Filling the Gap in Translational and Clinical Research.
I'm gonna give you this.
So in partnership with our colleagues at NINDS, we are very excited to be hosting an interdisciplinary group of speakers and participants, looking forward to learning from all of you with a wide range of perspectives over the next 2 days. And in particular, we're thrilled to welcome a panel of individuals with lived experience to kick off the workshop with a discussion of the challenges of DLB diagnosis. This is a key area of interest for NIH now and looking forward. In addition to learning from people impacted by DLB, we hope that in opening the meeting this way, it'll serve to really ground the entire workshop in the lived experience. And to our colleagues with lived experience, those presenting and attending, we at NIH recognize that we simply cannot make the necessary progress in diagnosing, treating, curing, and preventing DLB without your uniquely valuable input and robust collaboration. So thank you for being a part of this meeting and for sharing your stories and your perspectives. Today's agenda also includes discussions around the high degree of clinical and neuropathological heterogeneity associated with DLB and how this contributes to often delayed or inaccurate diagnosis. Tomorrow, we'll delve into research progress and the remaining challenges in biomarker development, drug development, and clinical trials. The overarching objective of this workshop is to collaboratively identify gaps and opportunities related to DLB research. Therefore, we will end the workshop with a conversation about the key areas of research needs and next steps. I also want to take a moment to share with you just how important your participation and input is to NIH by elaborating a little bit on the processes we employ to incorporate input from the entire DLB community in our strategic directions and those of the US government. All of the workshops and research summits that we host are specifically designed to allow NIH to hear from a range of experts, including researchers, clinicians, persons who are living with dementia, their care partners, and others to understand the wide range of perspectives you bring. Please know that your robust participation is encouraged and appreciated. To all of you attending virtually, you are encouraged to use the Q&A function during the talks and the panel discussions. The conversations we will have throughout the next 2 days, as well as internal discussions that follow, will directly inform NIH priorities moving forward, as well as the US government priorities through the National Plan to Address Alzheimer's and Alzheimer's-related Dementia, as mandated by the National Alzheimer's Project Act, or NAPA, and the Alzheimer's Accountability and Investment Act, both of which were recently reauthorized by Congress. So it is imperative that we ensure all perspectives are considered if we're going to maximize progress towards our shared goal of advancing research and improving treatment and care for those with DLB. For example, the outputs from NIH workshops and summits inform the NIH AD/ADRD research implementation milestones, which have been developed through consultation with hundreds of clinical, research, industry, and lived experience experts. The research implementation milestones provide a research framework that guides progress towards the goals of the national plan to address AD/ADRD, and there are currently hundreds of specific research implementation milestones. They span basic, translational, clinical, and health services research. I'm highlighting here a few of the specific research implementation milestones related to this week's workshop, such as those related to biomarker identification and validation. These will be central topics to this workshop. And you can learn more about all of these research implementation milestones, including progress updates, funding initiatives, and research progress through an annually updated database on the NIA website. So I'm going to share in my ending just a few of the current and recent funding opportunities that relate to our workshop agenda. This is not an exhaustive list, but it is meant to demonstrate that NIA regularly has funding opportunities to support DLB research and training from basic biological research through translational and drug development and clinical care. So please be sure to check regularly on our website for a comprehensive list, particularly as new opportunities are regularly announced. We also have several other ways to stay in touch with NIA and to keep informed about upcoming events, funding opportunities, and so much more. And with that, allow me to thank you once again for joining us for what I am sure will be an excellent 2 days of conversation. We're tremendously grateful for your presentations and your input, and we're honored to work with you to drive progress in DLB research, including ensuring earlier diagnosis and better treatment and care.
I'm Dr. Walter Corsett, and it's a pleasure to talk to you today. I apologize for not being there in person. I'm at meetings about ataxia in London, so I wanted to just record a couple of remarks for this Dementia with Lewy body workshop. I just wanted to start off by saying that we think of these as synucleinopathies. And as you know, synuclein causes trouble in many different forms. In Parkinson's disease, it affects the motor system. But way before that, it affects the autonomic nervous system, other nuclei in the brainstem. But in many patients, the synucleinopathy then progresses to affect limbic or cortical structures, causing cognitive impairment and dementia. And certainly what we've heard from the Parkinson's community over the years is that there is a concern that we may have been too focused on the motor issues in Parkinson's and not enough on the cognitive issues, which gets us to the issue of how do we prevent and treat the synucleinopathy when it affects the cortex and higher than midbrain levels. And so the Parkinson's and Lewy body dementia groups, I think, are really working to that same goal in many aspects. Now, as you know, in some cases, the synucleinopathy affects the upper brain regions before it comes down to the niger, and that's we call Lewy body dementia, or diffuse Lewy body disease. But I think biologically they're incredibly similar, and that the diagnostics and treatments for one will be also important for the other. And the big discovery in this field of synucleinopathy has been in the biomarker space, where the seeding assay has shown a very high accuracy in diagnosing synucleinopathy causing Parkinson's disease. But as you can see here in this work from Glasgow and Quinn's labs, that the same is applying to Lewy body dementia cases. But there again, there is something to be aware of, in that the accuracy of the test depends a little bit on where in the brain the synucleinopathy has taken hold. Not as good currently when the disease is primarily in the amygdala, as compared to the higher accuracy when it involves the neocortex. But I think the main thing to know for all of us is that this ability to diagnose diffuse Lewy body disease, although it's not 100%, it's a gigantic step forward. And as you all know, because patients present with unusual behavioral cognitive difficulties, it's often a long, hazardous road before the correct diagnosis is made, and hopefully this test will be able to shorten that You're going to hear from folks today who are working on developing the seeding assay and other more accessible tissues in the spinal fluid, although having done thousands of spinal taps, I consider it pretty accessible, but not as much as, say, serum and saliva, which will be interesting to hear from in terms of the ability to see that the seeds forming based on these more accessible tissues. Skin biopsy as well, certainly been looked at. So we're coming to a new age where we can make these biological diagnoses. Important to note that these markers become positive way before symptoms occur. So this offers another opportunity to make diagnoses really early, perhaps before symptoms occur, and then, intervene to prevent the disease, which is basically going to be a cure. So that's what we'll be shooting for. It's a long road ahead. But now with this ability to make these pre-symptomatic diagnoses, the pressure is really on to try to develop therapies that prevent people from getting sick, in addition to helping people who are already having trouble. So that's what I see the future. The issue, of course, and we may be, over-focused on synuclein. I hope not, but the issue is whether or not we can ever figure out what causes that initial nucleation of this abnormal aggregate and then spread throughout the nervous system. So trying to cut it off at the onset, at where the problem is first arising, would be really incredibly important. And then, of course, trying to understand how it spreads. So even if it gets into the part of the brain, if we can figure out a way to prevent it from spreading to other regions of the brain, that's the similar challenge that we have in pretty much all the neurodegenerative diseases that are characterized by protein aggregates. So learning how to prevent spread in one may actually help the others, and that's our hope. The other thing I think we have to be, really cognizant of is that Lewy body dementia and the dementia that occurs in people with Parkinson's is oftentimes a mix of synucleinopathy affecting cognitive circuits in combination with Alzheimer's biology. So trying to understand the relative weights of each of these things also incredibly important, particularly now with the ability to really effectively move amyloid out of the brain with the anti-amyloid therapies. So we're really interested in understanding in a clinical trial situation whether that would hold water in terms of helping people by removing the amyloid, and that is people who have Lewy body dementia. So I just wanted to say a couple of things. We've really been blessed here at NINDS and at the Aging Institute to have the funds to really put huge efforts into understanding neurodegenerative diseases, including Lewy body dementia. We have an Alzheimer's disease-related dementia summit coming up, and Lewy body dementia is one of the Alzheimer-related dementias, along with frontotemporal dementia and the vascular cognitive impairment. And again, we work heavily with NIA and mixed dementias. So this is coming up, and this gives us a plan to move forward for the research in the next 4 years. With these additional funds, you can see here that the funding for diffuse Lewy body dementia has increased substantially, as have the other Alzheimer-related dementias over the years with these congressional appropriations. And if you look at the institutes, there's a lot of institutes involved, primarily NINDS and Aging Institute, and you can see here on the right the types of research that NIS is funding in this space. And again, the increased funding and increased interest, I think, holds a lot of hope for folks with these disorders. I would say that NINDS is looking up to the 75th anniversary, and it would be really great to have a real big advance in this field to celebrate along with the 75 years of work that's gone on. We're really looking forward to get advice in this year of 2025 on what happens, what should we be doing in the future, what are our opportunities there. And with that, I'd like to hope you have a great workshop today, and looking forward to hear from our folks about the deliberation. So take care and see you soon. That's a lot to cover.
Do I have to do anything to turn this on? Or I could just go here. All right, well, welcome everybody. I am very pleased to announce the first session of today, and that is the lived experience of people living with dementia with Lewy bodies. We're going to go with a bit of a different order than is in your agenda. So as we discuss this session and with the approval of the NIH, we're going to start with 3 people who are currently living with Lewy in various ways, as people living with Lewy themselves or caregivers or both. And all 3 of these initial invitees are going to join us via Zoom. And each individual or pair will introduce themselves and then tell you over 5 to 10 minutes about their journey with dementia with Lewy bodies. And then after everyone shares their experiences, then we will have about a half hour of discussion with some questions. So I would like to introduce Graham and Colleen Williams, who will be joining us first. Give us just a moment while we get everyone on the screen. All right. Well, we can kind of see off on the side the Zoom pictures of people who are talking. So Colleen and Graham, why don't you go ahead?
Hello, everyone. I am Colleen Williams, and this is my husband, Graham Williams, who in September 2019 was diagnosed with Lewy body dementia at 61 years of age. Level-headed and competent, this hands-on father of 5 and sole breadwinner managed family and career responsibilities with amazing grace. Earning his MBA while full-time on the job, Graham was still able to remain active, in the local church. He retired as a senior financial management specialist at the American Bank, working in their country offices in the Bahamas, Suriname, Jamaica, and Belize. Between 2013 and 2014, complications from cataract surgery made overseas travel to Miami for medical care both necessary and frequent. At-home leave to our native land, Guyana, work-related trips to Latin America, the Caribbean, and Washington, and trips to college with children, and a busy travel schedule emerges. It was during these trips that Graham began to express confusion over which country he was in and to have hallucinations, especially after sleep. At home, he often mentioned that his thoughts were being snatched away, had difficulty following instructions, and regularly misplaced keys and glasses. Now and then, he would fall out of bed and frequently shout and kick and punch during sleep. My husband's driving became unsafe. He left the financials to me and generally gave the impression that he was overwhelmed by everything. Thinking that his vision problems were responsible for decreased productivity at work, we took 6 months leave, but when nothing improved, we retired in February 2017. In 2019, my husband reluctantly agreed to mention the above symptoms, to our primary care provider at Cleveland Clinic in Florida, who referred us to a neurologist there. MRI, PET, and neuropsych tests confirmed his suspicions, and he diagnosed LBD as the problem. The informative LBDA website, found through online research, introduced us to the Research Centers of Excellence And in 2020, we sought a second opinion at the RCOE in Washington State. The neurologist, with the additional help of a DAT scan, confirmed the diagnosis and prescribed rivastigmine, moving up from 4.6 to 13.3 mg over time. Because we had a relationship with the neurologist there more than with the facility itself, his resignation made us seek care at another RCOE in Miami in 2022. The new provider used an MRI with NeuroQuant, discovered hypostatic hypotension, added memantine, and connected me to a support group for caregivers run by the social worker on staff. This group has been invaluable in helping us to understand what to expect, what strategies to use, and how to manage the rolling emotions associated with this journey. It was their certainty that travel was going to get harder for my husband that caused us to make two decisions. A 40th anniversary trip while we could still do it, and move to the USA permanently to be closer to the best possible care available. On both occasions, their predictions were correct. On the first trip in August of 2023, 4 years after diagnosis, the crowds, the lights, the sounds, the movements, all things that had previously been enjoyable to us now produced directional confusion, anxiety, dizziness, mobility issues, particularly pronounced when using stairs, difficulty eating, and overall weakness. My husband was overstimulated and overwhelmed by the environment and needed to rest often. To my absolute amazement, most of these symptoms disappeared on returning home. The second trip, made in July of this year, saw the return of last year's symptoms, but this time the confusion is marked by difficulty determining day and night what is real and what is not, interactions with increasing hallucinations, behaving as if he's still at work even though he has been retired for 7 years, agitation, restlessness, and especially at night, snoring terribly and gnashing his teeth. For the first time, my husband of 41 years identified me as someone else and conversed with me as though I were that person, and a man at that. We have since ruled out a UTI and added melatonin under the guidance of the RCOE in Miami, even though we are out of state. Our efforts to be seen at the local RCOE have been unsuccessful. Graham and I are very grateful for the quality of care that we have received in the USA, especially since neither this expertise nor the medications he takes are available in our home country. We are also grateful that our journey to diagnosis was not long. The first neurologist who saw us got it right away. However, we have not been able to access appropriate LBD care and its related therapies such as physical, occupational, language, and speech therapy in a one-stop facility. Near paradise for us would be to have primary care doctors who are also educated and skilled in the diagnosis and treatment of LBD patients. At the very least, it would be quite helpful if the LBD doctors would collaborate with the PCPs, communicating directly with them in some kind of monitoring relationship, which does not leave the full responsibility of advocating for the patient on the shoulders of the caregivers, who are themselves learning. The present situation becomes more difficult when the LBD doctors and the PCPs disagree. Equally challenging to navigate are the long wait times before a relocating Lewy body patient having new episodes can be seen by expert doctors. Even with referrals in place, wait times can be 6, 9, and even 12 months away. We have actually been advised to go to the emergency room. Although usually good advice, this can nevertheless be a frightening proposal for the LBD patient. Thank you for this opportunity to share our experience with LBD diagnosis. Graham and I hope that it will be useful in helping this conference to achieve its goals.
Thank you so much for sharing those experiences, and so early in the morning for you. We are going to continue with the people sharing with us, and Dr. Drubach and his wife are next.
Hello.
We can hear you. Thank you.
Thank you so much for including me in this symposium, which seems to be very, very, very difficult, very, very good. So, do you want to have a?
You can go ahead and share what you would like to share with us today.
Okay.
Experience.
Well, my first experience of my first that there was something wrong was when I was with friends in a restaurant in Argentina, actually, and I noticed that there was something. Somebody else noticed that there was something wrong with the right lower extremity, that I was limping, and I had never noticed it before, but he certainly had it. Subsequently, I developed a lot of what you unusual symptoms, including visual hallucinations or visual distortions, and they were very, very, very bothersome, and they became worse over time. I am, by the way, a neurologist and a behavioral neurologist, and so I have some interest and it gets a little bit confused sometimes whether it's real or not real, and it's a very unusual symptom. I also developed other symptoms, including worsening Parkinsonism, and that came over time. And I actually diagnosed myself with DLB. I actually, my greatest practice at the university, at the Washington, at Mayo clinic, and that's where I work.
You want me to share a little bit?
Yeah.
Okay. So I'm Dina Drubach, Daniel's wife. A little bit of that lead up that he was trying to express is that, you know, Daniel has been at Mayo for over 23 years practicing in the behavioral neurology division amongst the expertise of other physicians and colleagues and very good friends. And so when some of the symptoms he detected, I detected early on with orientation, we both sort of started questioning, okay, what is this, without saying, what is this? And so therefore, it went on to have diagnostic testing with the best of the best at Mayo Clinic and the direction of his colleagues. And he also underwent scans, which revealed conclusively that he had. So his journey for his personal experience, not like others, which is difficult to hear, being that he was at the right place at the right time and working, his diagnosis was fairly straightforward and easy due to the the team at Mayo, which he led to a degree with the clinical care because of all the Lewy body patients he saw throughout the years. So his course for diagnosis, unlike others, was very direct. Everything got done, the results came in, and it was very clear. And then he proceeded to step down and from Mayo and go on to disability, and then further follow up with other modalities that would assist him. And so I think the early ones that he mentioned were the hallucinations and the visual disturbances that became more and more clear, and some hypersomnolence, which sort of took over and still comes in and out as far as his journey in the diagnosis. All of those things led up to his actual scans that were done. Mayo Clinic has an amazing team of researchers as well. And so we were very grateful to be at that place, Daniel serving thousands of other Lewy body patients. But he's now on the other side, and his view of things and how they're going sometimes fascinates him, right?
Sometimes they do, yeah.
He's very fascinated by the disease. But our course, his course, and working together, we also both spoke on the disease. Daniel was a clinical expert. Mayo has dementia days, and I'm a physical therapist, so I did the PT piece, shared with caregivers and others in the family, and Daniel was the medical expert. So that also made our journey very clear and concise, and what we needed to do and what should we pursue. So we didn't have, unlike Colleen and Graham, circumstance of having to go through so many different others. Ours was a bit of a direct path due to who he is and where he was, and we were very, very grateful, very grateful.
I had a number of PET scans and other studies, including genetic testing most recently, and they all turned positive. It's kind of ironic that I am the patient as well as the physician at one time, working right now. But it is kind of ironic that it's both both the patient and
the physician still.
Physician still. So then the other things that I had unusual hallucinations. I felt that there was always a person with me, and that was a little bit bothersome. Because this person, or this
Presence.
what I call the presence, got to be quite bothersome, and same with other. I began to have a lot of difficulty with mirrors. Interestingly, the mirrors, I just couldn't. I didn't seem to know where the mirror. How to get out of a place that had mirrors, and that's kind of my story. And I notice now that I look at the screen, that my face is quite much stiff, quotation marks, which I attribute to Parkinsonism. And that's kind of it with how was I diagnosed. And I was diagnosed by myself. Basically, even though it was with the help of a couple of physicians, I did diagnose myself basically, and so that's the story. The hallucinations are prominent. developed apathy or bulia and became very severe. People, my wife thought that I was lazy, and but it's more than just that. So.
Well, thank you so much for sharing your really unique story with us, both of you. We're going to go next to Juan Bujosa, and we have a slide for a few of our presenters. And so I don't know if it's possible to get the slides up. I want to thank both of our first two speakers. And then while we get Juan on the screen, we can see if we can pull up the slide that the picture he provided to us as well. But we can go ahead and hear from you. Here, I'll try to forward the slides while we go ahead.
Hi, my name is Juan Bujosa, and we're a same-sex couple. My husband is Dr. Jack Faraci. He's a retired OBGYN physician. He retired in 2000, actually a year before he was diagnosed with cognitive impairment in 2015. He noticed that he was having problems understanding things, being a physician. Sometimes he was doing surgery. He said, "Juan, I was getting upset because I was getting nervous about it." So he recognized there's something wrong with him. So finally, he was diagnosed in 2015 with cognitive impairment. In 2017, we moved from New Hampshire, where we lived, to Florida. We have been together for 25 years. And when we got to Florida, is when he got diagnosed with, Lewy body. Lewy body dementia, frequent hallucinations, orthostatic apopressure, delusions. I'm an engineer. I'm not a physician like he was. It was difficult to understand. So I was trying to go and get educated how to work with this. So finally, 3 years ago, he was diagnosed with Lewy body dementia. We have an excellent neurologist and psychiatrist that work with us all the time. And he lived with me. I tried to help him out. But finally, 2 years ago, he tried to jump, to commit suicide. And then, like a month after, he tried to stab me. He didn't recognize me. So we were advised to move him to a memory unit. And that's where he lives. He currently lives in an assisted living memory unit the last 2 years. Actually, he turned 2 years in October. I'm sorry, I'm getting emotional. So it's been quite a journey, seeing deteriorating the way he's been doing. Right now, he got Parkinsonism. So when he arrived at the memory unit, he was walking, and we have been always taking physical therapy, occupational therapy. We've always been on top. But as of a year ago, he stopped walking altogether. He's on a wheelchair. He still keeps getting his physical therapy, stretching exercise. He's very stiff, but he's in the last stage of Lewy body dementia. There isn't stages. He's really, he knows who I am. Doesn't recognize some of the friends that we have, but he's happy. I mean, he's in a different world. My message to this audience was mainly that I would like the medical system, the hospitals, and everyone else to be more educated or more aware of this disease. Jack had a series of UTIs, infections. He's like 5 of them this year, almost in a row. And every time I went to the hospital with them, they changed, the medications they were trying to give him. They're trying to change the medications, and they were giving medications that can affect his brain even more in the Lewy body dementia, particularly the anticholinergic medications. So I had to be an advocate and look at the medication list. I said, no, he cannot take that medication. That can affect his brain. And I was amazed how the physicians, a big majority of them, that they were in the emergency room and on the floor, they were not aware of that. So I've been, thank God, to the Mayo Clinic. I belong to a group of Lewy body dementia that participate every Monday. We have been educated. I've been learning about the disease. and being able to help other people that are coming along to Jack's place. Basically, that's the message that I have to convey. You have any questions, I'll be glad to answer them.
Thank you so much for sharing that with us. We're going to come to questions after we hear from a few more of our speakers, and our next 3 speakers are all here in person. So Tish, I'm going to invite you to come on up. You are our first speaker. And so the next 3 speakers are all people who were caregivers for people living with Lewy, and they're going to tell us about their experiences now. I'm just trying to forward this line.
Hi, everybody. Go ahead. Can you hear me? Okay, great. My name's Tish Hevel, and 10 years ago last month, pardon me, my youngest went off to college. I resigned my job, sold my house, gave my furniture to my interns, and moved back to my hometown to help my mom take care for my dad, who was declining. And we really wanted to keep him at home because he was a lousy patient. He had been diagnosed with MCI, mild cognitive impairment, about 5 years prior. And he thought he could charm his way through a lot of things, including the screenings. And he actually, since he was a financial guy, he was pretty impressive at counting backwards from 100 by anything. But that clock thing and the memory recall quizzes really tripped him up. So my mother, who used to be a drug rep and thought she was a doctor and now thinks she's a specialist, she insisted to put him on donepezil, Aricept at the time. And the neurologist resisted a little bit. He's like, well, it's still going to be the same outcome. Well, duh, we knew that. But, you know, so she insisted, and he did really well on that. I know not everybody does, but he remained terribly high functioning for 5 years. So anyway, so I moved down there. It's early November. We take him to the neurologist like the week after I got there. And we had suspected Lewy bodies. We had some friends in the medical field and a really good hospital social worker buddy who gave us some great books. So they diagnosed LBD, and, you know, we kind of suspected that, but it became clear at that meeting that we were later in the game than we thought we were. So we knew he was cognitively impaired. We knew he wasn't going to come back from that. We knew we were on a path. So I wouldn't say any kind of delay in diagnosis really affected anything. We were just waiting to see exactly what it was. And after that, we had 6 months of what my mother and I call the sacred days. His symptoms were, I mean, he was confused and full. I mean, just delightful. And he had been a real type A, hard driving guy for the longest time, and he mellowed incredibly. So some of the goofy things, he would eat breakfast and then take his cereal bowl and his coffee cup and put them back in the cabinet. And we were like, what are you doing, Dad? And he's like, well, they're not that dirty. And I'm like, yeah, they are. So we would take notes, and then he'd leave the room and we'd go throw everything in the dishwasher. He had also been a decent bridge player, but all of a sudden he wanted to play gin rummy, like one of the most basic card games, all day long. And he would sort his cards and stick a couple under one leg and sort some more and draw from the deck. And so there's cards everywhere. And all of a sudden he'd go, gin. And I'd be like, okay, let's see what you have. I mean, so there were some really sweet moments. He got confused. He was afraid one time that my mom was the one with the terminal illness, and he was just gutted. And then at some point he realized it was him, and he asked my mom about it, and she had the greatest answer. She said, honey, we've all got a terminal illness. Not one of us is getting out of here alive, you know? And it was funny and sweet and so true. And she said, but, you know, you're not going to be alone. So, anyway, he knew us with big family. He knew all of us till the very end, and he was as sweet as can be. We actually called Lewy bodies a kinder, gentler form of dementia than a lot of what we had heard about. In mid-January, we consulted hospice. We didn't really think he was ready for it, but we thought maybe we should see if there's anything else we could do to make him comfortable. So the nurses came and he's turning on the charm, walking him around the house and talking about things. And they weren't sure he was ready either. But when they came back the following week, they couldn't believe it was the same guy. He was in bed. He was not walking around. He was napping off and on. Pretty soon he never got out of bed again. And he died on March 10th. So it was a terrible loss. We had made arrangements to donate his brain, but it was very complicated. And the plans fell apart the day before. And so my sister and I had to scramble to come up with another option. And fortunately we did. But we told people a lot about it. And our friends and family were like, wait, what? You know, nobody'd heard of brain donation. And so these were, some of them were medical people. And of those, a lot of people were like, oh, can you help me do it? And I was like, let me see if I can help them make it easier first. So I had been a journalist. I wasn't afraid to call people. I called up a guy named Walter Koroshetz, who happens to be the director of NINS, still is, to see if he could use some help with the public education / simplification part of things. And so he put me in touch with the people who were running the Neurobiobank, particularly Michelle Freund and Anna Taylor, if any of you know them, who were fantastic and very patient, teaching me about brain donation. They were running this thing called the Neurobiobank, which is the NIH's structure of brain banks they had just put together the year before in response to PIs who couldn't get their hands on tissue. And it was like the most important thing they needed for their study. So that's why they did this. So we, long story short, we launched a nonprofit in 2016 to do what we thought was missing, which was simplifying the process to become a brain donor when you die on behalf of yourself or someone else, and raise awareness of the critical need for this most precious tissue that was gonna help us get to more breakthroughs. So we simplified by asking people to come to our website, learn about brain donation, and start the process with a pretty simple online form. We would take that information and refer the people to the correct brain bank that make the most sense for them. And then we'd hand over the relationship. That's what we do. You go to this brain bank, they'll help you from there. They'll decide if you're a good candidate. So we're just kind of the conduit. And we're educating people in a lot of different ways. We do podcasts, newsletter, content, presentations, all this fun stuff. And we've been fortunate to have some great consumer media attention with all the outlets, you know. So 8 years later, we're coming up on 25,000 people who've at least taken the first steps to become a brain donor. There are challenges for the brain banks, and we try to pivot to help them with those, targeting certain groups, helping learn how to invite other groups that aren't well represented. So we know there's situations that we need to pivot to help them with. So I'm going to close now with what I tell audiences everywhere in honor of Gene Armentrout. That's my dad. Please consider brain donation. Everybody, please consider brain donation. Make the arrangements, talk to your family about how to see those arrangements through. We spend time and energy, and we hire lawyers to help us figure out what to do with all our stuff and our money if we got any left. But the most precious thing you have should not go to waste. Thank you.
Thank you. You can stay up here if you want for the, as we get ready for a group discussion after a couple of more speakers. I'm going to invite Angela Taylor up. Oh, here she comes. So she'll join us up here. And then she will tell us her experiences as well.
Well, good morning, everybody. It's nice to see faces instead of like the profiles or backs of heads. Wonderful. All right, so I'm going to date myself right off the bat here. Here's the Reader's Digest version. Some of you may not even know what Reader's Digest used to be. But here's what I'll be sharing with you today. We were lucky. My dad got an early DLB diagnosis. I had expansive access to DLB experts. Dad's journey was rather benign compared to many, many, many other stories I've heard. And like every other DLB family, our journey was brutally painful. So, diagnosis. Dad's diagnosis was in the early 2000s. Mostly, it just needed time for his symptoms to progress. He started with MCI, and during that visit with the neurologist, we also learned, because I asked my dad to mention these nightmares he was having, we learned that he also had REM sleep behavior disorder, which the doctor could just fix with one pill at bedtime. That's all it took. All right. Over the next couple of years, I started to learn about MCI and RBD, and I kept running into this Lewy thing I'd never heard about. And over the coming couple of years, we saw, of course, not just his PCP, but 2 neurologists and ultimately a neuropsychologist. So that was his journey to diagnosis. It wasn't all that hard. It required a little persistence, and I had to have the 96 McKeith criteria in hand everywhere I went. But it was between the MCI and the DLB diagnosis that there were 2 years that we lived in crisis mode. Dad was living alone about 4 hours away from me, and I was raising 2 little girls, and we were in preschool. And he had 2 surgeries within a year on his back. And together they took a completely unexpected toll on his cognition. So by the time we sold his home and he got his DLB diagnosis, I was already burned out, anxious, and everything just felt hard. And I was really surprised when my doctor suggested that I was depressed. I mean, he was right, but I couldn't see it. So, caregiving. I was the luckiest caregiver on the planet. Seriously. I was in an online DLB support group on Yahoo. Had met the founders of the Lewy Body Dementia Association and was invited as the next warm body to serve on the board. And my first assignment on the board was to serve as liaison to LBDA's brand new Scientific Advisory Council. Raise your hand if you're in that group. Thank you, wonderful. These are my friends, my family. So that's remarkable access that I had to DLB expertise. But living with DLB is like traveling without a map. No one can tell you what you're going to face next week, next year, or 5 years from now. You face perpetual ambiguity and chronic stress. So trusting doctors is hard. Trusting medications is hard. Trusting hospitals, as you've heard, is hard. Trusting that you can get an admission to memory care or other long-term care is hard. Trusting that you know when the end is coming is hard. And given all of that, trusting yourself in knowing that you are doing your best for your loved one is impossible. A few years ago, and more than 10 years after my dad had died, I heard a researcher say that LBD caregiving is traumatic. Honestly, I'd never thought about it. I just knew it was really hard for me. But it immediately struck me as the truth. And yet my dad had probably the most benign case of DLB maybe I'd ever heard of, except for maybe now dishes. But he had persistent and upsetting delusions. He would spend, so he would tell me, all day organizing the clothes in his closet. So much so that he was so tired he really couldn't clean up the mess that wasn't there. A wavy carpet in the memory care facility was actually a flood to him that came right up to his door. There was a building next door that was always being torn down. That made Dad very distressed as far as where was he going to live if his building got torn down. There was never any construction. Dad once got furious, so much so with an aide that they had to change the aide that was assigned to him. And this was a wonderful woman that he absolutely adored. because he was convinced that she was having an affair with the young man who lived across the hall from him in the memory care facility. Except the young man was an old woman with dementia. And like every other person with DLB, Dad lost the life that he had carefully built, his home, his car, his independence. He lost the comfortable retirement he'd prepared well for that should have included lots of leisure travel, massive amounts of time on the golf course, and watching his grandchildren grow up. And over the course of time, he lost every friend he ever made and most of his family. I've had the honor of being a DLB research advocate for 20 years now, and have always approached it with a true sense of optimism that someday we would see progress in DLB like we've seen in Alzheimer's disease and in Parkinson's disease. I remember my excitement in 2016 when there was finally a phase 3 trial being done in DLB. And in 2018, when I read for the first time that we could diagnose synuclein in a living person. Those were amazing days to me. There was only one time in all of those years that I felt outright fear. And that's when there was a proposal to merge DLB and Parkinson's disease into a single biological entity. We all agree that biological definitions are essential to inform the study of potential disease-modifying treatments. But we don't know nearly enough about the biology of DLB, its genetics, or its natural history to have any confidence that a single biological framework will be sufficient for both PD and DLB, especially one that doesn't account for co-pathologies and the interplay between them. So my challenge to all of you, and especially to research funders, is to prioritize the detection of amyloid, tau, and synuclein as the standard for DLB, PD, and AD, so that one day we'll be that much closer to personalized medicine for all of these diseases.
Thank you, Angela. And I'm going to have Sandra Moose join us up front. We'll play musical chairs. And there is a slide for this as well. Yeah.
Well, good morning, and I want to thank you for inviting me. This is wonderful. So anyways, I'm Sandy Moose, and I'm here to talk about my experience with my husband with dementia with Lewy bodies. And perhaps my frustration with the Lewy body patient journey can be best summarized by my husband's simple question. Is it too much to ask before I die my brain that's killing me? Is it too much to ask? Turns out it was too much to ask. And more than a decade after first experiencing the REM sleep behavior disorder, and after we did 6 years of trying to understand his cognitive symptoms with countless visits to neurologists with different specialties, we could not find an answer. So the diagnosis of dementia with Lewy bodies finally came, but 40 hours before my husband died. So he did have an answer. I woke him up to make sure that he heard the doctor say, I think you have diffuse Lewy body. So he did have it. Autopsy showed he was in stage 5 out of stage 6 in the disease. So let me try to step back and highlight maybe just 3 aspects of this overall journey, and let me try to pull some takeaways out of it. So let me start in the first part of the journey. We were actually looking for a prompt diagnosis because we were hoping for some clinical trials. But that obviously didn't happen because there was mixed data and the tests that Eric had were inconclusive. So the risk of an incorrect diagnosis was apparent. So he would not have qualified if there had been any clinical trials. On the other hand, having no diagnosis left us in limbo. And after my husband died, the reaction of the doctors was, well, it wouldn't have made any difference anyways, even if he had been diagnosed, because there was no treatment. That doesn't make the caregiver feel good. They didn't seem to really appreciate the emotional burden of living with uncertainty. And in my husband's case, over 6 years, and he was a saint. He happened to be someone who could deal with uncertainty and ambiguity well. But as I say, the few days before he died, is it too much to ask? Living with the ambiguity finally did get to him. And nor the importance of really setting expectations so that the patient and the caregiver could prepare for the end stage. So my takeaway here in this first part of the journey is to recognize, as I think some of the other speakers have commented on, how difficult uncertainty is to bear, and that a diagnosis is valuable even if there is no good treatment. There's something about having the certainty of knowing what you have. And even, I will add, a probabilistic diagnosis would have been better than none at all. At least it gives you some sense as to what might be going on. So now we'll move into the second part of the journey. So with a lack of a prompt diagnosis, guess what we did? We undertook our own research because we didn't want to live with this uncertainty and ambiguity. So we started going through the internet, and my husband passed away in July of 2018. So as we're doing this research in 2015, 2016, there really wasn't a lot on the internet as there is now, but we relied on, quote, Dr. Google. We told the doctors easily over 2 years before Eric died that we felt as though he had dementia with Lewy bodies. And my husband was a very smart man, a businessman, Harvard Business School graduate, and he documented how every quarter he had complete documentation that we'd review with the doctor of his physical symptoms and his cognitive symptoms. So with our own research from the internet, coupled with his documentation, we told the doctors we thought that he had dementia with Lewy body. And in fact, he had all the attributes except for delusions and hallucinations. Well, guess what? The doctors dismissed our findings. The seeming inability to fully engage with patients' observational data and an over-reliance on inconclusive biological tests were very frustrating. So I have two takeaways from this part of the journey. One is patients don't have to have delusions or hallucinations, especially in the beginning, to have dementia with Lewy body. Second is with no diagnosis, it's important to realize that the burden shifts to the patients and the families who are less knowledgeable than the scientists and the doctors to do their own research. And it feels like an unfair burden. I can remember saying, why are we doing this? We who are least knowledgeable, and particularly when we were seeing neurologists at a top medical center in Boston. It engendered resentment and anger, and especially when the patient and the caregiver turned out to be right. So the patient-doctor relationship became more strained and less trusting at the time of extreme need. So my final stage of this journey, the third part, is we had no sense of the expected time remaining. In fact, one of my husband's questions to me is, where do you think I am? We don't know what the disease is. And how much time do you think we have left? And I said, well, one of your doctors thinks you have Parkinson's disease. And he said the average life expectancy was 8 years. So my husband, being sort of a quantitative guy, said, is that the average or the median? So he still had his mental capacity and sense of humor. And I said, I don't think it makes a difference between the average and the median. So then he said, how many years, how long do you think we're in this? And I said, I don't know. And how do you know about life expectancy until you have a diagnosis? And we don't think you have Parkinson's. They thought he had Parkinson's with mild cognitive impairment. We think you have Lewy body. And I said, according to the internet, it's not as much as 8 years. It's 5 to 7 years. And I have no idea. And after the fact, I didn't realize the clock starts ticking before you even have any observable symptoms, which just was mind-boggling to me, but I didn't know it at the time. So in any case, we did not receive any guidance in terms of how to handle the confusion, the delusions, and the hallucinations, which ultimately came, although they weren't bad in my husband's case until the very end. We were not prepared. And while we had done some end-of-life planning, we should have done more earlier. We had a family reunion planned in which Eric was going to discuss his health, and he felt as though this would be the last reunion that he'd be able to do. The first day of the reunion turned out to be the day of my husband's funeral. Sorry. So there are two takeaways from this. One is patients and caregivers want to know a prognosis and what to expect. And the second is guidance for very practical approaches for managing delusions and hallucinations is important. So as a result, in conclusion of our frustrating journey, I became determined to try to move the needle on this terrible disease and hopefully help other families avoid the same experience that we had. Recently, I established the Lewy Body Research Foundation to shine a light on the importance of breakthroughs in the two areas that I felt were critically important to us, diagnostics and biomarkers. And obviously, biomarkers help to inform the diagnosis, to improve both the patient journey and really to prepare the foundation for developing therapeutic breakthroughs from the biopharma industry. And part of the interviews I've done and trying to understand the landscape of Lewy body is, and I'll overstate it a little bit, they're effectively blocked from doing therapeutic intervention. They can do symptom modification by tinkering with a lot of drugs that are already out there. But in terms of therapeutic intervention, they need two things. One is good diagnosis. They have to know that the patients that they're working with have Lewy body. And number two, quantitative biomarkers. I mean, it's wonderful that we have RT-QuIC and the seeding amplification assays, but that's only binary. So they need some sort of quantification of that. So my focus is trying to see what I can do more by convening, cajoling, and networking to push forward on breakthroughs in quantitative biomarkers, which will obviously improve the patient journey and hopefully have better long-term outcomes. So thank you for your attention, and I'm just pleased to be here. Thank you.
All right, if we could get the Zoom back on. Before we move to the question and answer, and we have some questions we've discussed in advance for the group, but if we could get, see, I think the Zoom rather than the slides. So before we move on to our discussion, I think it's easy to clap, and it's appropriate to clap for people in the room, but I really do want to acknowledge our first three speakers who were very vulnerable and shared. So thank you very much for those who joined us via Zoom today. So the first discussion we will have, and not everyone will answer every question. This really is, people will share when they have something they want to share. Many people have already discussed their diagnostic journey, and I think a number of people in the session have been very fortunate to get to their diagnosis early, though not universally. Are there challenges that you or your loved ones faced in getting a diagnosis that you want to further discuss or highlight today? Well, then I'll kind of make it broader then. So what are challenges more broadly, either with diagnosis or in care? What are some of the biggest challenges that you or your loved ones have faced in your overall care? We've heard some of these from you and what you've shared already, things like connecting to specialty centers. We hear that also from other people living with Lewy, also working with primary care that is familiar with LBD, or hospitalized settings where people may or may not be familiar with LBD. But what are some of the biggest challenges that you or your loved ones have faced about kind of the journey and care for the DLB? Yeah, go ahead. Juan.
Yes, again, like I said earlier, it's education and awareness. I mean, our challenges began when Jack was home, we live in Florida, and they had the Baker's Act. So if anyone tries to commit suicide for whatever reason, they have to call the police. And they have to be in a place, dementia unit, for 2 or 3 days. So when, they didn't know that as Jack dementia was going to make him try to jump out of the balcony. So when I called the psychiatrist for help, he told me, Juan, I need to call the police to inform him that Jack tried to commit suicide. It's a Florida law. If I don't do that, I can lose my license. So when the police came to our house, it was awful. It was one of the worst experiences we had. They were screaming at Jack, asking whether I was trying to push him out of the balcony myself. But anyway, it was a lack, even in the police force, it was a lack of knowledge of the disease. Second, Jack lives in a memory care unit, which I'm very happy with. And thank God we bought long-term care insurance many years ago, and that helps us with that. However, due to the HIPAA law, there are many patients or residents there that you're not aware what they have dementia, but you know whether it's frontal dementia or Lewy body, because they try to protect their privacy. But among the caregivers who are wonderful, there's lack of knowledge. Sometimes when they take Jack to the restroom, say, move people to the right, move the leg. And I tell the lady, excuse me, he has Parkinsonism. So even though he would like to move the leg doesn't move. So it's a constant education. And thank God I'm there all the time, because I don't want it to be, he's never abused, but I want it to be comfortable. So anyway, education, the medical level, the caregiving level, in every level.
Thank you so much.
I was just going to add to that a little bit. Most LBD patients wind up in the emergency room at some point. I would imagine my dad had a small stroke and he was hospitalized, and what they gave him caused a psychotic episode. There's not enough education among hospitalists, who are the, first line of defense about, the harms of prescribing a drug that might be fine under other circumstances, but it's really bad for a Lewy body person.
I'd like to add it very similarly to what Juan said and who just spoke, that both of those elements, the emotional, psychiatric, suicidal element of this disease is profound, and the necessary willpower, contracts you make with family members to assure that they're not going to do something. But the underlining comment is they're at that point where they feel like they can or want to, but for other purposes of religion and children and other reasons, they don't. But that the world outside, I think Daniel has said many times to me that he understands now why and how strong that element of the emotional need, because the disease at times is so horrific and is very difficult to handle. But you get through it with management, but it is an obstacle that I don't think the outside world wants to fully acknowledge. Is an element of denial there. Yes, we manage it, but it doesn't change the fact that they get to a place. They just want to maybe say, let's be done. I'm done. But of course they don't, he doesn't. And it's not easy. It's not easy. And even with medical professionals, when we did have to deal with ERs and things like that, or paramedics, Daniel very firmly said, I know what I have. I know what needs to happen. I need you to understand my disease, and I know what needs to be done. And I don't necessarily need to be hospitalized. I can go home and be fine. If he had had a fall, of course, that was understood. They wanted clearance that he didn't have a subdural or something like that. But the frustration level for him is very, very high, because he is that physician and he understands, and he'll ask the paramedics, and they don't know, and they don't understand. And okay, they brought in a physician to sort of talk to him one-to-one, and Daniel was very firm. I know what I have, and I know what needs to be done, but the bigger group doesn't necessarily always get that. You know, putting him on an emergency hold of 72 hours just to make sure he's cleared and everything is good. But a better understanding and or processes to be put in place to help that and facilitate an ease of perhaps just sharing and talking about those emotions for, okay, why are you at that place? And as a physician and a world expert in the disease, yes, he's on the other side, but that's the takeaway message. It's still not clear. People don't understand the immediacy and the importance of that and the intervention that needs to be in place to put something in place and let it not go beyond, you know, measures that if they wanted to could do still themselves. So that's a hard one, but I agree. Education, what Juan said, is critical. And it can't be clumped into the other dementias. It's its own unique dementia. You know, it's frustrating. You agree, Daniel?
I do agree, yes. One thing makes it more difficult in treating patients with Lewy body are the fluctuations. The patient can do very well in the morning and not do as well in the afternoon. And I find that to be very, in both myself and very disturbing and very, and that's some feature of the disease, which is very prominent.
And it's a very good segue to the second question about the loved ones, because I will say, you know, in the morning he's great, turned on and 100%. And a couple hours later, it's like, okay, what happened to you? Where are you? What changed? But that's the nature of the beast. And I don't have the pathology. So as the caregiver, I have to change. I have to make my tune different and recognize, okay, he's already shifted, but I have to shift back to a different level. And it's a real dance back and forth, 2 steps forward, maybe 1 step back. And that's a constant.
And I think that segues too to one of the other questions we had about unmet needs. So fluctuations are a real challenge, and we don't have a good intervention for that. So opening it up to the whole group, what are some of the unmet needs that you or your loved ones with DLB have now or have had across their disease journey? What are some of those unmet needs?
We think it would really be helpful if the expert LBD doctors or facilities have some kind of network where they have the other therapists who work, like the physiotherapists, the occupational therapists, etc. But even the other doctors that are needed in the care of the patient. Like my husband has complications from cataract surgery, and we see a specialist ophthalmologist. But at this point in time, I don't believe that he can help us any further, because he's given us a great report when he examines something, but then the vision problems that I see every day don't match. So I'm wondering if after all this time, the expert facilities, even the research centers of excellence, if they can't have like a list of providers outside of the Lewy body specialist area who know about it, who have some kind of experience that can help. And it would be awesome if we could have all of this in one facility, because travel and moving around does get really difficult after a time. So we have to go to the Lewy Body Research Center of Excellence, find a physical therapist somewhere else, get the vision person another place. And sometimes they don't agree. Is this hypostatic, orthostatic hypotension, or is this high blood pressure? There should we not have vitamin D? One says come off of vitamin D, another one says that's not a good idea, and we are left to make the decision. And as somebody said earlier, we have the least amount of medical knowledge in it. So the unmet need is to have the other providers who are so necessary for the whole well-being of the person to work together in one place if possible, or if the research centers of excellence themselves, if they don't have a list of people by now who they know are capable of dealing well with the Lewy body patient.
Very well said. By the way.
So one of the things that I think not only happens in DLB, but in other forms of dementia as well. But when you're living day to day with one of these disorders and you don't know how to plan for the future, it's incredibly concerning. And one of the things we're all told is that, oh, I don't know, it could be anywhere from 2 to 20 years that your loved one might live with a condition like this. Or you might find out, well, the typical person with DLB might live 5 to 7 years or 5 to 8 years. And that's still not enough information. What we don't get is we don't get clear indicators from our clinicians that the disease is progressing. There aren't milestones that they can leverage, because we haven't really established them through research about when an individual is transitioning from an early stage into a more moderate stage. Families need that information, and whether that's something that you as experts know and understand, I think it doesn't get translated down to the frontline clinicians, doesn't get translated into how you can prepare your patients and their loved ones. And so I think the ability to create a sense of where individuals are on their journey is one of the most helpful things that you can give to families. When my dad was sick, I had to imagine, well, okay, how do we sustain this, right? How do we create a balance where my little girls could get cared for, my husband and I still had a healthy marriage, my dad, his needs were being met, that I wasn't frantic and, running around in circles. And I had to say, well, okay, what kind of routine would I need to build if this was going to last for 5 years? Nobody could tell me anything. Nobody along our journey told us where he was, how he had progressed, what any of that meant to us. And that information is really hard to hear, but impossible to live without. So I would say that is something that the field, the whole dementia field, would do better to understand. How do we deliver that in a way that is safe, that is helpful, instead of just not delivering it?
Mm-hmm. Education, again, is extremely important, very much so. For example, the autonomic dysfunction, which is not attributed to LBD, but should be.
Oh, it is. Yeah, I think for us, you know, both being in the medical field and understanding it because we've helped other patients. I used to give support groups, but now we're on the other end. So it is those practical tools that I gather and put in my toolbox for us to go on a trip. You know, maybe consider doing a cruise so that we can manage items as they come along and have what's necessary. The autonomic syndrome that kicks in with Lewy body and the fluctuation and the unpredictability is the juggle. But for us, I have found, it's a level of management of unpredictability that if you have the tools necessary with you in your toolbox, and I'm using it as a metaphor, it's doable. And you can travel, you can do a cruise, and you both have to be in agreement to take that chance and be brave and courageous to take things as they come, knowing that anything can change on you. So the ebb and flow of forward and back, the duality in our relationship of the give and take is all a part of it, but never really understood, shared, or given over because we each do the dance together at a different beat to a different song and in different environments. So you just have to be able to go with the flow and live in the moment. Unlike other diseases, maybe you'll project and it has some more firm ways of what's coming, but I remember at Mayo, and it was said many times, one brain with Lewy body disease or Alzheimer's disease is one brain with that disease. No two are alike. And you do the best you can.
And I think there is always room for hope. You know, that's something that even though there is such a bad disease, there is always some hope, and hope is incredibly important. Mm. And I think so.
You just have to keep moving forward through the motions. You'll find times one has to we just hunker down, and for a little bit, you know, if it's the peaks and valleys, and when you're in your valley, okay, you have those activities you do when you're in your valley, and hunker down and get through it because you know the upswing is coming. So
you hope, and
yeah, and that's where that hope is. It's a real window that exists, and you're grateful for it because it comes, not by your speed, your date, your timing, but it comes.
Thank you. Oh, go ahead, Juan.
Yeah, another aspect, I need to be realistic here. What this lady talked about earlier, I'm sorry, I apologize, forgot your name. I would like to develop some indicators so I can have an idea. I don't want Jack to die, but to have an idea what stage is that. I mean, there's a financial aspect. Mm-hmm. I spend $12,000 a month in the memory care. Mm-hmm. And, you know, we have funds, but it's not unlimited. So I need to plan to see, you have to be realistic. So at the end, that's the point. You need to be, so it'd be great to develop indicators to give us an idea so we can plan for the future.
Thank you. So we have a couple of questions from the audience. So they're not ones that we have discussed in advance, but we'll ask them and then people can feel free to answer them or not. Do you want to read one of them out loud?
Put them down because your son is in your face. Mm-hmm.
Oh, sorry.
Can you turn on your mic, please?
I'll have her read it and then I'll repeat it. No, go ahead. So the comment and the question was someone from the audience mentioned that their family member had a really prolonged time to diagnosis, particularly because initially the symptoms, which were psychiatric, were attributed to menopause and depression, and the diagnosis was delayed, even though they had someone in their family with Lewy body dementia. And so I think part of the question was, are there differences in what we attribute symptoms to between people of different genders? But I think also, in terms of the panel, it further emphasizes the frustrations and the prolonged time it can take for some people to get to a diagnosis, which we definitely have heard from the panel and which is also reflected in interviews and surveys that have been done with people living with Lewy. I don't know that that was so much a question as a comment, kind of agreeing with some of what we've heard. Is there another question for the panel? So maybe we'll open up the question more broadly, and maybe a question for the panel will be, what kind of non-drug therapies have you or your loved ones accessed, whether that be rehab therapies or caregiver support, and did you get the specialty non-drug care that you've needed?
I think the rehab, it's a good step to take, rehabilitation. I never had rehabilitation, and then so I didn't think it was important. And now that I'm getting, I think that it's important, rehabilitation perspective, even though it doesn't seem to be important. It really is.
Go ahead, Juan.
Also, the cognitive activities, where Jack lives, they bring music to his floor, performance twice a week. And these residents, they really get engaged with music. They sing. We brought a violin player, they were crying. So that's not a medication, but it made him feel good.
And medications are so vague, I think, there's so, even though they're useful, they're not so much as one would hope. And I've been given every type of medication, including psychiatric and non-psychiatric and psychostimulants and and all of those.
And going back to the first comment they made on the audience, at the beginning we didn't know what was going on with Jack. So we had the orthostatic hypopressure. He was fainting, and we're going to the ER, high blood pressure and then low blood pressure. We had no idea he had Lewy body dementia. So we're working with a cardiologist and treating all kind of high blood pressure medications. Other ones to raise the pressure until we realize, wait a minute, that's a symptom of Lewy body dementia. And that's when but that just happened in the last 2 years. We spent like 5 years altogether dealing with this, not knowing that that's an indicator of his disease.
Yeah, I think just to help with some of that is what Daniel said, not only the rehabilitation, but just generalized exercise. Daniel, when it was confirmed, took it upon himself to start walking and had gotten up to a place of between 4 and 5 miles every day. And that he made that and said, quote unquote, you know, Dina, this exercise is what's going to keep me alive. And it's been true to that statement. He's not doing 6 miles a day every day, but I think it's the level of activity physically and mentally. So the miles he isn't doing so much. So we try to alternate the routine or the structure in the day where his mental activity is occupied and being stimulated with music. One, like you said, a concert. You know, he's an accomplished guitarist. He's playing it, inviting somebody else to have a jam together. Just any alternative stimulation that's not, you know, a medication induced one, but one of their choosing and liking. It's less than what it used to be, but it's still being engaged, plugged in. You know, yes, therapy appointments, but even simple everyday life activities, you know, going to the barber to get the haircut. I can do it at home, but getting you out, getting you dressed, attending to those things, the social qualities of things, talking to the other people. And it can be big and it can be small, but that generalized stimulation is, I have found, a great substitute for any kind of medication, but it takes time, thought, and planning to get it in. We still allow for a break of a rest or a nap. But then what else can we do? Where else can we go? Who can we see? Even just phone calls to folks, colleagues. How are you? They're so happy to hear from him, but 5 minutes of that can go a long way. And at the end of the day, it's okay, what did I do? Has a nice inventory of accomplishments that he took on his own. Sure, I said, did you call so-and-so? But you own it. It's his.
Thank you, Dina. We'll go to Colleen and Graham. Go ahead.
Yes. For us in the area of managing the hallucinations, we have had increased hallucinations, especially since we have traveled, and interactions with the hallucinations that was never part of the past. And then the experience of him talking to me as if I'm somebody else. And the information from videos put out by the Lewy Body Dementia Association, the webinars and the videos, and the advice from the caregiver support group, which is attached to the Research Center of Excellence in Miami, where we go, about how to redirect and maybe come out of the room and come back in and have and see it switch. Like he's talking to me as if I'm this person, and I come out the room and change up something and come in, and it switches something, and he sees me again as myself. That's something that's not medication that has helped. And also to change the environment. In that moment, maybe we go out for a walk, which is something he really loves to do, but we switch. So in the area of the hallucinations, which have become so much a part of every day now, that's a non-medication thing that we do that has been helpful and effective, and that came from the support group that we attend and the Lewy Body's videos and education materials that they put out.
Thank you. So we're in our last 5 minutes, and we discussed as a group that we would close by allowing people to say, is there a big topic that we have not covered yet today that you want to make sure that this audience hears about? And if we've covered kind of the main points, that's fine, but I want to open it up to our panelists. Is there one thing, and keep it short just so everyone can talk, but in our last 5 minutes, something we haven't talked about yet that you really think it's important to mention? Tish.
Yeah, hi. Oops, is it working? Yeah. Okay. First of all, to those of you going through it right now, there is a terrible, tragic situation of watching your brilliant spouse in this terrible disease. I feel for you, and I want you to know that. I also think it's very clear that everybody in this disease needs a strong advocate. And, you know, fortunately, people that we've heard from today have the resources and the ability to stop their life and deal. Not everybody has that. Moving forward, fewer and fewer people may have that. And how are we as a society going to be able to help? It's a real issue that I think it needs as much attention in the scientific community as it does elsewhere.
One of the things I'd really like to see is a greater focus on feedback from the community about what their experience with fluctuations actually is on a day-to-day basis. I think this is an area that could use more attention. I know that when I read some of the fluctuation scales, it doesn't resonate with what I saw in my lived experience. And I don't know that I'm alone. I also don't know that people might not agree with it. So I think it is something that now that we have more engagement of the lived experience, that's one area that we need to take a deeper dive into.
Same thing. So I'll just echo what Angela said. I think the fluctuations, both in cognition and in physical symptoms. For example, my husband all of a sudden had urinary incontinence. And we mentioned it to the doctors. Well, you know, again, that's a symptom of Lewy body. And then about 5 weeks later, he said, guess what? I don't have that anymore. It's disappeared. So it's not just simply the fluctuations in cognition that can happen, as many have commented on, in the course of the day, being totally lucid, let's say in the morning, and an hour later, you know, not being lucid. And it's not a sundowner effect. It's not that it happens at the end of the day. It can happen at any time. But it's also the change in physical symptoms, such as incontinence, such as constipation. And I said, oh my God, you know, I'm not getting enough fiber there. And then the visual spatial issues and how that can fluctuate. So, and it's frustrating to the patient, but it's also frustrating to the caregiver because you're not sure what you're seeing or that you are prepared to anticipate it. And then there's a sense of inadequacy. Of, well, gee, what should I have done differently, or how should I have anticipated this? So I think understanding the fluctuations in the disease, both the cognition and the physical side of it, would be really helpful.
Well, I want to thank the NIH for opening the session with the lived experience, and I really want to thank all of our panelists for the time that they spent with us today.
Thank you.
Thank you.
Thank you.
Does this one work? Can you hear me? No? What? So, this is a really hard session to follow our previous session. And for the people on the Zoom, thank you so much for that amazing conversation. So we're a little behind, so I'm going to try to keep us ahead. So I'm going to introduce all the speakers right now, and then I'm going to ask the speakers just to follow each other up to make it a little bit easier. So we're going to talk about the clinical features, distinct and overlapping, and you'll see some of the real challenges as we go through these symptoms, how hard it is sometimes to sort them out. So first up is going to be John Paul Taylor. He's going to talk about the current clinical diagnostic criteria, then followed by Brad Bove, who's going to talk about sleep disorders, and then Dan Weintraub is going to talk about psychiatric symptoms, and then Jennifer Goldman is going to talk about the motor aspects. Tanis is going to follow up with the cognitive aspects, and then we'll have a panel discussion. So I'm going to ask John Paul to come up and lead us off.
So this is not working. I don't know. Can you hear me? Yeah. Hold that one. Can I change? Oh, portable. Hey, it's clever, isn't it? Hey, yeah, I know. Great. Well, thank you everyone for the opportunity to speak to you today and to cover the clinical diagnostic criteria for DLB and Parkinson's disease dementia. And I'm going to be honing in more on the DLB side, given that that is the premise for today's and tomorrow's workshop. I think we've heard today that diagnosis is the foundation and the first part of adequate management. So what my talk is in essence, for a lot of you may be very familiar turf, and it's really an introduction to segue in then to the deeper dives, which are going to come a little bit later on, and some of the real high science. So let's go into the introduction here. I think the first thing to say is that the DLB has undergone a diagnostic evolution. And many of you may be aware, of course, of Ian McKeith, who has championed this particular direction of travel. And certainly, I think he might be on the call today as well, remotely. But in 1992, he proposed operational clinical criteria for DLB of senile dementia of Lewy body type. And then this was followed in 1996 by the first consensus guidelines for clinical and pathologic diagnosis of DLB. So that brought in the neuropathological criteria. This was further iterated in 2005 with the introduction of suggestive features to increase the sensitivity of the clinical diagnosis, including REM sleep behavior disorder, neuroleptic sensitivity, and dopaminergic loss and imaging. Finally, the most recent iteration has been in 2017, and that separated the clinical features away from the biomarkers, and furthermore, RBD was promoted as a core clinical feature. Why is this important? Well, the adoption of the consensus criteria has been embedded within DSM-5 and also ICD-11, and that's also true for Parkinson's disease dementia. And this has led to the opportunities of recognizing these conditions in terms of impacts on social care and healthcare. And furthermore, indeed, also then leading into clinical trials and those opportunities which that has presented, as well as reimbursement in those jurisdictions which require that. So what are the clinical aspects? So you have a dementia that occurs before or concurrently with Parkinsonism, or with a 1 year of the onset of the motor symptoms. So this is the so-called 1 year rule, which is operationally consistent between the DLB consensus criteria and also Parkinson's disease criteria. It is an arbitrary division which has served its purpose in terms of helping stratify patients for research and clinical trials. But as we know, it is controversial because we see a lot of patients who sit at that interface space between DLB and PDD. For diagnosis of DLB, clearly you have to have a dementia, and that's you have a progressive cognitive decline, which is of sufficient magnitude to impact on social, occupational function, as well as activities of daily living. Prominent or early memory impairment is not necessarily in the early stages, but may become apparent with progression, and I'm sure we're going to hear more about this later, along with perhaps a predilection towards deficits in attention, executive function, visual perceptual ability. So I'm just going to break up, in addition to the dementia, what other elements help the diagnosis of this condition. These include core clinical features, supportive clinical features, as well as indicative and supportive biomarkers. And this is from the 2017 criteria. It's a probabilistic approach to the diagnosis when one is looking at it clinically. Probable DLB, you have 2 or more of the core clinical symptoms, with or without indicative biomarkers to make this diagnosis, or you just have 1 core clinical feature with 1 or more of the indicative biomarkers. It's important to say at this point, the criteria mandate that probable DLB should not be made on the basis of biomarkers alone. Possible DLB is a more relaxed rubric. You might have 1 core clinical feature of DLB present with no indicative biomarkers, or you don't have any of the core clinical features, but you've got the indicative biomarkers. The important summary statement is really DLB diagnosis at the moment is based on the expression of the core clinical features plus or minus diagnostic biomarkers. So let's turn to the core clinical features. There are 4 of these, and as I hasten that, I'm the warm-up act, to a much more impressive presentation. So I'm really just going to outline these. These are fluctuating cognition or cognitive fluctuations, which we've heard about, visual hallucinations, Parkinsonism, and REM sleep behavior disorder. What I will turn to is the diagnostic accuracy of these clinical core features. And this is a great study from the Mayo Clinic looking at pathologically confirmed DLB cases with high to intermediate to high likelihood of Lewy body pathology. If you've got 2 of the 3 core features, fluctuations, hallucinations, and Parkinsonism, then you've got pretty good sensitivity and specificity in defining DLB. If you bring in REM sleep behavior disorder, the sensitivity bumps up a little bit to 88%. And interestingly, we've been hearing about fluctuations, but this can be somewhat of a non-specific symptom. It is actually hard for us clinically to delineate this symptom, and that might feed into this. So when you take it out, the specificity actually improves. What about the temporal sequence? Well, in terms of the temporal sequence of the evolution of the core symptoms, RBD is the earliest core feature to develop. And again, this is based on great data from the Mayo Clinic. The age of onset may also be differentially expressed between the sexes. In men, it may be earlier on, particularly if they've got with RBD. And if they've got RBD and Lewy body disease, they are less likely to have neocortical tangles. We're going to hear more about the sex differences, which I think are, and again, that came up in the earlier discussions. So what about supportive clinical features? These raise your suspicion of the diagnosis of DLB, but are not pathognomonic or necessarily specific for the condition or the diagnosis. So there's a raft of these. These include motor, autonomic, and neuropsychiatric. In terms of the motor, there's severe neuroleptic sensitivity. This used to be a very important and pertinent symptom for the diagnosis of DLB, but it's been taken down to a supportive clinical feature, mainly the fact that we are much more alert of the neuroleptic impacts in dementia patients, so we just see a lot less of it. We were hearing earlier about the autonomic aspects. Personally, I feel that this is a neglected area. A lot of our patients experience problems with orthostatic hypotension, repeated falls, syncope, urinary difficulties, constipation, sexual dysfunction, and these have enormous impacts. We've also been hearing about autoneuropsychiatric symptoms beyond visual hallucinations, systemized delusions, depression, anxiety, apathy. Another element is excessive daytime sleepiness. A thing which is also emerging is the aspects of hyposmia, and I know that there's going to be further discussions about this. And certainly objective testing of sense of smell seems to be very predictive of alpha-synuclein seed amplification assay positivity. So what about the biomarkers in the existing criteria at the moment? Well, looking to the indicative biomarkers, there are 2 imaging indicative biomarkers which are used. And against autopsy diagnosis, they have good sensitivity and specificity. And this includes the dopaminergic transporter scan imaging. We can see a stereotypical pattern of deficit there in DLB patients versus Alzheimer's, as well as cardiac scintigraphy or MIBG imaging. The third indicative biomarker is polysomnography, and that's the gold standard for the diagnosis of REM sleep behavior disorder. Supportive biomarkers don't have the same degree of specificity. One of these is structural imaging, where you might see a relative preservation in the medial temporal lobe in DLB patients compared to Alzheimer's. But in autopsy studies, this is not a particularly sensitive or specific biomarker. And indeed, medial temporal lobe atrophy doesn't rule out DLB, particularly as the patients get older. Furthermore, we're aware that medial temporal lobe atrophy, and more specifically hippocampal atrophy, is associated with Alzheimer's co-pathology. Functional imaging is another modality. SPECT perfusion or PET metabolism imaging, and we see a stereotypical posterior deficit in the occiput, with this also tendency towards cingulate sparing. And indeed, the cingulate island sign has been muted as a potential biomarker. In contrast to Alzheimer's patients where you don't have this preservation, it's been reported that there is a degree of good sensitivity, but more variable specificity. This may relate to the fact that the cingulate island sign may also be positive in individuals with PCA. But if you have got DLB and you're positive on the cingulate island sign, then that is probably associated with a more pure Lewy body case. The third supportive biomarker is EEG. EEG slowing occurs in DLB patients compared to Alzheimer's patients, particularly at the early stages. However, challenges remain with this particular biomarker modality. There's a heterogeneity of how we acquire EEG, what features we should be looking at, and a lack of validation studies. So this remains a supportive biomarker rather than an indicative biomarker. So I'm going to shift gears here and now speak about the MDS criteria for Parkinson's disease dementia, which were published in 2007. You can see they're very clinical criteria. We have the clinical diagnosis of Parkinson's disease coupled with a dementia syndrome of insidious onset and slow progression in the context of Parkinson's disease. Impairment in more than one cognitive domain, representing a decline from premorbid function. Clearly, it's a dementia, so you have to have deficits which are sufficient to impact upon day-to-day function, although the impairments can't be attributable to motor or autonomic symptoms. The criteria also focus in on what might make the diagnosis less certain. Perhaps there's another reason for the cognitive impairment, vascular disease, or the timing of the motor relative to the cognitive symptoms is unknown. So could it be DLB? The other aspects it comes in on is very clinical, cognitive features and behavioral features. So a typical cognitive profile, attention, executive, visual, spatial, and free recall impairment, coupled with at least one behavioral symptom, apathy, depression, or anxiety, hallucinations, delusions, excessive daytime sleepiness. My main take home from this is that the diagnosis is clinical or syndromic. It includes mention in the criteria for ancillary investigations, but not biomarkers. So again, shifting back to DLB is moving into that focus area of prodromal DLB. And this is really speaking to about the disease being a continuum. So even before the dementia, there is a prodrome, or indeed even a preclinical space where there is no clinical symptoms, but the disease is present. Clearly, this has got a lot of traction within the Alzheimer's space, but it still needs a little bit more traction within the DLB world. So apologies, just a slight slide dysfunction there. Speaking to this is the research criteria for the diagnosis of prodromal dementia with Lewy bodies. This is recognizing that there are many roads to Rome to DLB. We have a stereotypical cognitive onset, mild cognitive impairment, which then evidences as DLB. But we also see people who have recurrent unexplained delirium, who then manifest as DLB. There are other patients, as a psychiatrist, that I would see who present with a history of depression or severe psychosis, which then develop motor symptoms and DLB. And of course, we're going to hear probably from Brad about idiopathic REM sleep behavior disorder, which can antedate by years or decades the onset of DLB. Perhaps within these research criteria, the most developed aspects are that of MCI Lewy body. So this maps onto typical criteria for mild cognitive impairment. You have subjective concern from the patient, clinician, or family member, coupled with objective evidence of impairment in one or more cognitive domains. But the level of function is preserved or only minimally affected. What these research criteria do is couple it then with the DLB core clinical features, fluctuations, hallucinations, diagnosis of probable prodromal DLB or possible prodromal DLB. The criteria also talk about the biomarkers, but very much within the research context. And certainly more work is needed to be done in this space. And I'm just showing 3 exemplar studies here focusing in on MIBG imaging, DAT scan, or dopaminergic imaging, and EEG. What we are seeing is that sensitivity of these particular biomarkers is poor at the early stages, although the specificity may be high. Nevertheless, validation exercises looking at the criteria for prodromal DLB are building, and I'll draw your attention to a UK-based study as well as a US-based longitudinal study. In the US study, 2 or more of the DLB core features in the year before the dementia has got a pretty good accuracy in distinguishing prodromal DLB from Alzheimer's. In the UK study, probable MCI Lewy body classification is both sensitive and specific for the classification remaining either as probable MCI Lewy body or progressing to DLB for 3 or more years after the initial diagnosis. What about PDMCI? And I'll just very briefly introduce this. Again, it's predicated very much on a clinical perspective. Diagnosis of Parkinson's coupled with cognitive deficits, either on a global scale or on a formal neuropsychological battery. Deficits in a single domain or multi-domain cognitively, a gradual decline from pre-morbid levels, but deficits not sufficient to interfere with functional independence, or only subtly apparent if present. Again, the diagnosis here is clinical syndromic. There is mention of biomarkers, but they are not included within the criteria. So this segues into the biological definitions of Parkinson's disease and Lewy body related diseases. So we have the neuronal alpha-synuclein disease integrated staging system, NSD-ISS, as well as synergy classification, both published in Lancet Neurology of this year. Now, the rationale is very clear for biological criteria. We have got evidence for the pathological role of alpha-synuclein. Furthermore, there's the availability now of the alpha-synuclein biomarkers, as we were hearing earlier. And we know that a common pathobiology may lead to these heterogeneous or protein clinical manifestations, whether that be Parkinson's or DLB. And furthermore, it also speaks to the disease continuum, the disease starting before the symptoms emerge. The biological criteria also speak about biological neurodegeneration, dopaminergic deficits. They also include genetics in that context. And we have similar systems in terms of things for cancer and in Alzheimer's, the ATM framework. It's important to say that clinical features, because that's what this presentation is about, whilst discussed, are for staging rather than diagnosis or classification. Now, another thing which was intimated earlier was the impact of co-pathology. And again, we're going to hear more details on this later, so I'm just introducing this. Alzheimer's co-pathology is common across the Lewy body disease spectrum. 2/3 of DLB patients and 1/3 of PDD patients are amyloid PET positive. We also see lots of pathology when we take a look at post-mortem. And when you have that high neurofibrillary tangle burden, that reduces down to DLB diagnostic sensitivity. Furthermore, if the Alzheimer's pathology is present, that modifies the trajectory or prognosis of DLB. You have impacts on survival, for example. Yet, as was also intimated earlier, there is an opportunity here that patients with LBD might benefit from Alzheimer-related therapies. Now, I focus on Alzheimer's here, but other co-pathologies might be relevant, and this needs further work. Vascular, TDP-43 as examples. So I'll speak very briefly about similarities and differences between the diagnostic criteria, and I've also sort of tagged on the end the staging frameworks. I think the first important thing to say is that both the DLB and MDS are getting a little bit longer in the tooth compared to perhaps the biological frameworks. Looking towards the DLB and MDS PDD criteria, there's a predominant cognition and clinical symptoms focus, perhaps a greater focus on the non-motor symptoms within the DLB consensus criteria. And clearly, these are diagnostic criteria, hence diagnosis is a big feature, which is not so much within the biological frameworks. In contrast, the biological frameworks speak a lot more about staging and progression and that relationship to prognosis. They also speak to the neurodegenerative biomarkers and the more direct pathologic marker of alpha-synuclein, with a greater consideration towards the genetic impacts. There's also, we've always in the field had this arguments about lumping and splitting, and certainly the existing consensus criteria are all about splitting things and separating, whereas perhaps the biological frameworks are bringing things together. None of them are especially brilliant at talking about co-pathologies, although certainly the DLB consensus criteria does include discussion of this in the context of neuropathology. So this is a personal view just of some opportunities going forward, and this is my sort of final slide. I think that the incorporation of accessible alpha-synuclein biomarkers represents a real possibility, and I'll throw it out there. Should they be in the diagnostic criteria? Could it help improve DLB diagnosis and help us understand better the phenotypes? Maybe we need to be reevaluating some of the clinical features to the diagnosis. We're seeing a lot of data now coming out about hyposmia, for example. Validating the prodromal DLB groups, such as the psychiatric onset unexplained delirium cohort, that needs further work. And as I've sort of intimated as well, this emphasis on co-pathology as well as genetics is necessitated, I feel. I think the biological frameworks do offer an opportunity of bridging the DLB PD PDD gap which exists, and then by extension allowing clinical trial participation for disease modification. I think the focus in on dopaminergic biomarkers of neurodegeneration is great, but we need to also recognize that there are other aspects as well: cholinergic degeneration, noradrenergic, synaptic, glial, and I suppose expand the biological anchors beyond just alpha-synuclein to think about neuroinflammation, mitochondrial, lysosomal dysfunction. Finally, I think this is as Sandra was saying about the idea that we have got very binary biomarkers. The opportunity presents itself that development of quantitative biomarkers will help with staging, prognosis, and clinical trials. And that will segue into also new scales for clinical progression. So that's just my starter for 10 to get some discussion going.
Thanks, JP. Great intro. And I'll be speaking about sleep disorders in DLB. I really appreciate the invitation to talk on this topic. These are my disclosures. And this is the outline that I was hoping to try to present, but with 20 minutes, we're going to have to trim this down. But we'll try to focus and spend less time on obstructive sleep apnea, insomnia, restless legs, and periodic limb movements, but talk about some important sleep issues just as a framework to consider DLB, and really focus on daytime hypersomnia and REM sleep behavior disorder, because there's a lot that we know about it and a lot more we have to learn about it. And then that will be the topic for the future directions. So essentially all animal beings exist in wakefulness, REM sleep, or non-REM sleep. And these seminal articles by Mark Mawald and Carlos Schenk several years ago started to question, could some of the parasomnias and other neurologic disorders such as narcolepsy be explained by the loss of the boundaries between non-REM sleep, REM sleep, and wakefulness? And I'll come back to this point in a minute. These two co-authors also were the first to describe REM sleep behavior disorder almost 40 years ago. And John Paul already showed this evolution. RBD almost always begins years or decades prior to the onset of cognitive symptoms in DLB. And so I'll come back to this framework on the right-hand panel, RBD evolving to MCI of the Lewy body type, evolving to DLB. And then a key reference, John Paul led this with Lee Townsend and a few other folks, a pretty recent review of sleep disorders in Lewy body dementia. And I'll talk a little bit of some comments from this review article. I know this is a busy slide, but it really emphasizes the flip-flop switch of sleep wake transitions. Cliff Saper in Boston first described this mainly based on animal models, but it is really gotten a lot of traction. This is fairly busy, but it's basically implying that the framework it's a flip-flop switch. We're in wakefulness or sleep, and there's no wobbling on this seesaw. It's either or, and there's multiple nuclei as well as neurotransmitter systems that feed into this flip-flop switch. a key component is orexin, which is in the lateral hypothalamic area. And this is based on a lot of work in narcolepsy. And this probably does have applicability to Lewy body disease too. The loss of the orexin neurons in the lateral hypothalamus makes this flip-flop switch wobbly. And that can at least partially explain the hypersomnia, cataplexy, hypnagogic hallucinations, and RBD that are so characteristic of narcolepsy. We'll come back to that point. This also indicates the hypnogram of young people, older people, with a lot of changes, including less N3 sleep. That's the deepest stage of non-REM sleep, less REM sleep, more sleep-wake transitions. This is all happening as we age, and sleep efficiency goes down. All of those components are further compromised in the setting of Lewy body disease, and we'll talk about a few of those points in a minute too. So several years ago, we looked at polysomnographic data of almost 80 people that underwent, that had DLB, that had sleep-related complaints. And the bottom line is sleep disorders are very, very common in DLB. I don't think I've ever met somebody with DLB who does not have one or more sleep disorders, often that are not diagnosed. And if they're not diagnosed, they're not treated. Some main points from this review: AFNARs are very common. For those aren't familiar with AFNARs, arousals for no apparent reason. So there's arousals from snoring. So you'll wake up from a snort, arousals related to movement. So you have a leg jerk and you'll arouse and then fall back to sleep. But many people have these arousals for no apparent reason, and less than 5 is normal in the population, which seems like a lot in the normal population. But more than 5 was very common in this population. Sleep efficiency was poor. Most people in this room probably have 95% plus sleep efficiency, and that's quite poor in most individuals with DLB. RBD was common. Most clinical series show 80 to 85% of people with DLB have RBD, most of whom had RBD precede their cognitive onset. Obstructive sleep apnea was quite common, and periodic limb movements were common as well. And now turning towards excessive daytime somnolence, if you do just some simple clinical measures, so one that's used in clinical medicine quite frequently, the Epworth Sleepiness Scale, it's an 8-item questionnaire. You can ask the individual or a family member, what is the tendency to doze in those 8 situations? And then you add up the numbers, and a score greater than 10 is considered abnormal. And you can see that in DLB, the tendency to score high in the Epworth is much greater than in Alzheimer's disease dementia and in FTD. And furthermore, the percentage of people who have abnormal scores is much greater in DLB compared to Alzheimer's disease and dementia, FTD too. I should note that that last name is my daughter wrote this paper with Tanis and Adam. So she's starting her sleep psychology position in a few weeks. So very, very proud. And this was work led by Tanis Furman, looking at a more objective measure, the multiple sleep latency test, MSLT. This is where individuals are all wired up, have an overnight polysomnogram, and then they have 4 sleep opportunities to fall asleep. And most people take 10 minutes or greater to fall asleep in that situation. And you can see the Alzheimer's disease dementia were in the normal range. The DLB patients were far more sleepy. And so just some other common in DLB and is different from in other disorders. How do we treat EDS or hypersomnia? There's a number of agents. Some are non-pharmacologic, just optimize sleep hygiene, and then try to treat those sleep disorders that can contribute to a sleep fragmentation or reduce sleep efficiency. So treat insomnia, treat restless leg syndrome, use nasal CPAP for obstructive sleep apnea. And there's a common thought that people with dementia can't tolerate CPAP. That's wrong. It's wrong. Many, many people with dementia, even moderate to severe dementia, tolerate CPAP and they benefit from it. So it's an important point. Now, some of these ways to treat these elements are with various medications. and some of them do have side effects, but so this can be a challenge. On the flip side, if you treat everything that's disrupting sleep and a person is still sleepy, what can you do during the day to promote alertness? So phototherapy is one means, some light exercise. And this is where wake promoting agents come in. And this is controversial. Modafinil, armodafinil, methylphenidate, methamphetamine, they can be used safely and effectively. There is one small pilot data substantiating armodafinil, but there's not much work done in this area, and a lot more work does need to be done. It may seem counterintuitive that you would use a stimulant in people with obstructive sleep or with people with DLB who are sleepy, and it may cause problems, but it can increase alertness. And just like in narcolepsy, it can decrease visual hallucinations. So again, that link to narcolepsy we'll keep coming back to. Now, switching to REM sleep behavior disorder, I think most people in this room and viewing are familiar with RBD. This is a parasomnia where individuals seem to be acting out dreams. The dream content almost always has a chasing or attacking theme, and the person tends not to be the attacker, tends to be the defender. So trying to hold off or push things away or kick things away, and yelling, screaming, shouting, swearing can happen. Injuries to individuals and their bed partners can occur. We still don't fully understand this, and this is really important from a selective vulnerability standpoint. Why is RBD so common and so common preceding the other manifestations in the synucleinopathies and uncommon in the non-synucleinopathies? And we still don't understand that very well. Several of us tried to better understand what is the pathophysiology in humans underlying REM sleep behavior disorder. And so we worked with Dennis Dixon, Joe Parisi, Cliff Saper, and Heiko Brock to try to pool all the animal data and the limited human data and try to make sense of it. And it's hard to make sense of this because it's a complicated, but this is life with sleep circuitry all in this very small part of basically the brainstem. The main point here is most of the data and the data to date also substantiates this. The sublateral dorsal nucleus, which is just caudal to the locus ceruleus, and or the magnocellular reticular formation are involved in RBD pathophysiology. The problem is both of these nuclei are not well defined, so it's hard to see the borders, and so it's hard to do neuronal counts. And that's kind of standard for trying to do any clinical pathologic correlations. Now, this may change. I'll come back to this point in a minute. But you can see the sublateral dorsal nucleus on a human slide that's very close to the locus ceruleus. And glutamate, glycine, and GABA have been implicated in the pathophysiology. And again, the sublateral dorsal nucleus looks like that's the most significant nucleus involved with RBD pathophysiology, with those three neurotransmitter systems involved, with a new one, again, we'll come back to in a minute. How do we treat RBD? Most people, this is pretty easy to treat. It's rare to have people that are refractory to treatment. First, if it's not that common and the risk of injury is relatively infrequent, you don't need to treat it. So just being aware of what it is and just promote safety in the sleep environment. So move sharp objects away from the bed, put a cushion next to the bed, just some simple safety things. But if the frequency and severity warrants it, some type of therapy can be used. Just over-the-counter melatonin, usually, well, about half the time. Works about 3 to 12 milligrams per night is pretty well tolerated, but there's still about a 50% that does not seem to benefit from melatonin. Clonazepam works in almost every individual, 95% of individuals, but you can see the quagmire. You don't like using clonazepam in somebody with dementia. And so in our experience, using low dose clonazepam can be used safely and effectively. But when working with non-DLB experts, especially primary care physicians, they really don't like the idea of their patients being on clonazepam. So it's a problem, but it usually works. So either or both. There are a few others when these two don't work, which I won't get into. What about some other phenomenons, fluctuations, or even visual hallucinations? Could they be explained by some of the same sleep circuitry? And again, this comes back to Mahowald and Schenk. We know that elements of wakefulness are invading into REM sleep. That's what REM sleep behavior disorder is. So we're supposed to be actively paralyzed. We lose that normal paralysis and therefore act out their dreams. Could visual hallucinations be the flip side? So dream imagery of REM sleep invading into wakefulness. And then also the flip-flop switch being altered, contributing to daytime hypersomnia, cognitive fluctuations. These are provocative thoughts, but again, this happens in narcolepsy. This is pretty well understood, and it may have relevance to PD, DLB. So where to go from here? And in the interest of time, I'm just going to fly past this. Some recent data and what begs the question for further research. And a lot of this requires, to emphasize an earlier point, we need more human brain tissue of well-characterized individuals during life, people who have or had versus not these sleep issues. For example, this is work done by Leah Grenberg from UCSF. People with progressive supranuclear palsy, they tend to have insomnia and usually are not sleepy during the day. Contrast that to other disorders where hypersomnia tends to be a little bit more, but not even that much in Alzheimer's disease. In this particular paper, there was a differential degree of degeneration of these three wake-promoting nuclei. So again, could be contributing to insomnia and or daytime hypersomnia. And these nuclei have not been explored in any great detail in DLB. This article, I personally think this is a really, really cool article. This was just published a couple months ago by a large Japanese group. And they took mouse models and did a lot of manipulations to better pin down what is the REM sleep circuitry underlying REM sleep behavior disorder in the mouse. And they took that information, applied it to human tissue, who normal controls and those that have Parkinson's disease with RBD. And I don't have a pointer here, but if you look at the right side of the panel in the control individuals, that square is the sublateral dorsal nucleus. And you can see this new corticotropin releasing hormone binding protein. I never heard of this protein before until this paper was published, but these nuclei are in the SLD of humans. And you can see on the graph, they are largely degenerated in those with PD and RBD compared to normal controls. So this may not explain the whole picture of RBD. Glutamate, glycine, GABA still may be involved, but this population of neurons, if this is replicated, again argues that those neurons are selectively vulnerable to synucleinopathy pathology for reasons that we don't understand yet. And then another interesting line of work, this was led by Isabel Arnolf many, many years ago, where she had people with Parkinson's disease who reported hallucinations with or without delusions during life, and they were all wired up. And then they were being studied during the day, and they were asked to report if they were experiencing a hallucination or some experience which could be a delusion during life. And they were able to document that as they reported this, they were immediately preceded by being in REM sleep based on the electrophysiologic data. And so again, evidence that these REM sleep intrusions could be contributing. Now, we've tried to replicate this, and this is really hard work because of all the motion artifact. It's really hard to be confident that if somebody reports hallucination, they were right in REM sleep before, but it's a very provocative study, and it's been hard to replicate. But along that line, if you look at other sets of data, now this is not reported in every clinical pathologic series, but in this particular series, the number of orexin secreting neurons in the lateral hypothalamus was reduced in mild stage Parkinson's disease and further reduced in more advanced Parkinson's disease, again suggesting that loss of orexin secreting neurons could be contributing to hypersomnia and possibly even visual hallucinations at least in PD and presumably DLB. So where are we going, at least from the REM sleep behavior disorder and planning for prevention studies? And there are many groups now actively studying people with REM sleep behavior disorder prospectively. We're doing this in the NAPS program, North American Prodromal Synucleinopathy program, following, now we've seen over 500 people in North America with REM sleep behavior disorder at least once with a comprehensive battery. There are many groups, Michael J. Fox Foundation, who are working in this area, many in Europe, Australia, and in Asia. But if you do serial cognitive and biomarker assessments over time and anticipate some of them are going to evolve through an MCI phase or something similar to an overt syndrome, and it's shown by the blue line, if one or more biomarkers changes in the asymptomatic phase, we could use that for tracking in an intervention study. And we already have some data. I know Kajal and others are going to present some of this data tomorrow. But if you look at the mapping of the Braak staging, so RBD fits into the evolution of DLB according to the Braak staging, even though it was designed for people with PD, it works for DLB evolution too. And let's just choose two biomarkers, FDG PET, normal in clinically normal, essentially normal in REM sleep behavior disorder. As MCI develops, you start seeing some degree of hypometabolism shown by green, yellow on that PET scan, and then very clear hypometabolism as shown as that latter example. And then DAT, the same thing. The striatal degeneration decreases with advancing stage of the clinical syndrome. So these are reasonable markers to follow, and several groups are using that. And FDG PET hasn't really become embraced as this. It definitely should, and plugging for future RFAs for this. But so if we have these biomarkers and looking at this bottom panel, if a biomarker is changing in those with RBD and you start an intervention, then could you then demonstrate a flattening of that change of that biomarker? And that would be an indirect reflection of pushing out the eventual evolution, perhaps even preventing the development, because somebody will die from other causes before they ever develop DLB, PD, or MSA. And so this is the concept that many people are working on. And so this is just showing the NAPS program, comprehensive battery of clinical markers and biomarkers. And John Paul already showed this, and I'm sure Eche, you're going to be talking about this too. This fascinating and very poorly understood sex difference in not only DLB, but REM sleep behavior disorder. RBD is largely a male disorder, and the onset and the associations of RBD to other clinical features is very different in women compared to men, and we do not understand this. So this is a summary. Interest of time, I already repeated this, so I won't go through this again. But a lot of exciting directions to go from a research standpoint. And if we better understand the pathophysiology, obviously we can design therapies that much better. And so just want to thank many collaborators at for participating in research. Many other collaborators are support from NIH and several foundations. And thanks for your attention.
Good morning. I'd like to thank the organizers as well for the opportunity to attend and present. Let's see. I'm a psychiatrist like John Paul. I think we're probably the only two in the room. I'm not sure about online. Oh, I'm sorry, Debbie. I forgot. Unlike John Paul, where they call you, I think, an old age psychiatrist still. We're called geriatric psychiatrists here in the United States. I apologize. I realize now there's no monitor in front of us. So if I look left or right and not at you, no way around that other if I want to see what I'm presenting. If you set the table, John Paul, this is kind of a smorgasbord of psychiatric features. 20 minutes doesn't allow anything beyond that. But I will say that for those who presented on the lived experience this morning, very compelling. A lot of it was psychiatric in nature. So I feel like what I'm going to present is certainly relevant to the conversation. Okay. So I'd say it's the back of the envelope, but thanks to Tish, it was the front of a napkin. So this is by way of explanation. So I'm using the term Lewy body dementia, which I think is okay here. Most of the work that I do is in Parkinson's. So that's one reason, but also because it acknowledges that there's overlap between these disorders. We know now also that more research has been done in Parkinson's and DLB. I did just look this up this morning to kind of verify that. So I did a PubMed search for psychiatric and complications and these different disorders. So about twice as much research has been done in Alzheimer's in the psychiatric area compared with Parkinson's, and then Parkinson's versus DLB is 5 times more. So there's just more literature to draw upon in PD compared with DLB right now, and certainly more in Alzheimer's. And I did want to mention briefly the prodromal early disease stages. There's more of a focus now on both clinical and biological characteristics, the desire to intervene early, and it really does allow this assessment, the holy triad of cognitive, non-motor, and motor symptoms over time. So a little bit about prodromal and early disease. So some of this has already been referenced already, but this is an opportunity to work with Kate Wyman-Chick, who's done some very nice work looking at the NAC database and looking in the years leading up to a diagnosis of dementia with Lewy bodies. And here you can see these prevalent psychiatric symptoms in the years leading up. And actually, psychosis is not the most common of them. There's other things: nighttime behaviors, apathy, anxiety, depression, irritability. If you look at the DLB group, those who are diagnosed with DLB ultimately compared with Alzheimer's disease, you see again a differentiation for anxiety, apathy, delusions, sleep disturbances, and hallucinations. So what's the point here? Really that psychiatric symptoms broadly are more common in DLB compared with maybe Alzheimer's disease, but also in the years leading up to the formal diagnosis. We also have research criteria for prodromal Parkinson's disease, which are largely non-motor in nature, including depression and anxiety. So I highlighted the 2 psychiatric ones. Interestingly, the original prodromal criteria did not include cognition, but then when revisions came out several years later, cognition was added, and that was in recognition of additional prodromal research for Parkinson's disease that was able to detect cognitive differences. Fast forwarding to more late stage or dementia stage illness. So we know that there's kind of a common or similar psychiatric syndrome. I feel like I've lost my mind. Common psychiatric syndrome or overlapping syndrome for both DLB and PDD. And the most commonly reported features are psychosis. So this is a slide referencing that, both delusions, hallucinations, and what you really see is this continuum from Parkinson's disease without dementia to Parkinson's disease with dementia to then dementia with Lewy body, that the frequency of delusions and hallucinations just increase over that spectrum. I did want to make a note here that there's some things you see in Parkinson's that you don't really see in dementia with Lewy bodies, and those are things that are primarily related to the treatment of Parkinson's disease. So for instance, one common psychiatric disorder in Parkinson's disease are impulse control disorders, but because DLB patients are rarely treated with dopamine agonists or the large number of Parkinson's medications that PD patients are, you don't really see impulse control disorders in the same way, or the complications of deep brain stimulation because DLB patients don't undergo DBS. And this is work in Parkinson's disease, but what I really wanted to highlight here is that there's an appreciation now that although visual hallucinations have typically been the focus in both PD and DLB over the years, that hallucinations really can occur across the sensory domains. So auditory hallucinations are fairly common. It's interesting that Parkinson's patients invariably can't smell, but yet they can still experience olfactory hallucinations. And then if you add in more minor symptoms, passage, presence, illusions, which are probably less well studied in DLB than I think are formal hallucinations, you get these really high rates of prevalence of psychosis across both disorders. And there's even been research in de novo Parkinson's disease patients. These are untreated de novo PD patients, that rates of minor psychosis are relatively high compared with healthy controls. And I think that really, again, helps tie together the PD and DLB experience, because these are patients that are untreated with dopaminergic therapy. A little bit about assessment and management. Again, this is a smorgasbord. So in terms of clinical research studies, because I know there's an interest in improving that, increasing that. So we have formal diagnostic criteria and rating scales for various psychiatric disorders in PD primarily. There's some of these instruments have been imported from Alzheimer's disease, not surprisingly. There is a fair amount of rating scale work for DLB ongoing. I don't know if these two instruments I'm referencing will be discussed in this meeting, maybe. Brad can take credit for the first one, PSRS. John Paul can take credit for the second one, the LBD DRS. So this is ongoing work. Most assessment honestly happens informally in the context of a clinical interview and clinical care. It's important to have the informed other available for collateral information. And I mention that only because this is not often formalized in the terms of research studies, but probably needs to be. There's the whole issue of symptom overlap, which really bedevils us still. So what is disease-related psychosis versus delirium-induced psychosis? How to disentangle apathy versus depression, RBD versus psychosis. So what are perceptual changes occurring during sleep versus during the waking state? And then finally, the issue of differentiating disease from medication effects. So for instance, Parkinsonism is inherent to Parkinson's disease, also to DLB to some extent, but we also know that antipsychotics can induce worsening Parkinsonism. In terms of treatment options, so this is a review table covering really a range of psychiatric treatments and symptoms, and really showing basically that we're at the state where we have insufficient evidence for almost all the treatments that we offer these patients other than acetylcholinesterase inhibitors, for which there is evidence for efficacy. So just a little bit more about cholinesterase inhibitors and their treatment effect. There's some evidence that perhaps beyond improving cognition to a modest effect, that they may have neuropsychiatric benefit, whether it be delusions or hallucinations, other neuropsychiatric symptoms. This is a table on the left from a Japanese study using donepezil in dementia with Lewy bodies. And on the right is a meta-analysis comparing the effects of cholinesterase inhibitors for psychiatric symptoms, comparing those with Alzheimer's disease and Parkinson's disease. Interestingly, the benefit is greater in Parkinson's disease with cholinesterase inhibitors than in Alzheimer's disease, both the cognitive and the neuropsychiatric benefits. So when we're talking about treatment, particularly psychosis, but really beyond that, it's important to note that we're really not just talking about efficacy in this population, but safety and tolerability. And that's not often built into clinical trial design. Safety and tolerability is often just reported at the level of adverse events, but that's really not capturing the whole story often. So we now have this story for antipsychotic use in neurodegenerative diseases or dementia, where there's an increased morbidity and mortality risk associated with antipsychotic use. The morbidity risk is for cerebrovascular events. The mortality risk is for cardiovascular events and infections. This led the FDA to issue a black box warning, first for atypical antipsychotics and then for typical antipsychotics. And we also know that most antipsychotics, whether they're typical or atypical, often come with a host of other side effects that are of potential concern as well in populations such as dementia with Lewy bodies and Parkinson's disease. We had done some similar work using Department of Veterans Affairs data, looking at this risk in Parkinson's disease, and had shown something similar in this epidemiological study that patients with Parkinson's disease that were exposed to antipsychotics had an elevated 6-month mortality rate compared with Parkinson's disease that were not even controlling for covariates. So John Paul already referenced about antipsychotic use, that the admonishments or warnings not to use antipsychotics in DLB have been revised slightly, and that probably has to do with the shift from older typical antipsychotics more to atypical antipsychotic use. Really, the differentiating characteristic there is the 5H2 or serotonin 2 receptor to D2, dopamine 2 receptor binding ratio is higher with atypical antipsychotics, and therefore thought to confer some increased safety as a result. But still, the concern is about use of these medications in this population. This is just a table from a paper that Melissa led that I was involved with, just offering some practical advice about the pros and cons of using antipsychotics in this population. But I think the point really to make here is that this is not research informed. This was really our opinion as much as anything. So clearly there is additional research needed. There has been a little bit of advancement in terms of antipsychotics in the Parkinson's field. This is a study called the Harmony study. And what I'm presenting here is a secondary analysis from that study. This is using pimavanserin, which is a selective 5-HT2A inverse agonist that's approved for the treatment of Parkinson's disease psychosis. But this particular study was testing pimavanserin in a group of 5 dementia syndromes, including Parkinson's disease dementia and dementia with Lewy bodies. It was a positive study, but nearly all the positive effect was being driven by the Parkinson's disease subgroup in this case. There's also been a similar study using a kind of a sister compound called neotanserin in a mix of PDD and DLB patients that was negative, but it was really kind of a small, flawed study that I never saw published. In terms of other populations, we do know that there's some evidence for antipsychotic efficacy in Alzheimer's disease, psychosis, or agitation, including a recently approved compound called brexpiprazole, an atypical antipsychotic. Once you get beyond the efficacy, again, I think it's important to really look at safety and tolerability. This is just more Harmony data showing that in this case, pimavanserin, the compound I mentioned, it was safe from a motor standpoint. So looking at a Parkinsonism instrument, it did not have any effect on it. And then looking at cognition here using the mental state examination, there was no deleterious cognitive effects with pimavanserin use. Once you get beyond psychosis and antipsychotic use, you're really on thin ice here in terms of evidence. So in terms of other disorders and compounds for antidepressants, there's no randomized controlled trials that I was aware of for DLB or PDD specifically. Within Parkinson's disease, we actually have a fair amount of positive studies now for both SSRIs, that's selective serotonin reuptake inhibitors, SNRIs, or serotonin norepinephrine reuptake inhibitors, TCA, a tricyclic antidepressant, and even a dopamine agonist, all efficacious for the treatment of depression in Parkinson's disease. In terms of antidepressants for other use, there's a randomized controlled trial of citalopram for agitation in Alzheimer's disease. That was called the CITAD study. And actually, SSRIs are the first-line treatment for agitation in Alzheimer's disease. Brad was already mentioning about anxiolytic use, or specifically benzodiazepines, and the pros and cons of that. There's no randomized controlled trials that I'm aware of in DLB or PD for anxiety. There has been one small negative study of buspirone, which is not a benzodiazepine, but it's an anxiolytic in Parkinson's disease. But me as a clinician, confronted with often quite disabling, crippling anxiety in Parkinson's patients, do have to resort to using benzodiazepines sometimes, but always mindful of instability. But we really, again, have no controlled research to point to guide us. So this is my concluding slide. So psychiatric symptoms in Lewy body dementia. So a range of symptoms clearly occur, and even in early disease stage. There's an increasing prevalence as the disease progresses for most of these symptoms. We know more about prevalence than severity. Does a given symptom actually worsen in severity over time? They're frequently comorbid. It's rare to find somebody with just one symptom. They're associated with a range of negative impacts and long-term outcomes. We already heard about that this morning. I didn't have the time to discuss neurobiology, but they're mostly associated with changes in multiple brain regions, neurotransmitter systems, and neural networks. There are some comprehensive rating scales available or being developed. They often require treatment, not invariably, but often. There's limited evidence for non-pharmacological treatments. I didn't mention that at all, but there's a fair number of education and behavioral management techniques that exist. I know that's an area of interest for Melissa, and I think it's also more well-tested in Alzheimer's disease than in Lewy body dementia at this point. And then finally, psychiatric medications are used off-label, but evidence base is thin and risk for morbidity and mortality exists. And that's why there's one study I'd like to point to that I was involved in that I'm particularly partial to, which was called KDAD. It was a study of antipsychotics for agitation and Alzheimer's disease. And that was really designed as an effectiveness study, not an efficacy study. So the primary outcome was time to discontinuation of the antipsychotic medication. And that time to discontinuation could either be for lack of efficacy or for an increase in adverse events. And the study very nicely illustrated that antipsychotics do work for agitation and psychosis in Alzheimer's disease. That was the efficacy end. But those efficacy benefits were offset by the earlier time for discontinuation due to side effects, worsening Parkinsonism, other side effects. So at the end of the day, it was not an effective medication because the drawbacks offset the benefits. And there's clearly an urgent need for efficacious treatments across the range of these psychiatric symptoms in Lewy body dementia. Sometimes it may make sense to conduct a basket trial. That was the Harmony study I mentioned, was a basket trial because it lumped both DLB and PDD together along with other neurodegenerative diseases. And sometimes it may make sense to study psychiatric symptoms broadly. More and more Parkinson's disease studies are looking at neuropsychiatric symptoms as a group as opposed to just targeting one individually. So for instance, depression and anxiety, because they're so highly comorbid, it often makes sense to study them together. And that's it. Thank you.
Are these someone's? Dan, are these yours or no?
They were left by the top.
Oh, okay. Great. Well, good afternoon, almost everyone. Hopefully I'm not going to do this without slides, but oh, here we go. But I suppose I could have needed. So thank you, Deb and Nina and the organizers for the invitation to speak today. I'm going to talk about the motor aspects of DLB. And I think this session actually really highlights the multifaceted nature of DLB. Here we have psychiatrists, behavioral and sleep neurologists, neuropsychologists, and I think I'm a movement cognitive behavioral neurologist, often straddling the world of PD and DLB. But really today I'm going to talk about motor and Parkinsonism in DLB, trying to be more specific towards DLB. These are my disclosures. So what I'm going to cover and really just probably scratch the surface of this is outlined here in these different bucket items. So we'll hear a little bit of each of these. And I wanted to highlight some of the recent studies and work that's being done to help elucidate some of the new knowledge that we have about motor features in DLB. So motor symptoms, this probably is familiar to many of you in the audience. We talk about these as elements of Parkinsonism. The core clinical features of Parkinsonism include bradykinesia, so slowness and decreased velocity and decreased amplitude of movements. These can be big movements. These can be finger taps and small movements. We see rest tremor, rigidity or stiffness, and gait and postural impairment. These are sort of the hallmark that we associate with Parkinsonism across multiple disorders, including DLB. It's also important to notice that there are other common symptoms, and these are often the less reported ones, except patients and their families experience them, and often it leads them to see other physicians and healthcare providers along their journey to diagnosis. So these can include symptoms such as smaller handwriting, decreased arm swing. That lack of mobility can lead to frozen shoulder. Someone can see an orthopedist as perhaps even their first person on the medical journey. Balance issues, freezing of gait, falls, softer speech, reduced facial expression, and swallowing difficulties. I'm not going to talk about all of these today, but really to emphasize that when we talk about motor symptoms and Parkinsonism, there's a lot to unpack underneath that. Okay, so you saw this from John Paul earlier. These are the DLB fourth consensus report criteria. And where you see the big purple arrow is one of the core clinical features. So one or more spontaneous cardinal features of Parkinsonism, so bradykinesia, rest tremor, or rigidity. And then under the supportive clinical features, under the motor element, postural instability, or repeated falls. So I just wanted to call attention to the motor pieces of the DLB criteria. In addition, on the subsequent slide of the figure in the manuscript, DLB is less likely if Parkinsonian features are the only core feature and appear at the first time at severe dementia. So typically that's not the clinical picture we're looking at. We talked about the 1-year rule, so I don't need to probably beat the horse entirely to death on this one, but I think it's also a relative weighting of what symptoms we see and when we see them that really drives clinical management, often diagnoses, and so forth. But much has been done in the field to look at comparative motor features across Alzheimer's disease, DLB, and PD dementia. And so many of the studies actually are really trying to discriminate DLB from Alzheimer's and healthy controls. Some are to discriminate dementia with Lewy bodies from PD and or PDD. So this just summarizes a number of the features that give a comparison across the 3 clinically defined disease entities. We'll put it that way. So, typically when we think about DLB, we think much more on the cognitive and dementia neuropsychiatric angle as the predominant or defining feature, albeit with Parkinsonism as one of the core criteria. We know that not every DLB patient actually has Parkinsonism, and that is part of the problem, something for us to understand. The timing, whether or not you apply the 1-year rule or not, the timing and the relative weighting of that can be different. So PD and PDD, we typically think motor first and later cognitive. DLB, we think cognitive early, plus minus motor Parkinsonism. Rest tremor is less common in studies of DLB patients, suggesting it may be in about 1/4 of them. And again, many of these studies are small. We lack really robust longitudinal data on that. They have a tendency to have greater postural instability and falls. They tend to lack those motor complications that we talk about with wearing off and dyskinesia, and that can be multifold. So it may have to do something with the pathophysiology of DLB, but it's confounded by the later age of onset of these patients compared to your young 50-year-old Parkinson's patient. It's compounded by the medications we use to treat the doses. If we treat motor symptoms in DLB for levodopa are tiny, often compared to what we typically use in Parkinson's. Therefore, we may not see the dyskinesias are wearing off. Okay. Several studies have looked at just differentiating motor profiles, and I use this as an illustration to differentiate LBDs, really small sample size, we know, compared to AD, and looking at a balance and mobility score, gait, and hand dexterity. And you can see there are areas where AD has better performance versus LBD, and even some areas where PD may perform better than when dementia sets in whether it's DLB or PDD. So one question that I find interesting in this recent paper highlighted is, so what is the impact of the clinical phenotype? So we talked earlier that people start with 1 symptom or 2 symptoms and then collectively on their journey accumulate more symptoms, doesn't matter what symptom they start with first. And so I wanted to highlight this recent study. It's a multi-center retrospective study. One element I thought that was very nice is it included 2 movement disorder centers and 2 memory disorder centers, again, highlighting one of the silos we need to break down. And they categorized the participants by a predominant symptom, so cognitive, psychiatric, or motor. Of the patients, 310 DLB patients were followed over, about 7 plus minus 3.6 years. And at about a 3.5-year mark, they had the full picture. So they had cognitive, psychiatric, and motor symptoms. And they found that the full clinical picture was more frequent in the group that had the motor features at onset versus those who had cognitive only. It did not impact the survival, death rate, or mortality. But I thought that was sort of an interesting lens as we talk about disease modification and intervening very early. What do we know about some of these very early symptoms and where do they go? Another recent work looked at DLB subtypes based on their initial symptoms, dividing them into, again, cognitive and psychiatric, motor onset or mixed onset, and also looked at ApoE genotype. They found that Parkinsonism was present in 85%, again, supporting that not every person with DLB has Parkinsonian motor features. There were no differences in the clinical characteristics among the subtypes except for the onset symptom. And this did not affect the survival, but it was shorter in memory, and again, highlighting that gender sex difference of males. So I think some of the more recent literature, we're starting to, disentangle or try to understand what the trajectory of symptoms are. And I really wanted to just pull out the motor as best as we could from the DLB picture. So this is longitudinal data from the Arizona Brain Bank study, where they followed a large cohort of people with PD, dementia, Alzheimer's, and DLB, and they looked at the subgroup of DLB with and without Parkinsonian features. So about 65% of them were DLB plus Parkinsonism. And they looked at the Unified Parkinson's Disease Rating Scale, part 2 of activities of daily living, and part 3, the motor scores. And compared to the PD dementia group, the DLB with Parkinsonism group had faster motor progressions on the UPDRS over the 8 years, and it was driven by gait and limb bradykinesia subscales. And I think this is also important when we think about clinical trial development and measures and clinical outcomes. How do we understand what happens over time? So on a shorter snapshot, so that's the long-term picture. That's what happens over 5, 8, 10 plus years. What happens in the course of 6 to 12 months? And again, I think this is also critically important when we think about designing trials, which are not 5 years, 10 years, and so forth, but what happens in a shorter time frame for not only motor scores, but cognitive and psychiatric scores. And so this study looked at DLB and PDD patients who were followed at baseline 3 and 6 month assessments with several cognitive and neuropsychiatric scales, the UPDRS for motor, as well as the neuropsychiatric inventory. And after 6 months, so that's not a very long period of time, we know, there were significant changes with decline in cognitive and motor decline. And you may argue, okay, it's a point or two on the mini mental, how much does that really matter? But we know that drugs get approved due to statistically significant differences like this. And to highlight the motor element, a 3.2 decrease on the UPDRS-3, leading to an annualized change rate of 6.4 points for the DLB group. So I think, again, as we start thinking, how do we implement these measures? If these are measures we're going to use in trials, this gives us a snapshot of what should we be looking for from an intervention if it's going to move the needle. To highlight the line item where it mentions the inclusion of one or more spontaneous cardinal features of Parkinsonism here. Again, recapitulating the DLB criteria. And again, sort of applying that 1-year rule, if you will, to PD, MCI, and DLB, MCI, LB. That's another controversy still brewing amongst us. But what do we know about the DLB symptom evolution? And I think, Dan, you just mentioned Kate's recent paper looking at the NAC data set. So this is looking at those who converted to DLB. And their motor symptoms, as many of us know from acquiring data for this, are based on a structured clinical interview and motor exam. And so what you can see highlighted in yellow are really the motor Parkinsonian symptoms across 5 years, 4 years, 3 years, 2 years, 1 year, and at the time of diagnosis. And so even if you just look at the very top line, motor slowing and gait disorders, rigidity is present somewhere between about 50 to 75% of people going back even 5 years, largely with increases in the amount of those symptoms the closer it is towards diagnosis. I think this also supports the relative, less frequent occurrence of tremor compared to gait disorders, general slowness, and rigidity as well. Okay, so what about motor assessments? So how do we assess motor, whether it's in the clinic or research studies? And I think this is a moving target. This is an area that we need to fill in some of those gaps. So most of these motor assessments are snapshots in time. Some of them are historical data. Some of them are just by a clinician's observation and scales, looking at finger taps and hand movements and gait and speed. So traditionally, most of the studies, most of the trials have used the Unified Parkinson's Disease Rating Scale. Part 3 is the motor part. It includes the Hone and Yar stage, which has to do with presence of unilateral or bilateral symptoms, presence of postural instability on testing, or use of assistive device or wheelchair bound. It's been revised in 2008 to the MDS UPDRS, and that in current trials, we start to see that being used, but most of the older studies that we talked about from a clinical trial standpoint still use the UPDRS. There are other motor tests to consider. So looking at different elements of gait, breaking down elements of gait and balance, looking at dual tasks, so that combination of cognitive and motor tasks, looking at postural control, some of which using stability tests from eye open and eye closed conditions, looking at falls. And I think we're seeing a growing interest and research into quantitative motor assessments. So where can we harness technology to give us better snapshots of what's happening, not only when we see someone in the clinic at that moment, but also when they're out and about at home or in even nursing home or memory care facility, but all those in between time points. So I just wanted to highlight, these are newer scales that I actually found in preparing for this talk. They come from a group in, I want to say Taiwan, that developed a motor dysfunction questionnaire based on really historical kind of questions, which may or may not be fully adapted to Western language and audience. So with some caveats there. So they distilled from 13 motor associated questions to include 7 in their motor dysfunction questionnaire. And then they looked at this in coupling with dopamine transporter scans in the first paper, and then plus synuclein measures in the plasma. Again, we can talk about the CSF versus plasma to create a composite scale. I don't know if we'll see more of this work or not, but I thought it was worth highlighting what's kind of hot off the press in looking at how do we combine clinical scales also with biomarkers. We're also seeing more about automated and machine learning and assessments where people have sensors. This is one study looking at parameters measured from looking at sensors, someone doing hand-to-mouth tests, showing that greater impairment in DLB with speed, trajectory, target approach compared to healthy controls, and the other looking at posturography. So again, ways we can harness technology to understand motor elements. Sensors. So this is a brave new world of where we could go on looking at technology in clinical trials, in the clinic, and all those in-between time points. So this comes from the I might have spelled that wrong, metavalent agent that was studied from Eli Lilly. It was studied in a phase 2 randomized controlled trial, and they had a sub-arm where they used the Verily smartwatch. Kind of a pilot to see, is this feasible? Can we do this in LBD patients? And so 70 out of the 340 something LBD in the trial wore the wrist worn multisensory device. And they looked at 6 digital measures for both sleep and activity. So I think it's something that happens all the time when you look at sleep studies and actographs, but less so on the motor standpoint. They didn't separate in the paper PDD versus DLB, so I can't really tease out that part, but they found significant associations for the daily step count, daily ambulatory time, and total sleep time with some of the questions from the MDS UPDRS. So I'm just going to really touch very, very briefly on the pathophysiology because we're going to hear more about that in subsequent sessions. But just to illustrate that not only do we recognize the dopaminergic deficits and the presence of Lewy bodies and neurites that in the nigrostriatal system, which are probably responsible for many of the motor Parkinsonian symptoms, but that there are other areas in the motor cortex, in cholinergic pathways involved in attention and gait and falls that may certainly play a role in the motor features. So we may see that in some of the imaging studies. We may also see in some of the neurophysiology studies, and I'm not a neurophysiologist, but highlighting that we can pick up references to neurochemicals that we know are important in motor excitability, as well as others that might separate more into cholinergic circuits and cognitive aspects. All right, so I'm just going to spend a moment on management here and thinking about how do we approach this from a multifaceted way to address some of the motor features. So dopaminergic medications, we've grown to know more about levodopa in terms of its role in DLB. I think many times people are fearful of, and rightly so, of using levodopa or dopaminergic medicines because of the high risk of psychosis associated with it. There have been several studies looking at acute and chronic effects. One very early study that I did many years ago looking at the risk and benefit ratio. And really, I think the caution is there that of up to about a third who had motor benefits also had increased psychotic symptoms. Doses are very low. They're very tiny compared to what we think about in Parkinson's patients per se. And again, the side effects can be very real. That doesn't mean that we can't cautiously, judiciously use them in the right patient with appropriate monitoring. Other medicines have been looked at. Zonisamide, which primarily comes from several Japanese studies. It's an anti-epileptic. It's been used as an adjunct to levodopa, showing benefit in the UPDRS motor scores. Other trials really have been negative and few and far between. Just wanted to give a shout out to the Diamond Lewy toolkit that John Paul is part of that gives a nice kind of treatment algorithm and general principles associated with treating motor symptoms. So a few takeaways on that. I think it's okay to consider these medications under good guidance. Again, needing specialists in these areas who can manage side effects and appropriately monitor patients, establishing goals and expectations, as well as the pros and cons. And we talked or heard from some of the panelists about the role of rehabilitation therapies and exercise in their management. It is very near and dear to my heart, and I'm a big proponent of all of these aspects, but they're sorely understudied in LBDs and DLB. And so this paper just highlights a few of the studies. They're really scant and they include like 3 patients. So really hard to draw conclusions from that limited knowledge. And then here you can see a snapshot of recent trials in the DLB landscape. There are at least 3 in the motor domain. Perhaps, you can argue we can draw from what we've learned in Parkinson's, where there's been a lot of effort looking at motor therapeutics, but still more room to go to fully and adequately address. So in terms of challenges and opportunities, just a few closing thoughts on that. I still think as much as we know about Parkinsonism and motor features, we have great room and opportunity to really understand what they mean in the DLB defined population, when they occur, how are they different or how are they similar, and how do they impact the overall progression? Again, are there different associated biomarkers? I think there's room to improve the clinical outcome assessments and measurement tools and really harness technology and understand that better. And effective and safe therapeutics beyond levodopa, beyond zonisamide perhaps, without the neuropsychiatric sequelae would be really welcome. So thank you.
Is there a way to get the mouse to show? Okay, that'll work, I guess. Okay, I have a few times I want to show them what I'm doing. So, all right. No? Why do I have this problem? Read the instructions. All right. I'd like to acknowledge my colleagues at the Mayo Clinic, thanks to NIH, and also thank you to our patients and their families for partnering with us. Today, I'm going to talk about the cognitive features of DLB and prodromal DLB and the contribution of neuropathology. And I think this is relevant as we consider future clinical trials, as well as potential refinements to biological staging systems. Now, the primary pathology of DLB is alpha-synuclein, but Alzheimer's related pathology can occur. Now, A-beta 42 can accumulate in diffuse plaques, and those are common in DLB, but they're also common in normal aging, but not associated with cognitive impairment. When A-beta 42 and 40 form a dense core and have tau positive neurites, that's neuritic plaques, and those along with tau positive neurofibrillary tangles, that's the hallmark of Alzheimer's disease. And that occurs in about 50% of patients with DLB. Now, neuritic plaques are associated with cognitive impairment, but they're also highly correlated with neurofibrillary tangles. And high levels of tau in the hippocampus is associated with memory loss with or without amyloid. Now, in DLB, alpha-synuclein burden far exceeds that of tau or amyloid. When DLB occurs, Lewy body disease may be essentially confined to the brainstem and limbic regions, or may extend also to the cortex in diffuse Lewy body disease. Now, the limbic regions have a heavy synuclein burden. As far as the cortical regions go, the inferior temporal and occipital temporal, which includes part of the fusiform gyrus, have the heavier burden in the cortex. And when tau and amyloid occur in DLB, you can see that they can aggregate in many of the same regions as synuclein. Now, for a subset of patients, there's some evidence that indicates that there might be a bottom-up progression. And before the cognitive symptoms occur. However, there's also a subset of patients that might have a more limbic-centric progression. And in these patients, the cognitive symptoms may actually occur before Parkinsonism or RBD. And in fact, there may be synuclein deposition in the brainstem, but it may not reach the threshold of cell loss needed for Parkinsonism or RBD to be present. And as Jennifer said, some patients do not have Parkinsonism. And in this study, we separated out patients with Lewy body disease, whether they have AD pathology based on a high Brock stage or low Brock stage. And these groups have transitional Lewy body disease without AD pathology. And when we look at the time from cognitive symptom onset to when they develop their DLB core features, it actually is quite short. Within a year or so, these patients can actually get a diagnosis of DLB because they meet criteria. About 80 to 90% of those patients have RBD or Parkinsonism. This group has a diffuse Lewy body disease with AD copathology. They have a high Brock tangle stage, and they might have a longer duration of cognitive symptoms to when the core features are identified, 2 core features. And these patients, about 50 to 60% of them have RBD or Parkinsonism. So it might take them a little bit longer to get a diagnosis because they may not present with the 2 of the 4 core features as early as the others. Now, we need to do a better job at being able to identify these patients as well and as early as we can identify those. Now, this group here is an interesting group. They have greater AD pathology than synuclein, and they have very low rates really of core features. And when they do develop 2 core features, it tends to occur quite late in the dementia. Now, these 3 subtypes of Lewy body dementia of Lewy body disease have different cognitive trajectories. The patients who have brainstem and limbic only pathology have the slowest rate of progression. The patients who have diffuse Lewy body disease without AD pathology are more intermediate, kind of more along the lines of AD. And the patients who have dual pathology with both diffuse Lewy body disease and AD copathology have the most rapid rate of progression. And this study from Sweden showed that when they used CSF biomarkers of synuclein or AD, compared to normals, the patients who are synuclein positive and AD negative have the slowest rate of progression. This is their Alzheimer's group here. And then this group here is the equivalent of their AD positive and synuclein positive. So they have the most pathology and the most rapid rate of progression. So as we're considering clinical trials, I think we really need to keep in mind that different subtypes of Lewy body disease may have different rates of progression. So we're trying to identify change. We kind of have to understand who we're looking at. Now, we all know dementia doesn't just develop overnight. It's accumulation of neurodegeneration. And in the very earliest stage, a person may, preclinical stage, may have no cognitive impairment at all. And that's, as Brad mentioned, the isolated RBD group. Now, when cognitive impairment develops, but day-to-day functioning is preserved, that's mild cognitive impairment. And when the cognitive impairment interferes with functional independence, that constitutes a dementia. Now, I want to point out that the MCI stage is huge. So some patients who have MCI have very subtle cognitive changes. Other patients who have MCI are very close to transitioning to dementia. So the cognitive profile for DLB is pretty well established. Essentially, patients who have mild DLB have disproportionate attention and visual processing difficulties, but relatively preserved memory and naming. And for AD patients, it's the opposite. Patients have memory and naming difficulties with relatively preserved attention and visual processing. And this dissociation has reasonably good diagnostic accuracy. Now, when we look at our Lewy body disease autopsy groups, and in this study, we looked at composite scores. And what we see is worse attention and visual, worse attention and visual performance in the Lewy body dementia groups, Lewy body disease groups here without AD pathology, and this group with AD pathology. But in the AD and the AD predominant groups, relatively preserved attention and visual processing. Now, when we look at the memory and naming composite score, what we see is the AD patients and the patients who have AD pathology have worse memory and naming, but those who don't have AD co-pathology have preserved memory and naming. The Swedish study looked at different set of tests, but found that when you look at the CSF biomarker for synuclein, it's associated with worse attention and worse visual spatial skills, but is not associated with memory. And on the flip side, they looked at the CSF biomarkers for tau and amyloid, was associated with memory impairment, but not attention or visual spatial skills. And this study from Penn showed that naming was disproportionately affected in the DLB patients who had AD CSF biomarker. So when we look at the hippocampus, and this is a wonderful study from UCSD, and what they did was they took patients who had DLB with AD co-pathology, and they looked specifically at the hippocampus. Now we know the CA1 sector of the hippocampus is important for memory. When tangles accumulate in that sector in Alzheimer's disease, there's memory impairment. And sure enough, they found a relationship between CA1 tangles and memory in their patients. But what they also found was that some of these patients had synuclein in that region. Not a lot, but some. But it was enough to have an additive effect. And these synuclein accounted for memory problems over and above what was accounted for by tangles. So what they found was, in this situation, you have synuclein and tau in the same general region, having an additive effect on memory. So this raises the question, first of all, what is amyloid doing? Not sure. Secondly, why is synuclein hanging out with tau in the CA1 sector of the hippocampus? Don't know. And also, if we target one protein aggregate, how will it affect the other protein aggregate? How will it affect memory? If we target synuclein, will memory get better because we're targeting apparently situations where there's co-regional localization? Now, visual processing difficulties are a major issue in Lewy body dementia. Patients often will have visual misperceptions. And interestingly, one of the core features is a visual feature. Now, patients will have perceptual difficulties, not just due to motor problems or organizational problems, but actual true visual perceptual processing difficulties. And this may be related to greater damage in the perihippocampal gyrus, which has heavy connections with the fusiform gyrus. That's part of the extrastriate visual what pathway for object discrimination. The perihippocampal gyrus is also part of the where pathway for spatial or knowing where something is. So this circuit is heavily affected in Lewy body disease and may have a role. Now, patients who have visual hallucinations have worse performance on visual tasks, but patients can have visual difficulties and never develop visual hallucination. Here are a couple of tests that are gaining some traction that show some discrimination from DLB to AD and from DLB to normal controls. This fragmented letter test and the noise pareidolia task, both of which are involve identifying information that's kind of fragmented, finding a face where there isn't one, finding a face where there is one, or incomplete letters. Okay, so let's take a step back to the mild cognitive impairment stage. When we followed our patients who developed DLB and who developed AD dementia, we found that patients who had non-amnestic MCI, that was attention or visually mediated, were 10 times more likely to develop DLB. Patients who had single domain amnestic MCI were 10 times more likely to develop AD dementia. So this attention visual distinction between DLB and AD in the MCI stage still holds. This study from Amsterdam also showed that they found attention and visual difficulties early on that was significantly different in their MCI of Lewy body group compared to their MCI of AD group. But what was interesting was that they found a greater difficulty in attention and a more rapid rate of decline of attention. And as expected, they found the MCI AD patients had worse memory. Now, this study was a very nice study from the Newcastle group, and they also showed that MCI of Lewy body patients had worse attention and the MCI of AD patients had worse memory. But what they didn't show was an effect of visual processing. And it's unclear why. One possibility is that it might be test sensitivity, different tests were used, but I actually think what probably was the case was that they had MCI patients at an earlier stage of their disease. And we can see here with the Amsterdam data, it depends on where you are, where you're going to have some visual changes. And attention seems to be an early feature. And this wonderful study from the Montreal group looked at isolated RBD and what predicted phenoconversion to PD or DLB. And what they found was the attention measures, timed attention measures, trail making test measures were the earliest predictor. And what was interesting was 6 years before phenoconversion was when these tests started to first show impairment. Design copy, the rate complex figure copy also showed a difference, but the changes were about 1 year. The deficits were about 1 year before phenoconversion. Now, the second study here is very nice conformational study from the International IRB study group. And that includes 10 countries, a gigantic data set of patients with RBD who are followed over time. These patients have isolated RBD, and they also showed attention was the earliest predictor occurring 2 to 6 years before phenoconversion. So attention is really important in DLB. And as we heard earlier, you need attention to carry out any other task. And if your attention is waxing and waning, all of your other abilities will also wax and wane. And again, cognitive features here, attention, have some parallel to one of the core features, which is fluctuations. So what would be the basis for the dementia or for attention problems in DLB? Well, we've kind of hinted at or pointed to earlier that limbic regions are heavily affected. Certainly limbic areas like the cingulum and perihippocampus are very important. But the cholinergic nucleus spacialis of Maynard has direct projections to those limbic regions, as well as to the thalamus, as well as to the entire cortex, as well as to the hypothalamus. And cholinergic basal forebrain cell loss and cholinergic depletion is far more severe in mild DLB than it is actually in mild AD. It doesn't mean it doesn't happen in AD, it just happens a lot earlier. And it may be one of the reasons why attention and fluctuations are so prominent and can be prominent very early on. We know that cholinergic depletion can contribute to impaired attention, problems with alertness, and even subsyndromal delirium. There's also evidence that cholinergic cell loss can predict cognitive impairment in Parkinson's disease. Cholinergic basal forebrain volume was associated with visual and attention scores in these newly diagnosed Parkinson's disease patients. This other graph shows that when you look at cholinergic uptake, patients with DLB and PDD have severe cholinergic depletion. But IRBD and the PD patients also have impairment in their cholinergic uptake compared to normal controls. Volume loss in the nucleus spacialis is associated with lower cognitive function in MCI of Lewy bodies, but not in MCI of AD in this top study, and is also associated with cognitive and attention impairment in patients with isolated RBD. interesting study where they looked at isolated RBD patients. They followed them for 3 years and found that the patients who did not decline over those 3 years had reduced cholinergic uptake. But the patients who had some cognitive decline based on their Mini-Mental and MoCA, just, some scores dropped, showed much more pronounced reductions in cholinergic uptake. So so what I want to point out here is, I think what's important here is we need to consider the basal forebrain and cholinergic depletion when we're thinking about other ways of biologically identifying early stages of DLB. So just in summary, just rates of cognitive decline depend on path burden. I think we need to be aware of that. Alpha-synuclein seems to be responsible for attention and vision. Tau seems to be responsible for memory and naming. And attention is very early, and we need to get a better sense of what tests are useful and what kind of overlap there might be between the pathologies. And lastly, should cholinergic integrity markers be included in biological staging of neuronal alpha-synuclein disease? Thank you.
Okay, people come up with a final discussion.
You could even sit too if you want.
So I don't know if there are any questions from the audience, but Michelle, yeah, you have a question? Yeah. Yes, now, go ahead. It was green for a second there.
Give it another chance.
Yeah, this one works. Oh, this one works. Okay. Yeah. So it's come up a number of times now, the cholinergic system, and particularly JP and Dan, and also Tish in your discussion of response to cholinesterase inhibitor. Are we thinking that the cholinergic deficit is because of comorbid Alzheimer's changes, which you sort of implied, JP, but didn't say that? Or do we think it's really intrinsically part of the disease, which you sort of implied in your last talk? And if so, should responsiveness to cholinesterase inhibitors be part of the criteria?
Oh, the green light works. Brilliant. No, I mean, I think that in terms of the pathology, and again, there's neuropathologists who are in the audience who will be able to comment on the basal forebrain, but the alpha-synuclein node within the basal forebrain can clearly have an impact on driving the degeneration there. I think the other aspects to say as well is that there may be a differential pattern of changes within the basal forebrain, the MBM, that you might see between Alzheimer's, DLB, and indeed Parkinson's, and there's been a number of studies that sort of suggest the slicing and dicing of the areas of the basal forebrain. So I think that that is one point. I'm not quite sure whether you could use cholinesterase inhibitors as an element in the diagnostic criteria, because Alzheimer's patients show a great response to cholinesterase inhibitors as well, and it's maybe not as obvious as you might see in DLB patients, but it is still present. And certainly we know that they will get, neurodegenerative changes in the same areas. So that would be my points. I don't know if Tanis, you want to.
Well, I do want to say that anticholinergic agents can be devastating to Lewy body patients, much more so. Don't negatively affect patients with Alzheimer's or any older adult, frankly. But it does. There's definitely evidence that when we lower acetylcholine even just with a burden, 2 or 3 medications can have a gigantic anticholinergic burden, and that can trigger not only cognitive difficulties, but confusional episodes and visual hallucinations as well. Sorry.
I'm just reminded of like Nick Bonin's work that demonstrated that even in early Parkinson's without significant cognitive impairment, there's prominent cholinergic deficits looking at various imaging modalities. So I don't think it's probably likely explained just by comorbid Alzheimer's pathology, because that co-pathology isn't so prominent until usually typically later in the course of cognitive impairment in Parkinson's. And these deficits happen early on in the illness. And they're probably diffuse well beyond the nucleus bacillus, the cholinergic system that's impacted.
I was just going to add that I think the treatment response is a potentially tricky one just due to the non-specific nature of it and the lack of robust measure of that. But I think what could be worth considering is what are the markers of cholinergic denervation that we can measure from in vivo biomarkers, whether imaging or others, and working to make those more mainstream and not just isolated research basis in a couple of people's labs would enhance perhaps some of those biological definitions.
Great. So we did talk about a bunch of features, right? We covered motor, psychiatric, cognitive, sleep, and behavior. But I think one of the other things we didn't talk about at all was obviously autonomic features. I was just mentioning to Jen before that the neurology continuum for neurodegenerative disease is coming out next month. I wrote the DLB chapter, and the editor took out the autonomic checklist because he said that neurologists already know all about that, and we didn't need to include that. But what other features of the disease, as experts that we see patients, what other features of the disease do people complain about that we didn't talk about today? And how do we address those? Brad?
I'm just curious, having seen some over the past few years, prominent anxiety that is refractory to everything. And what's the mechanism? And if you've tried almost everything, what else is left? So I'm being a little selfish here, looking for guidance. So prominent anxiety.
Okay. Dan, we'll just go across, everybody can. Yeah.
I would agree with Brad about the anxiety. I mean, I touched on it briefly, but that is a huge problem, particularly within Parkinson's disease, of course, but I assume DLB as well. We briefly mentioned apathy, but I think that's one that comes up day in and day out from care partners, particularly about the lack of motivation and initiative and what to do it. And we know so little about it, and including how to intervene.
JP?
Yeah, so I mean, one of the things which has come up quite a few times actually is visual symptoms. So intermittent double vision and other problems of, acuity, which is again fluctuant. I think is one of the things which is sort of interesting. I think apathy is, to my mind, one of the biggest challenges. And the other thing, which is I'm always struck, I see patients predominantly in an outpatient setting, but when I speak to my psychiatry colleagues who are inpatient doctors, they talk about some very severe refractory cases of people with DLB who, don't respond to anything. And I do wonder again, is there another group which is very rapidly progressing, which we perhaps don't necessarily see within our clinics per se?
Tanis?
Well, it was touched on earlier, but Capgras syndrome is a misidentification where the patient may not always recognize their loved one. Usually it's the person they're closest to, spouse usually. And in our sample, it's about 30%. So it's not super common, but it's definitely reasonably common. And I think one of the caregivers earlier today did a very nice job sort of explaining some of her tips and suggestions of, leave the room, come back in, turn on a light, go for a walk, do something else instead of focusing on it, introduce yourself. One of my favorite things that I tell people to do is just talk about, tell me about your wife, what's she like? Hope it's good. But I think that's something that patients and family members often aren't really sure what to do, and it is fleeting. It's not that it's all the time. It seems to come and go. So I think that that's important too.
Yeah.
Great. So I'd add fatigue to that tricky, amorphous, vague concept of fatigue, whether it's mental or physical, but something that doesn't fit as nicely in any of these boxes, that overlaps a bit with sleep, it overlaps a bit with depression and mood and cognitive as well.
Great.
Jim, one more over here.
Yeah, sure.
As long as we're doing our laundry list. So one that comes up, and maybe for me more than others as a psychiatrist, but it's almost like a taboo subject, but I would say it falls under autonomic maybe, but sexual function. I mean, issues of intimacy, but literally sexual performance for both men and women is so prominent and often kind of goes unspoken. Maybe it's more so in Parkinson's because patients are often younger and not so cognitively impaired, but I assume it's quite relevant to DLB as well. And it's just, it's such a huge topic, I think, but it's often just completely ignored or unaddressed.
Anybody else have a laundry list they want to go to? Yeah. Okay. There's online questions. Deb, you had a question? Or okay, so we'll take those. Okay. So alpha-synuclein in the CA2 region.
Yeah, you can hear me now.
Yeah.
Okay.
Yes. What about alpha-syn and CA2 region?
That's a great question. We have no idea what the CA2 region does. There's some suggestion it might be related to familiarity memory, but like theory of mind type of things, but we really don't know. But it is interesting that it's more in this hippocampus, the CA2 and the entorhinal cortex are more heavily burdened with synuclein.
Melissa, you had a question?
Into the literature, and is it going through? Yeah. And understanding the timing of intervention. So whether that's weight loss, whether that's actually getting a CPAP, do we have any longitudinal data to help to see what that does to the risk for DLB?
It's a good question, but complicating matters even further. There's central sleep apnea and mixed or complex sleep apnea. And so, and CPAP alone isn't sufficient. So auto PAP plus or minus oxygen. So that whole PAP element to sleep apnea management in general. But looking at the AD field, there's growing data that treating OSA may impact amyloid deposition. And so could that be relevant to synuclein? It's an important hypothesis, has yet to be tested though.
Okay.
Yes. Has orexin agent use, for example, suvorexant and DLB, been examined?
Thank you. I think all case studies anecdotal. I'm not aware of, and it is being studied in AD dementia, but not in DLB, to my knowledge.
I would like to add something,
Okay.
is it possible?
Irene, go ahead.
Hi. I think another aspect to consider is orthostatic hypotension that occurs early and not always, but very common, and can influence the treatment of the Parkinsonism, as well as in the long run affect cognition, and at times actually in the short times, and leads to syncopal events that are events that patients may have as well.
Thanks, Irene. I think the autonomic symptoms, as Jim alluded to, are such an untapped box and so important, and contribute secondarily to, as you mentioned, the cognition, whether it's short-term or long-term, falls, all sorts of risk, even probably the fluctuations to some degree. And I think also we need to be mindful of any of the medications we think about using that we don't exacerbate that, whether those are the cholinesterase inhibitors that we talked about or any of the dopaminergic ones.
Great. So I was going to ask it. So, you treat one symptom, you worsen another symptom. So I wanted to get your perspective on sort of the antagonism or interaction as you're trying to do the best you can for the patient who complains about a symptom and the consequence on other symptoms. So cognition on motor, motor on behavior, everything on blood pressure, et cetera. Brad?
I think the approach a lot of us have used is working with patients and families. What is your priority list of issues? And you treat number one, see them back in a month or so. If that gets better, then everything rises to the top. Treat the new one, and you spend months going through that manipulation. Some of them will worsen something either expectedly or unexpectedly, but that comprehensive longitudinal approach, optimize it, takes months, but it's worth it.
Yep.
Really in Parkinson's again, so one example I mentioned before, dopamine agonists. Dopamine agonists can potentially improve mood and apathy. They can also cause impulse control disorders, psychosis, and sleepiness. Antipsychotics can improve psychosis in this population, but it can worsen Parkinsonism and cause other side effects. And I'll default back to the point I made before. That's why I think an effective trial design is really quite helpful sometimes, because you're not just looking at efficacy as your primary outcome and adverse events in some separate universe, but you're combining them together into a combined primary outcome.
I'd just add to that. I mean, it's clearly an alliance between clinicians, patients, families to have that discussion about what the priorities areas are. I think the other thing which was alluded to this morning, very loud and clear, is about education. And it's our duty as clinicians to sort of say, these are the panoply of symptoms that might occur and, what we best suggest to manage that. And then it's a sort of as I say, an alliance of working out, well, I'll take this risk with this drug because that will help with my movements, at potentially the consequence that maybe my thinking ability is go down or I'm more sedated. So I think it's that partnership, that alliance, which is absolutely vital, and everybody's on the same page of what the range of different symptoms are. So it's not a surprise.
Dennis?
Well, I don't prescribe medicine, but apparently I don't talk on the microphone either. Okay, I don't prescribe medicine because I'm a psychologist, but one of the things I do with every single patient is we go over their medicines together, and I look to see, are there any medicines on here that I'm worried about from a cognitive standpoint? And then I recommend that, for example, again, not to belabor the anticholinergic angle, but if they're taking anticholinergics for a variety of reasons, as we know, they can be used for many things. Are there some other options? Patients have incontinence. Are there some other options instead of these ones that do cross the blood-brain barrier? Are these ones a little bit more tolerable for patients? So that's one of the things that I do.
Sure. So I call this management whack-a-mole. That's really essentially, it's one thing, something else pops up. But in all seriousness, I think part of that message is the education of the risks and benefits and having that decision-making dialogue. I also think it's a good plug and opportunity to talk about the multidisciplinary care element, that it's not just any one healthcare provider. And we think about medications, non-pharmacologic therapies, really that team approach for other strategies that can be used, from, everything from pelvic floor training when you're talking about urinary incontinence and other things for the home and the environment and so forth. So not an easy challenge.
Deb, is there another one?
Yeah, we have a few more. I think you just address this one, which is you have spoken to the buckets of symptoms. Can you comment on how the symptoms interact to complicate management efforts? So I think it's the same question, but from the symptom standpoint. Then we have a question, could psychedelics be effective to manage anxiety, depression, and LBD? Pros, cons.
I was going to ask Tanis this because I wasn't thinking of psychedelics specifically, but we're also asked commonly, I think all of us, cannabis use, CBD, THC, and it's very commonly used in Parkinson's now for sleep, for pain, for motor symptoms, for anxiety. And I don't know. I don't think we have, I guess I'll take the easy way out and say we don't have much literature to support the pros and cons of that. And that would certainly extend to psychedelics as well. But there is, I will say, a revolution in psychiatric treatments ongoing. And this is not within this field, but just in the general population. And that includes a lot of these novel stimulation therapies, psychedelics, cannabis, novel mechanisms. That it's really going to quite impact our field as well, I think, over time.
And it's not just the psychedelic part. So there's actually a large program in Alzheimer's disease for agitation, not getting the psychedelic part, but attacking the cannabinoid receptors. So it may not have anything to do with the psychedelic component, it's the receptors that these drugs attack. And so if you design or drug the compound correctly, it's possible to get action at the receptor without the untoward effects that may be deleterious to the patient.
I have one more. Some of the other common symptoms include frequent falls and dysphagia. Notably, these symptoms can occur early in both PD.
You're on.
In both PD and DLB. Any insight or comments? So falls and dysphagia.
They happen and they often happen. They happen and they often happen early. And I think was brought up is that, it's important to talk to the family and the patient, find out what's important to them, sort of prioritize that list, as Brad said, and then begin to address them in a logical fashion. But I think several of the panelists this morning highlighted how important it is to, PT, OT, speech and language pathology, exercise, working with the trainer. I mean, there's a lot of things that we can do that aren't necessarily within the doctor's office. And it's just so important. I don't think we utilize those services nearly as well as we could. Other panelists?
Happy to make a comment. I think early and often comes to mind of early awareness and recognition and asking the questions, even if someone's hasn't had the disease for terribly long. These are not just late stage phenomenon. And with that coupled early screening by people who can do more detailed assessments, like your speech language pathologist, like your physical therapist, to actually go through some of the measurements and screening and then implement training and other programs. So.
Yeah, one thing I'd love to bottle, as it were, is social interactions. I mean, again, we see time and time again when we do some of our social prescribing to attend various groups, whatever they may be, align with people's interests. They just transform, and people describe how they are much more alert, engaged, and involved. And I think that has a profound effect. And we haven't done enough research to understand the impacts of that, but it really does make a big difference. And we certainly heard about that this morning. So
I wanted to also, we have a couple minutes left. I wanted to also sort of address what you thought about insight and anosognosia in DLB compared to AD. And, anecdotally, there's some thought that one DLB may be a little higher prone to suicide. Is that because they're experiencing symptoms, or is that because they may have more insight that they're undergoing a disease? So, thoughts?
This is one of the tough things of the illness. Some people may have some degree of anosognosia, but awareness is painfully sharp in most. It just adds to the burden and stuff.
Anybody else? Any other questions from the audience?
returning to that question about the order of operations, which things to prioritize, what to treat. I just wonder if this resonates with anybody else, that if the patient isn't sleeping well, nothing else works. So my approach was always, do everything you can do to regularize the sleep first and then approach the other symptoms. Does that resonate with anyone else? Yes.
Oh. That also emphasizes, most people have some degree of obstructive sleep apnea. And so get people on CPAP or some PAP. And then many have restless legs. Try to manage that. I see this situation quite a bit where no formal sleep assessment is done, but they go right to, for example, Ritalin because of sleepiness. That's not going to work until you make their sleep better, and you may not even need any daytime med. So yeah.
Okay, so just before lunch, I'll ask all the panelists maybe if they have a closing comment or statement. Since we started that table, the end of the table for most of it, Jen, you go first.
Lots of lead time on there. Thanks, Jim. One I think is it takes a village. I think this conference illustrates that remarkably from the session prior to ours, from our session. And while we appreciate and recognize so many facets, both from the pathology, pathophysiology, and clinical syndromes, we still really haven't cracked this nut. So more for all of us to do.
I don't really have much to add, to be honest with you. I think that I really don't have much to add. Go ahead. You have more to say.
Well, I think one of the things which came out this morning is the necessity for good clinical care, good early diagnosis, and that's an important thing to emphasize. I think the other element as well, I know today and tomorrow there's going to be a large emphasis on disease mechanisms, biomarkers for disease modification, but also what we're hearing is as well is symptoms, management of symptoms, getting on the day-to-day, dealing with the condition as it fluctuates. And, I have to say, non-pharmacological interventions and that broader elements, aside from the pills and potions that we prescribe, is actually probably more important.
I want to hear more about potions later, so
I'm very happy to share them.
Dan?
Just thinking about NIH hosting this meeting and industry being here. So it seems like the most valuable time I spent, I feel like sometimes, is encouraging people who are designing studies, funding studies, to make sure that the range of symptoms are covered and assessed, because these are such valuable research project studies. I feel like lending the expertise of those that have it to industry to help design adequate clinical trials, because these are incredibly complex studies to conduct, as you know, Jim. And I think sometimes they're not as well designed as they could be. And we want to see them succeed when they happen. They're such precious studies overall. So I think, those are the other thoughts that come to mind.
And maybe to echo a little bit what Dan said, knowing that the ADRD summit is planned for March, and in the Lewy body dementia realm, I think the latest version of the recommendations were very, very good. But already this morning, there's gaps that weren't specifically or even indirectly stated in those recommendations. So hopefully in the next couple of days, it will guide updated recommendations for going forward.
I want to thank the panel for excellent discussions and a great presentation. And I think it's lunchtime, correct? Lunch for everybody. Okay.
Okay, we're going to get started with the data blitz, and our first speaker is Lenora Higginbotham from Emory University.
All right. Hi, everyone. I'm happy to be presenting today on behalf of our team at Emory on network proteomic signatures that we've analyzed in the LBD brain. All right, I think we can all agree that we've only begun to scratch the surface on, understanding the complex cortical limbic pathophysiology that contributes to LBD. And that at the end of the day, it's going to probably be multi-analyte or multiplex biomarkers that capture this kind of diverse range of cortical limbic pathophysiology that really moves the needle diagnostically and therapeutically. So for the past decade or so, our group at Emory has been applying a strategy of proteomic co-expression network analysis to 80 brain tissues. And what we've seen is that it's a highly reproducible way of just developing a systems-based map of neurodegenerative alterations in the brain. And so the idea behind this project was to apply it to Lewy body tissues. So for those of you who aren't familiar with network proteomics, data-driven approach in which complex proteomic data sets are organized into groups or modules of proteins with similar expression patterns across individual cases. And even though these modules are data-driven, they often are very biologically relevant in a reproducible way, mapped to specific cell types, molecular functions, organelles. And so it's nice is that you can take these different disease networks and you can actually compare them at the network level, looking for changes at the module level between different diseases. And this is, kind of a representation of a large consensus network that we published a few years ago in Alzheimer's disease, and kind of what it looks like with the modules on the outside, and then correlated to different disease traits and their cell type enrichment also assessed. And so again, just clear stating the objectives for this project, we wanted to really develop a large-scale Lewy body co-expression network in brain tissue, look at the overlap and divergence of some of the changes we see in that brain tissue compared to disease. And then all of this is to potentially identify really diverse pathophysiological markers that we can take into the plasma and CSF, which I'm not going to talk about today, but Nick Seifert will talk about later. And so the results that I'm going to present in brain tissues were actually recently published in Molecular Neurodegeneration, which was pretty exciting. And at the base of this whole paper was a discovery data set that was derived from collaborators at the University of Pennsylvania. And you can see the numbers there included 47 controls, 33 Parkinson's disease, 47 PDD, 11 DLB. So altogether almost 60 dementia with Lewy body cases. We performed tandem mass tag mass spectrometry on this group, identified close to 10,000 proteins, did differential expression, of course, built the co-expression network, and then actually compared that co-expression network to a couple of networks that were derived from 80 brain tissues. And this is the UPenn network that we generated here. Just to walk you through this briefly, these are the modules up here. They're all designated by particular number and color. And then as you can see, we're able to then correlate using the quantitative data, those module expression patterns to different disease traits or pathology, I should say, and then analyze their cell type enrichment and finally their ontological associations. And as you can see, there's actually by the coloring in this heat map, it's a lot of significant alterations across the LB brain network, which is nice. A lot of it overlaps with Alzheimer's disease, but I'm really gonna just highlight one story here that immediately jumped out to us where it might actually diverge from what we've seen in Alzheimer's cases. So we noticed that there are a group of modules in here, in this square, that were neuronal in nature and were actually elevated across the Lewy body dementias and also PD, actually. And what's interesting is about that is when we look at the Alzheimer's disease brain network, usually all these neuronal modules, particularly with these synaptic ontologies, are all just generally decreased across the board. So it's interesting to see these increases. And there are a couple in here like M17, M19, M26 that actually seemed correlated more so to synuclein burden here as opposed to like amyloid and tau burden here. So you can see they're almost selectively correlated to synuclein, whereas the majority of disease-related modules are just really blazing hot for all three pathologies. So that group really jumped out at us. And so when we actually delved in a little bit more and compared it to Alzheimer's disease networks, including one also derived from the University of Pennsylvania brain tissues, but then that other large AD consensus network I showed at the beginning, and we overlapped the two, looked at these same presynaptic modules. They all had largely presynaptic gene ontologies. And those groups of proteins in the AD network, we saw divergent changes. So I guess the most striking are the ones where in M19, M26, you can see that they're actually going up in the LB tissues, but going significantly down across the AD co-expression networks. Similar appear at M17. This one actually was not changing in the LB tissues and then going significantly down in Alzheimer's. And then I already said that these modules correlated well to synuclein pathology, but synuclein itself was actually measured and assigned to the M19 module, so one of these synaptic modules of interest. And this is pulling out synuclein, alpha-synuclein, and other proteins from those modules of interest. So you can see in a heat map form, they're going up in the Lewy body diseases, but then going starkly down in Alzheimer's disease. We looked a little bit harder at alpha-synuclein itself and its place in the network. So we noticed it wasn't a hub of its particular module, so it didn't have necessarily the most number of spokes to all the other interactors in that module. But when we looked a little bit more at its correlations, we saw it was moderately high correlations to all 4 of these kind of presynaptic modules of interest. And so we looked at another measure instead of hub status in the network. We looked at something called protein centrality, which looks for bottlenecks in the network, which are proteins that communicate between modules. And we saw that synuclein was one of the strongest bottlenecks within these 4 modules for the 4 modules itself. So it really communicates information between modules, solidifying its importance in the network. And then we did do some validation in 2 separate cohorts, including Ross map and an Emory cohort. I pulled out the Ross map tissues because these were a little bit unique in the sense that we had a corticolimbic Lewy body deposition with dementia, which we termed LBD, but we also had a group with corticolimbic or mostly cortical Lewy body deposition, but no clinical symptoms at death. So we had an ASIM LB group, and that particular group, we could see that some of these modules that of interest, these presynaptic modules were changing, but looked to be early in that cohort. So in general, LBD features a variety of proteomic alterations in the frontal cortex across diverse cell types and biological functions. Have this group of synuclein-associated presynaptic proteins that seem to diverge in their alterations from LBD to AD, increasing in LBD, but decreasing in Alzheimer's. We've validated these changes in 2 separate cohorts, but there's also ongoing validation across regions, which is an interesting question for us. And the preclinical stuff that I showed you also needs to be validated. And then, of course, future directions are really, we're just trying to map out the brain and then ideally examine the overlap in the CSF and plasma to develop panels that are actually pathophysiologically diverse. And I'd just like to thank our group at Emory, Alan, Nick, who's here, our collaborators at UPenn, and of course, NIH for funding. Thank you.
Excellent. Thank you so much. Our next speaker is Stephanie Sandoval Pistorius from the University of California, San Francisco.
My name's right. Oh, there we go. Okay. Hi, everyone. I'm going to keep you on your toes and change gears a little bit. I'm going to focus more on like systems level work. I'm a postdoctoral scholar working with Dr. Philip Starr at the University of California, San Francisco. And my project is mostly focusing on creating a less invasive tool for recording cortical activity to be used during deep brain stimulation for Parkinson's disease. So today I focus a lot on Parkinson's disease as a proteinopathy, or in this case, Lewy body dementia. And during my doctoral work, I did study protein quality control in clearance of alpha-synuclein. And I spent a lot of time thinking about what happens to neuronal activity in these cells that start to accumulate alpha-synuclein. Not only how does that lead to downstream dysfunction because of dopamine cell loss, but even early what's going on with cell activity. So we can think of single unit activity, changes in firing rate, maybe suppression or more bursting activity is something that people are seeing in Parkinson's disease specifically, that then leads to how we think of Parkinson's disease in terms of an oscillopathy. So a disorder that has hypersynchronization of neuronal activity, leading to a lot of activity in like beta and gamma frequency ranges. And we study that a lot in Parkinson's with deep brain stimulation in the subthalamic nucleus and the pallidum. And that then leads to Parkinson's disease, the network disorder. So thinking of macro scale dysfunction in the brain that then kind of contributes to our understanding of this classic model of Parkinson's disease and basal ganglion cortical dysfunction in the disorder. So deep brain stimulation is a surgical treatment for Parkinson's disease that kind of targets the oscillopathy and network dysfunction components of PD. It essentially, patients will get a lead implanted in Parkinson's disease, either the STN or the pallidum, that is connected to a battery that's implanted into the chest that also serves as a pulse generator. There are multiple approved indications for Parkinson's disease, and they each have their own target site. Parkinson's disease, for deep brain stimulation. Parkinson's disease is one of the main indications for DBS, the targets being at the STN and the pallidum, but there are a lot of other indications that are under investigation, namely Alzheimer's disease, where the nucleus basalis of Maynard is the target region. There have been a few clinical trials looking at DBS for Lewy body dementia with mixed results. So really there's just a lot more that we need to know about the potential benefits of that for individuals with Lewy body dementia. DBS is super specific. Its outcomes depend on great patient selection, target, like lead placement, having really good lead placement, and then the clinicians and their ability to get really good stimulation parameters set for patients after clinic. So there's just so much that goes into it, which is why 2 clinical trials might not be enough to really understand if this can be helpful for individuals with LBD. DBS has enabled a better understanding of the physiology in Parkinson's disease, not only from the placement of the leads early on in DBS's history, but also with new research devices that are bidirectional. So they can sense brain activity as well as provide therapeutic stimulation. And lots of people are starting to use subdural ECOG paddles to do multi-site recording, so they can record from the cortex and target sites. So this has led us to understand network dysfunction in Parkinson's disease and other indications for DBS, but it's also led to the advancement of applications for DBS, such as adaptive DBS, where a patient's own brain activity can be used as a feedback signal to automatically adjust stimulation parameters when they need it. So they're getting as much stimulation as they need when they need it the most, or decreasing it when it's no longer necessary. So this is kind of an example of what that might look like. This is a neural signal that's used as a feedback signal at the top, where as we see in this individual, as signal went up, it was better for them for DBS to stay low. But as their signal dropped, then we wanted to increase stimulation. So this just kind of happens automatically with patients who benefit and are trying adaptive DBS. But future implementations of adaptive DBS, the goal is to make it simpler, scalable, and inclusive. So historically, if we want to use a cortical signal for the feedback signal, we'll use a subdural ECOG strip, but that is...
Hi, it's Dr. Gompers from Mass General Hospital calling. I'm sorry I've missed you.
Okay, guys. So that's really invasive. There's a lot of exclusion criteria involved in that, and it's pretty risky. So for our work, what we want to do is use a less invasive subgaleal lead that's placed in between the scalp and the skull. So the goal of this is, one, because of it's less invasive, there's less risk, easier to remove if patients don't want it or for whatever reason anymore, and will hopefully lead to more inclusive study cohorts and criteria involved with a subgaleally placed lead versus subdural. And also now that we have commercially available devices that are bidirectional. In the past, they were only research devices. So like at UCSF, we had 20, right? So now with a commercially available device, there's thousands and thousands of people across the country being implanted with devices that could be compatible for adaptive DBS. And so the question though is, can we actually use subgaleal leads to record good cortical oscillatory activity that we can then hopefully use for adaptive DBS? So the first thing we looked for is this canonical cortical beta desynchronization. So when individuals do an arm movement, in this case, they were doing like hand movements, then oscillatory activity in the cortex decreases in the beta range. So you can see that here, these are EMG data that when we see the spike here correlates with muscle contraction, we can see a decrease, more blue in the beta range in the STN and also in the cortex, which is better represented in this plot here with power spectral density. We see decreased power in the beta range from 13 to 30 Hertz during movement compared with when they're just holding their arm out. So that was really promising. It's like we can actually see good signals from above the skull. The next thing that our lab was really interested in looking at was this really specific DBS entrained finely tuned gamma activity. Our lab has earlier this year, we published that this specific brain activity is correlated with dyskinesia. You can see that in yellow, as dyskinesia goes up, so does the signal from this specific brain activity. It just follows really nicely with dyskinesia. And then this is also in a recent publication, our lab has shown that this specific brain activity is really helpful as a feedback signal for adaptive DBS. And so we wanted to see if we can detect the signal. It's in the gamma frequency range, so it's higher, at a higher frequency that normally EEG doesn't pick up high frequency ranges. And since our leads are essentially kind of an EEG signal, we wanted to see if we could detect that. And so we wanted to induce it. Lots of times these patients develop this signal the longer they're on DBS. And so we essentially induced it by incrementally increasing stimulation in an individual in clinic. And we can see as we increase stimulation amplitude, we can see the development of this finely tuned gamma activity. So that was really exciting for us to see that because it means that we can hopefully use these leads to apply adaptive DBS to these individuals. And these new commercial devices are able to do really cool things. Patients can record brain activity at home. So they can set up to 4 symptoms or states that they're interested in tracking. And then they can just do short 30 to 60 second brain recordings at home when they're experiencing that symptom. So in this case, we see an off medication series of recordings and then dyskinesia. So we can record some physiologically relevant activity here. And this is just really great for getting lots of data for specific symptoms and hopefully using this data to identify physiomarkers that then could be used as feedback signals for adaptive DBS. And then also we can use a really cool function that allows the devices to continuously track a 5 Hertz frequency band. So in this case, we're tracking this finely tuned gamma activity. And we can see that we can detect a circadian rhythm where this activity decreases during their nighttime sleep hours and then increases actually like as they're waking up throughout the day. So this will then enable us to apply a sleep aware adaptive DBS that will allow us, because a lot of patients actually decrease their stimulation at night to help with sleep. And so now this can maybe automatically do it for them. So main takeaways is that we can use these less invasive subgaleal leads to sense cortical brain activity that then can be used potentially for adaptive DBS. And especially want to point that we can detect that finely tuned gamma activity, which we've shown to be a promising feedback signal for ADBS. So the next thing is just to try to implement adaptive DBS in these individuals. And so good timing here. I just wanted to thank my labs. I work with Dr. Philip Starr, but very closely with Dr. Simon Little. So this is our group, our massive group up here. And then I have 2 really incredible undergrads that helped me with this project. And I want to thank my funding sources. Thank you.
Thank you very much. Our next speaker is Bernard Fonggang. From UT Health San Antonio.
As soon as we have the slide. Thank you for the invitation. My name is Bernard Fongain from University of Texas Health Science Center in San Antonio. And I'm going to talk to you a little bit about the microbiome and dementia and what is known about microbiome and dementia in Lewy body. And I have nothing to disclose. And I will basically have 3 stops. And the first one is to talk about the gut-brain axis. And then the second one is to look at the gut microbiome in dementia with Lewy body. And then I have a conclusion, which is what are the current limitations of what we currently have. So it's well known that dementia has several risk factors, right? And the gut microbiome is not recognized as a risk factor for all-cause dementia, including DBL. So this is just a state where you have imbalance in your microbiome. You have more microbes than other, or the distribution of this microbe is not even. So when you have this imbalance, then it's linked to several diseases like type 2 diabetes, obesity, cancer, autism, dementia. In that specific case, there is a concept that is well applied and known in the field, which is the gut-brain axis. So what is the gut-brain axis? It's just a bidirectional communication network linking the central nervous system with the enteric nervous system and the gastrointestinal tract. So basically what you have is no pointer, but you have several pathways, in fact, that link. You have several pathways that link. Okay, I might not want to use this. You have several pathways that will link the gut to the brain. And then some of these are listed here, the neural pathway. You have the immune system pathway, the endocrine pathway, and then we also have the metabolic pathway in this. So understanding the gut-brain axis role in dementia will open up potential therapeutic strategies such as dietary intervention, probiotics, and prebiotics that will aim at restoring a healthy gut microbiome to support brain health. So what it means is if you have imbalance that leads to disease, how can we do to balance the gut microbiome to come back to a normal state, to healthy state? So there have been a lot of studies linking the gut microbiome and all dementia type, and but also a very recent symposium to try to now move forward to how we can use this for prevention and treatment of ADRD. So and when you come up and key finding here, and this is not exhaustive, a lot of other things, is that the microbiome composition is different, right? If you look at people with Alzheimer's disease, or people with let's say Parkinson's disease, without Parkinson's disease, I cite both because they are the most studied in the field, then you will see that the composition of the gut microbiome, in fact, changes, right? You have some of these bacteria are repeatedly known to be lower in people with Alzheimer's disease. Some are known to be increased in Alzheimer's disease. But there is also a study showing that if you transplant a gut microbiota from Alzheimer's disease patient to a healthy animal, then the animal will develop Alzheimer's disease-like symptoms. So those are the fact that we need to know and probably explore for therapeutic targeted if they are validated. But they also the impact on brain inflammation, right? The gut microbiome will influence brain inflammation, which is a key factor for Alzheimer's disease. And imbalance in gut bacteria can lead to increased production of inflammatory molecules that contribute to neuronal damage and cognitive decline. So all these knowledge, in fact, are very interesting. I just showed a symposium that highlight how we can use this for dementia prevention and treatment. But what we really know, and this is for Alzheimer's disease. You saw that this morning for Lewy bodies, for dementia with Lewy bodies, dementia symptom will appear a decade before clinical diagnosis. So there is really a window of opportunity somewhere there where if you target and have those interventional therapy or microbiota, then you have a window of opportunity where you can help with disease management and disease treatment, in fact. So what we really do in our group is besides doing those case control dementia with no dementia, but we're also looking at dementia at midlife. So the goal is to, and when we do oral microbiome, gut microbiome, the goal is really to understand, identify gut microbiota features that are associated with change in ADRD marker at preclinical stage of the disease. So we know that we have several neuroimaging, neuropsychological tests, neurocognitive, that can give the state of the disease. So we want to understand how will the gut microbiome composition correlate with all this? Are they the same, and how would that change? So one of the very first paper that we got here is using Framingham Heart Study data. This is 1,400 people with brain MRI, PET, cognitive assessment, CSF, plasma biomarkers. So the goal here was to assess how the gut microbiome feature, when I talk about feature, just explain that it's a gut abundance, diversity, function, how these associate with dementia markers. And we found that if you look at, here, this is the data showing with some MRI markers. If you look at the MRI marker, then you will see that every time that you have an increase in burden of each dementia marker, you have one specific bacteria that is reduced, right? The reduced abundance in that bacteria is Bacillus intestimoni, and that bacteria is neuroprotective. It's known to have a neuroprotective effect. And now, if you move forward, you see that most research here have been involved in, have mostly been focused on Alzheimer's disease. Most research in this field has been focused on Alzheimer's disease. As you can look at this picture, this is relative distribution of a published study looking at the gut microbiome and dementia, gut microbiome dementia. Most study, of course, is Alzheimer's disease, but dementia with Lewy body is less study here. So, but something is common between all these studies. It's like a decrease in shortened, we found a decrease in shortened fatty acid production bacteria, which is repeatedly seen in all type of dementia, Alzheimer's disease, but also Parkinson's disease. So what we really know about dementia with Lewy body disease and the gut microbiome is data that we collect that come from Alzheimer's disease and data that also come from Parkinson's disease, which of course, as you know, is the concept of the gut-brain axis, where we have an increase of specific gut bacteria that will degrade the intestinal mucus layer and increase permeability that can allow toxic substance like FPS to pass through the mucosal barrier, which trigger neuroinflammation. And then you have accumulation of alpha-synuclein in this area. The second one is that the reduction of short-chain fatty acid producing bacteria with tying in the mucosal barrier and accelerate the vagal nerve pathway. This is the second one. And the third one is mostly that the fact that the lack of short-chain fatty acid will aggravate microglia activation, likely through the reducing the GLP-1, but the detailed mechanism of this is not known. So one key result here is, and this is coming from a group in Japan, is that dementia in Lewy body patients have an increased abundance of Rhamnococcus torus and Cholinicea, and a decreased abundance of bifidobacteria. And this was seen in different ways between PD patient and dementia with Lewy body. Those changes were not observed in dementia in Parkinson's disease patient. So what they thought was that we can use this result to distinguish DLB and Parkinson's disease if validated. So, and then, so I will skip this is a summary. You just talk about there are a lot of microbial changes associated with dementia and Lewy body. So what I'm going to talk about to finish is the challenge, the different challenges. As we saw in the limited DLB study on microbiome, right? So most research focus on Alzheimer's disease and Parkinson, and mostly they are a small sample size and a limited cross-cohort replication. So the second challenge here is complex microbial composition and diversity measure. Diversity and across studies. And the most important one is to establish causation and correlation. So we need more microbiome longitudinal changes to establish the causation of this association. Thank you for me.
Thank you very much. Our next speaker is Eja Bayram from the University of Colorado.
All right. Well, hello, everyone. Thank you for having me here. I'm very anxious / excited. So I'm going to talk about sex. Let's get started. So first, want to start off with some disclosures. I don't have fancy disclosures, but I do have amazing funding from the NIA and Lewy Body Dementia Association that helped me do this research. And you know, we do this research thanks to all the research participants. So big shout out for them and also my collabo friends. Once we go through a paper grant phase together, I consider you a friend because we went through torture and also celebration together. I think that's the core of friendship. And my family, my partner's family, they're not scientists, yet they read my grant applications, my papers, my surveys that I put together. My partner always goes through my slides. So shout out to them too for just sticking through it all. All right, so my introduction is just going to be about sex and gender, because thankfully everyone covered the background I could have given today as is. I'm not going to dive into the specifics of Lewy body dementia, but I have to talk about sex and gender before I start talking about my results. So these are two separate terms. I know traditionally they get misused and they get used as if they're the same thing, but they define two different things. So please be mindful of that. Sex is the biological variable that relates to the anatomy, physiology, genetics, hormones. We usually go by female, male categories, but it's not limited to that. So, you know, we focus on the majority, but there's a minority of different sex groups as well that we're leaving behind. Gender is the social and cultural variable that can vary over time, vary across cultures. It's not just two categories of men and women. It's way beyond that. It has to do with identity, roles and norms, relations, power. So for this talk, I'm gonna focus on sex, but you know, you can't really separate sex and gender in life because we're not fully biological or we're not fully environmental. These things are interacting with one another. So as we're going through, you know, it may give you some ideas about, oh, what if this is a gender effect, not sex? That may be the case. So be mindful of that. And if you're ready, I'm gonna dive in. Fun facts. Ece, my name in Turkish means queen. So there you go. All right, so it's pretty cool. I get to talk about my research a little bit. So sex differences that we have identified so far. In terms of the clinical profile, there's that, you know, commonly known finding that females have a lower prevalence when it comes to Lewy body dementia, but it's not just limited to that. We also know for females, there's a higher likelihood for misdiagnosis. They usually get diagnosed with Alzheimer's instead, and also delayed diagnosis, which was mentioned during the panel discussion earlier this morning. So females have a longer diagnostic process that's waiting for them, unfortunately. And if you look at the specific core features, we see that compared to males, females have a lower likelihood of REM sleep behavior disorder and Parkinsonism, which means two of the core features out of the four core features are not happening as often for females. And thus the miss or delayed diagnosis, probably they're not showing you the phenotype you expect from them. And if you look into the pathology, we see that Alzheimer's likes coming into play more for females. Females have a higher likelihood for having that Alzheimer's co-pathology compared to the males. And once they have that Alzheimer's co-pathology, it's usually more severe when they get to the dementia phase compared to the males. And thinking about Lewy body and nigral loss that also impacts the phenotype in Lewy body dementia, we actually see nigral loss not as common for females either. Until they reach that neocortical Lewy body pathology stage, females seem to be, doing fine with not having too much nigral loss, which probably has to do with that Parkinsonism being lower likelihood for females that we see. And let's tie these together. So you have the clinical differences, pathological differences. What about the clinic and pathology correlations? Well, they differ as well. So if you look at our main guy, Lewy body pathology, if you take a female and a male with the same level of Lewy body pathology, females compared to the males are going to be less likely to have dementia and that Lewy body dementia phenotype, despite having that pathology similar to the males. If you bring Alzheimer's pathology, sorry, forgot to show you my graph. So as you can see, if you look at all of the core features, these are all the people that have a high likelihood for that Lewy body dementia phenotype. So you expect to see all the core features in these people. And if you look at females, 50% of them, we're missing them because they don't show the core features we expect from them, and we call them Alzheimer's instead. So let's bring Alzheimer's pathology into the play since, we see the co-pathology pretty often. And if you bring that Alzheimer's co-pathology into the play, for females, it causes dementia way more than males. It's just like taking the center stage and torturing females' cognitive skills. But when you look at the core features for Lewy body dementia, it lowers the likelihood of those core features more for males because females didn't have the core features as much to begin with. So Alzheimer's co-pathology coming into play doesn't really make it too much worse for them. They don't show the core features as is. And the final one, the nigral loss, similarly, we see the sex difference there too. It's not as likely to be associated with Parkinsonism. You take females and males with similar levels of nigral loss, females are not going to show you that Parkinsonism as much as the males do. So consequentially, they're not showing you that Lewy body dementia phenotype as much as the males do. These are my grandparents. I wanted them to be included in my talk. So, all right, we know differences between clinical profile. Pathology seems to be different. The correlations between clinic and pathology seems to be different. Let's move to the risk factors a little bit. Well, if you think about risk factors, Lewy body dementia probably has to do with genetics, environment, and interplay of those. We're only scratching the surface so far with the risk factors for Lewy body dementia. Dr. Schultz is going to talk about the genetics more detailed later on, but we have found those risk factors to be different for females and males so far too. We did the X chromosome-wide association study and we identified a new risk locus just for females. It didn't show up as significant in female and male together cohort. It just showed up in the female stratified cohort. And there was a meta-analysis published a couple of years before, and they showed that ApoE seems to be associated with risk, both for females and males, but GBA, CNCA seems to be associated with the risk more so for males. It differed. It wasn't as significant for females. And in Parkinson's, our typical knowledge is that dementia risk is lower for females. Well, we kind of looked into that, taking into the gender effects consideration too. And we saw that, sure, females have that biological advantage compared to the males, but once you bombard them with the gender disparities, like lower years of education, higher levels of discrimination, their risk actually becomes similar to the males. So we can alter and make the risk better or worse based on the disparities we're putting them through. And it actually puts the sexual and gender minoritized groups at risk too, even though male sex is associated with, higher risk. If you bring sexual and gender minoritized groups into the play, sexual and gender minoritized group males have higher risk for dementia compared to the cisgender straight males. So keep that in mind, and that discrimination is the perceived healthcare discrimination. So while they're receiving healthcare, not the discrimination they go through their daily lives. So this is the discrimination that we may be putting people through. And the impact on daily life, we don't know much. I will assume there are sex differences and gender differences there. And something to consider is majority of the caregivers are women. I mean, majority of the panel we had today, the caregivers were women. So it means the disease, even if it's not hitting the women as much, it's going to impact them through the caregiving process regardless. And accordingly, you know, we don't get females represented in research, which bleeds into the clinical trials that we're doing, and we're not seeing a good representation to test out the interventions we have. So we're not really getting results that are as helpful for them probably. We have so much more coming out. You know, we're also looking into the prodromal symptoms, the progression rates, and I wanted to mention the survey study because we just collected data and the data is available. If anyone's interested, I'm going to start doing the analysis, but all this work is done with collaboration. So I hope you'll consider continuing to be welcoming to the field and, you know, elevating the early career researchers like me, everyone else on the panel, and lift one another up so we can push the field further. Thank you.
Thank you so much. And our last but not least talk is from Georgina Aldridge from the University of Iowa.
I'll introduce myself while they're getting the slides up. All right. Hi, I'm Georgina. I'm a cognitive neurologist, and that means I see patients. I actually run the Lewy body dementia multidisciplinary clinic at Iowa. So a lot of people talking about getting physical therapy, occupational therapy, geriatric psychiatry, and pharmacy all on board. That's one of the things I run at Iowa. But I'm also a mouse researcher, work on translational models, and I really want to figure out how we can treat symptoms now, not just for the future. So in my patients that I see every day. So to me, dementia is not only cognitive symptoms that are severe enough to impact daily life, but also psychiatric symptoms. And all these symptoms you see up here actually fluctuate. And we've heard about this today. And this is something that entices me so much because when my patients fluctuate, I think about how I could get them back to their peak, right? We have that opportunity. This symptom's fluctuating up and it's fluctuating down. But the difference between these symptoms and the motor symptoms is we know so much less about the circuits that are involved. And so there are some main hypotheses out there about what differs from a patient with Parkinson's disease that doesn't have a dementia compared to one of my Lewy body patients or one of the Parkinson's dementia patients that do. One of these hypotheses is a direct result of alpha-synuclein. So is synuclein outside of the brainstem? Is it impacting some new brain region that's causing that dysfunction? So that would be number one. A second hypothesis is that the loss of circuits is just so much worse in these patients. They're losing more acetylcholine, more norepinephrine, more of all these different neurotransmitters. So that would be an indirect type of hypothesis. And then thirdly, the co-pathology that we've heard a lot about today. Is amyloid, tau, TDP43, all these different pathologies, are they impacting that transition into dementia? So I'm going to tell you briefly about what my lab is doing on the first, and then I'm going to just hint at what we're doing on the second and third, because obviously I am ambitious and want to attack all three hypotheses. So just starting with the direct alpha-synuclein. Traditionally, in Parkinson's disease, if a patient goes to autopsy without dementia, they tend to have more synuclein in the brainstem areas. And the patients that develop dementia tend to have this diffuse alpha-synuclein in all these different other locations. And so my question, because I was very interested in the cortex, is what is alpha-synuclein doing to cortical cells at that direct level when we're not looking about dopamine loss or acetylcholine loss? The way my lab handles this is trying to overexpress or induce pathology in a very specific brain region. So up here you see on the left, in green is overexpression of synuclein in a mouse model located in the cortex. On the left, it's using a viral overexpression model of just traditional normal human alpha-synuclein. On the right, we're using preformed fibrils, which is a little harder to keep in one location, but we at least can start them in the cortex and get more pathology up there. And then our lab uses multiple different methods to try to look at outcomes in mouse models that we can't do in humans. So for example, structural connectivity. Here you see a prism in a mouse looking at individual neurons, dendrites, and we can even look at synapses, and that mouse is alive, awake, and behaving. And we're able to actually track those neurons over time to see what happens, what changes when we put synuclein in that area. Nope, we're not going to get that one, but you can imagine neurons, individual neurons firing. We can actually track them during behaviors. And then we also, he's going to press the play. There we go. This is a Mac transition problem. There we go. Neurons firing while we're doing cognitive tasks with these mice, trying to tell whether neurons are hyperexcitable in the presence of alpha-synuclein, or whether they start to die. Even we can track over time. And we do our cognitive tasks in mice while we're actually able to image, something you wouldn't be able to do at this level in humans. And so I'm just going to give you one taste of a very tiny aspect of those things I was talking about. So looking at what overexpression of the wild type human alpha-synuclein does to dendritic spines, which are the connections or the synapses between, or the postsynaptic side of a synapse. And after painstakingly counting these over multiple years, we found that overexpression of synuclein actually increased the dendritic spines in the cortical areas when we saw this. And this was just in the first 2 months. So this might change if we looked longer, and we're doing that, or if we use the preformed fibrils, or if we used a different mutant form of synuclein. But my finding did make me really, really want to know what was happening in the patients, so that the next 5 years I spent trying to count individual dendritic spines, I had a good thing to compare it to. Because the data that inspired all this is actually pretty few and far between. There's very small samples of patients where we had looked at, where the field had looked at dendritic spines and showed that there was almost no spines on the frontal cortex on some Lewy body patients. But it was a handful of patients, and co-pathologies weren't discussed. And so I said, well, we got to go back to patients. And luckily I'm a cognitive neurologist, and so I could, and I have collaborations with neuropathologists, and that's what jumped me into getting into the neuropathology field. So this is very preliminary, but basically we started doing Golgi analysis on patients that were coming to autopsy. We can't go retrospectively. This has to be on fresh tissue. And this is some of our first 7 patients that we finished completing counting dendritic spines using Golgi Cox, which is a fancy method for looking at individual dendrites and neurons and spines. And as you can see in the middle, here on the right, these are some trace neurons. In the middle is a control patient that died without dementia. And then 2 other patients that had different amounts of synuclein, lower or more synuclein in the cingulate cortex, like right in locally, ignoring the whole rest of the brain, but just locally around those cells. And way too early to draw any conclusions from this, but the main thing that I want to highlight is that most of my patients had dendritic spines. They weren't absent. So this is something we definitely need to look into carefully with larger studies, that at least in the cingulate cortex, the spine density on the remaining neurons is fairly well preserved. You'll also notice we're quantifying all 4 of the top 4 pathologies within that cingulate area to show how much amyloid, how much tau, how much TDP-43 are in these locations. And that also doesn't seem to have a really huge effect, at least on this layer 2-3. But well too early to actually draw conclusions from this. I more put this up here to highlight our lab's main and overall strategy, which is that as a mouse lab, I constantly want to bring this back to human patients. So and we've become even more ambitious with this. And I'm at Iowa, so the really fun thing about being at a new kind of center that's growing in the dementia field is that I get to design the stuff myself. And so, for example, we have started a registry that's very kind of what I want to call hyper-inclusive. We accept patients beyond what meets Lewy body criteria, people who only have one core feature or just Alzheimer's patients. And the goal there is to get people to join our registry who may not fit the criteria we know now. So for example, getting the women involved, even though they may not have Parkinson's, they may not have, meet criteria, so that our pathological diagnoses are much more broad. We also want objective data. So we're starting to have those registry patients wearing Fitbits, recording their cognitive fluctuations, working out cognitive skills that our patients in moderate to late stages can actually do. Because sometimes when they're getting towards the severe end of the disease, you know, they can't do the types of things that that they would have been able to early on. And then we're working to build a brain bank at Iowa. And again, a hyper-inclusive brain bank, so across the board. And then of course, because it's my lab, we want to then, from the patients, it's kind of everything, everywhere, all at once. But in the mouse, we can go back and reintroduce just one circuit at a time. And so just to touch on, like I said, hint at some of those other things we're doing. This would be looking at the locus coeruleus, one of the brainstem regions that produces norepinephrine, in a patient that died without any dementia. And then on the right, one of my patients who passed away, who had very severe fluctuations along with a lot of traditional Lewy body symptoms. And as you notice, or hopefully can notice, those green cells that produce norepinephrine are few and far between. They're swollen. The blue there are the Lewy bodies that are in, you know, each of those cells. And then the red is actually tau. So this indicates both the co-pathology aspect of it and also just that loss of neurons in this region. And we are able then, you know, to go back and introduce alpha-synuclein or one of the co-pathologies into the mouse model. And it looks, you know, it's different. Mice are different. I have I know as one of the mouse researchers here, I know that it's a very different thing. But we have that benefit of being able to isolate an individual brain region or circuit that we can't do in the human patients and try to ask. And the good thing is mice do sleep and they do get sleepy and they have a lot of the same symptoms we do, you know. All right, and so with that, just thanking my lab, all of my mouse research is funded by NINDS, and all the human research right now is funded by internal awards and philanthropy, and we're looking to fund more so that we can keep growing in Iowa.
Okay, let's give another round of applause for our early career investigator data blitz. Thank you all so much.
Have everybody in the neuropathology section come up in their order. Melissa, I think you're up first. All yours.
Hello, everyone. Thank you very much for that data blitz. And I'm glad we're all gathered together today. I took a little bit of a different approach with this challenge. I wanted to look out into the landscape of the field and even disease adjacent to dementia with Lewy bodies to kind of give us some exciting future possibilities and to hopefully inspire individuals looking to really focus in on drilling in on one aspect of the disease. These are my disclosures, and I'm very grateful for my funding to allow me to be here today. Much of the work I'm going to present today is not from my laboratory, but from really inspiring groups that I had the pleasure of really drilling into the literature, if you will. And I'd like to talk a little bit about neuropathology and histology, and I'm going to little by little introduce you to some of the techniques without hopefully losing anyone. So we're going to talk about multiplex fluorescence with some of the more advanced pteramide signal amplification assays that we have going on, what this looks like for proximity ligation assays, and then how machine learning might be able to benefit a lot of us in what we're trying to do with some of these deep dives. So traditionally, we've looked at hematoxylin and eosin, silver stains, we have had immunohistochemistry.
and more recently immunofluorescence, which gives us a chance to really label what we're interested in. You can do this directly or indirectly, so you can look specifically at different aspects of a protein you're interested in. But for the longest time, we've really utilized one type of synuclein antibody that might be giving us a narrow window. LB509 and ACP, these are C-terminal parts. And so I'm not going to go into too much detail on the protein side. That's for the proteomic specialists to do. But what I just want to highlight is there are many different types of alpha-synuclein antibodies that might give you different answers to the questions that you're asking. One of the ones that came out was phosphosynuclein 129 that was heralded as this more disease-specific form. And so I just want to really try to encourage individuals looking at a big picture view, and where this might really be coming a part of biomarker studies is when we start to think about plasma assays, and of course with our radioligands. And so not to drill in, but a paper did take the leap to do and perform some multiplex immunofluorescence. And what this really allows us to do is actually to save precious brain tissue. So you can do serial sections right next to each other, having similar stains, and then compare across to kind of gain a sense of the differences. However, this might prevent you from really seeing as much when they're co-localized. There's all kinds of caveats we can go into later if anybody's interested in. But what I want to highlight is the multiplex immunofluorescence, what allowed them to do is to look at the N-terminal, so the beginning portion of synuclein. They're able to look at this more disease-specific form as well as the C-terminus. And I think this comes into play because when we've learned about Lewy body pathology, very specifically, there's a lot happening in this inclusion. And so when we can understand distribution differences, it might actually reveal some targeted aspects that might be quite particular in where we see the pathology. So we've talked about Parkinson's disease, we've talked about dementia with Lewy bodies, which is of course why we're here. And there's different components or where the brain pathology can actually reveal itself. And this study particularly really highlighted that the N-terminal aspects of alpha-synuclein, which is fairly understudied, does vary quite a bit across the brain tissue. One of the newer aspects that we're working on in the lab that others have already had a really good handle on is where you can do 20 different markers if you wanted. I think some people are still in the 6 to 9 range, but you can basically have your slide, add your solution, and then sort of from a heat treatment, you can then knock off what's on the slide. Why is this exciting? Because once again, every brain tissue is important and every piece of brain is precious, especially since most individuals very much like looking at the substantia nigra or the amygdala. We have the opportunity to then look at all of these layered on top of each other. And so you just go through this process that iteratively allows for you to examine. And these individuals noted differences in Parkinson's disease as well as in dementia with Lewy body brains, but then also found differences in some of the genetic forms and what this could tell us hopefully about the biology. We're always looking for differences and similarities to help us gain a little bit more insight. One of the other methods that I wasn't as familiar with until we had Dr. Sekia join Dr. Dennis Dixon's lab was this proximity ligation assay. So I'd seen this work in Dr. McLean's group, but I hadn't seen the work where he was specifically utilizing this to look at oligomeric forms. So we focus a lot on alpha-synuclein. This is the deposition of the proteins, but there could be earlier forms that might actually be even more toxic. I think there's still a lot of information out there that people are deciding upon. But the goal of this technology is to allow you to be able to see what is of interest when it's in close proximity, as the name belies. And so in the study that focused on MSA as well as Parkinson's disease, so this is what I'll continue to do. Some of the studies didn't have the opportunity to study dementia with Lewy bodies. So if you see sort of a vacancy, it's just kind of a highlight sign of where I think some of the field needs to be headed. But what I'm demonstrating here is this beautiful staining patterns in an MSA brain and an individual who was clinically diagnosed with Parkinson's disease. But what they found are differences in where this might be affected and could help us to understand some of this selective vulnerability. I won't show you too many data slides, but I still thought it was quite important to really highlight the differences amongst individuals that are affected by alpha-synuclein. A lot of the seeding assays are teaching us how aggressive the synuclein pathology is in MSA.
But I think these oligomer burden assays are also demonstrating the robustness that we're seeing in MSA and Parkinson's disease, but the variability with regard to the brain region. And I was particularly struck by a more recent publication where they actually also showed this inverse relationship with the Lewy related pathology and with the oligomeric pathology. Could this be kind of giving us a clue? We always look for patterns in nature. And when we can start to see some of those patterns, we can really potentially draw out some of the underlying biology. I don't have the answers here, but I think it's very much worth investigating. And I think especially because of the concept of a temporal shift, right? Our chance to intercede and might be that certain brain regions have already progressed, but what they posited was that potentially these oligomeric forms may come before some of the Lewy related pathology that then comes before some of the neurodegeneration. And I know this is an active area of research, but imagine if our biomarkers were really revealing this and we had these very targeted therapies that many of the individuals in the room and online are actively working upon. And so that was really kind of some of the big picture view with some of the fancy multiplexing and what we're able to do when we really think about certain technologies and how we can manipulate them to be very specific. Well, we are in the future. I'm very into sci-fi, so it's kind of exciting to see machine learning in the reality that we're now able to be in. And I've been working in digital pathology for many moons, and I actually have a lot of repetitive motion injuries as a result. So I was very excited to start teaming up with machine learning specialists who can really help with some of the tracing, and I'll explain what I mean by that in just a moment. But I am only burgeoning in my knowledge. So we're going to just group it as supervised learning and unsupervised learning. I'm going to teach you a couple of the examples to maybe think about with your own research. So in digital pathology, the goal is to scan the whole slide. So as opposed to being able to look down the microscope, still very, very useful, especially at high resolution. But the goal there is to scan the whole slide, trace an area of interest, and then measure the burden. So we talked earlier about the temporal pathology, but this is very helpful from the spatial reasoning because neurons in proximity to neurons or glial pathology may have quite a bit of bearing, but especially with regard to the mixed pathologies that we've been talking a lot about today. And one of the capabilities that many different, well, some of the newer technologies have is with tissue classifying. So when you design an algorithm to recognize whatever is being stained, you have a lot of things that like to interfere. So there's something called lipofuscin, which is an autofluorescent pigment, not an issue in bright field, but the neuropil, so the background portions of the brain outside of the cells, will often also have some kind of staining. So you can actually class the tissue to teach it to ignore certain areas or to highlight areas of interest. And Dr. Dave Irwin's group really did a great job here of being able to leverage that technology to identify some of the differences and specifically looking at interactions of tau, A-beta, and synuclein. Now, I also want to highlight, once again, looking down the microscope, we've often relied on and continue to rely upon semi-quantitative assessments where mild, moderate, severe, it gives us something that we can all talk about. And it does have quite a bit of bearing. So whether we're looking at comparing the neuropath to biomarkers or biomarkers to neuropath, it gives us something to better understand. And amyloid PET has had quite a lot of actually contributions to improving our understanding. And some of the nuances there is some of the radioligands might recognize a little bit more of the diffuse plaque pathology. So when we talk about amyloid plaques, there's many types of deposits that can occur. We tend to see a little bit more diffuse plaque pathology in a dementia with Lewy body brain. And in this study, in a collaboration actually led by Dr. Kajal Kandarsi here in the audience, the importance of understanding the severity of the diffuse plaques was really quite helpful in informing our understanding of the amyloid PET and its deposition differences. And so if we could now do this on steroids, if you will, we now have opportunities where you can utilize neural networks to actually look for objects of interest. And so Dr. Duggar undertook this with a really awesome machine learning specialist where they specifically were looking at diffuse and cord plaques, and they're able to count the number. This does require somebody to label the data. So you need somebody that's an expert enough to say what it is or what it isn't. And some of the newer technologies where we'll be actually a member of my group who is amazing at amyloid plaque pathology. So she's an expert labeler. We're planning to expand this, but you can imagine some of the conversations we've had today about amyloid beta pathology, where it occurs, the severity that it might occur. Are there differences with regard to sex differences? Are there differences with regard to some of these cardinal features where some people may or may not have as much of an overt symptomology? And so the goal there, whether that is Lewy body pathology, the Lewy related pathology, or the different components of amyloid, I think could really help us change the considerations of what the therapeutics might do, right? Because if you're taking something away, if the therapeutics are actually targeting something, could there be a change in the deposition, the morphology? But having a computer help would really be quite useful. There are some individuals, so just recently, Dr. Ono, Dixon, and Koga decided to take a bit of a foray with ChatGPT. And so there was a newer version where you can interact and upload images. And while they do not think it's ready for prime time, I thought it was a really interesting approach where if you don't have a ton of subject matter experts to be able to label the data, can you on a very minute level teach iteratively? It differs a bit from generative AI, but if you only have a few shots to kind of teach something, their message was we're not there, but still sci-fi, right? I mean, that means the possibility, and it is not to replace the diagnostician by any means, but I think to help improve some of our considerations. One of the areas that really machine learning has come into quite a bit of play is to understand or to have the computer figure out what you're looking for. So once again, this is our whole slide imaging where we'll scan. We can have the computer somewhat learn about the regions of interest. But in this instance, the group undertook a really, I think, impressive study where they wanted to understand the range of which you can see it in a multiple system atrophy brain. And this is very distinct pathology, but can have quite a bit of regional differences that are important. And the goal here was to take the individuality of differences in these patterns, but try to find clusters. And how do you do this? Well, I actually learned about this elbow method. And so if you have to try to come up with some kind of clustering, you need to tell the computer how many clusters. And so there are different ways that they can approach this, where they can look to see when there's sort of a break in the number of clusters, if you will. And the individuals wanted to understand not just the distribution differences, but what this could mean from even the GCIs themselves. A lot of times we'll focus on the neuronal inclusion, but of course in the multiple system atrophy brain, the glial inclusions are very important to understand. And they found some robust differences, but I think more importantly, it just underscored the intersection of the neuropathology with the machine learning. And so without further ado, I'd like to thank my lab and for their understanding while I travel here to speak with you all, and for our generous funding and our collaborators. And I look forward to talking with anybody later, any questions they may have. Thank you.
Thank you, Melissa. After this talk, I really start to wonder now, do Android dream of electric sheep or don't they? So, but I will bring you back now to the hardcore reality. Let's see. Can I somehow go to the start? Huh? Is there a way to go on the? But goes to the. Can I go on slide presentation or? Ah. It gets even more confusing. Yeah.
Okay, so I will just talk about our basic neuropathological criteria, very, very basic. So that's what we really do. I mean, on a day-to-day basis, and then a bit about co-pathologies. How do we? So obviously, Lewy body diseases, this is incidental Lewy body disease, which means you have a little bit of Lewy body pathology, but no clinical symptoms, usually a little bit in the brainstem. Then you have Parkinson's disease, dementia with Lewy bodies. And as you know, and John Paul said this, the distinction and is on between PDD and DLB is just clinical. So in PDD, Parkinsonism has to precede the onset of dementia by at least 1 year. So there are no strict neuropathological criteria to distinguish those, although they differ neuropathologically, but there are no strict criteria. And obviously, as you know, there are Lewy bodies and Lewy neurites, and you see them here, the Lewy bodies in the substantia nigra, easy to see because they push the neuromelanin away, not so easy to see in the neocortex. That's why we are very lucky to have immunohistochemistry here. You see the Lewy bodies and Lewy neurites in nerve cell processes, which, as you can see, is similar to tau pathology. A lot of the pathology is actually present in the nerve cell process and not so much in the nerve cell bodies. So this is also very important. And Melissa mentioned this semi-quantitative scoring. So when I started my training and we all did this semi-quantitative scoring across all sorts of pathology. But as you probably can imagine, this is very subjective because here it looks mild, moderate, severe. That's quite clear here. But what about a case that is somewhere between mild and moderate, between moderate and severe? So we will have it's prone to have a huge inter-rater reliability, even intra-rater reliability, maybe Monday morning mild, Saturday evening, or Tuesday evening severe, or moderate, not severe. Anyway, so please keep that in mind because it will be important in this talk. So we have the Prague-Lewy body stages, then we have quite good criteria, this unified staging system for LBD by Tom Beach, and then the Lewy pathology consensus criteria, which are our kind of updated Newcastle-McKeith criteria. And again, please keep in, what are these criteria for? These criteria provide an approximation about the amount of Lewy body pathology in a given brain, and they do correlate with the clinical findings. So if you have neocortical Lewy body disease, you will have clinical symptoms, but they do not provide accurate information like Melissa was talking before, which we also do, of course, image analysis in the sense of histological slides, immunohistochemical staining, where we measure the amount that is covered by immunopositivity. For example, we found differences between cases that have both full-blown Alzheimer, full-blown Lewy body pathology, but some of them presented clinically as Lewy body disease, some presented as Alzheimer disease. With semi-quantitative scores, with these stages, you wouldn't find any differences because they would be all in the highest category. If you do image analysis, then you find subtle differences. But this is not what such criteria are for. They are just mainly should ensure that if we say Newcastle, this is neocortical Lewy body disease, that if Mayo Clinic say it's the same that Mayo Clinic would say is neocortical Lewy body disease and Imperial College in London and what have you. That's the only, it's a crude estimation, but it has to be in a sense accurate. Okay, so now let's look at the Prague stages. You see that they always assume pathology starts in the dorsal motor nucleus of the vagal nerve, and it gets more severe in this area as it progresses to the neocortex, and I show you this better. So pathology starts in the brain, in the medulla oblongata, and as soon as it gets a certain severity in the substantia nigra, you will get clinical symptoms, call it Parkinson's disease, and then it progresses to the, I'm not sure why, neocortex, and then you would have the pathology of dementia with Lewy bodies or Parkinson's disease dementia. However, there's a problem. As you know, only 25% of DLB patients have Parkinsonism at all at diagnosis, and 25% of autopsy-confirmed cases never had any Parkinsonism. So it's hard to imagine how the pathology in these cases marches through the substantia nigra without causing any clinical symptoms. So this is a bit of a, and that's also why when we look at the cases, you will have cases that have a lot of pathology in the neocortex, but little or sometimes no pathology in the medulla oblongata. So these stages are not very useful for DLB cases, actually. Unified staging system assumes the pathology starts in the olfactory bulb and then either goes via the brainstem or the limbic system meets in brainstem and then meets in brainstem and limbic system and finally goes to the neocortex. And again, heavily reliant on semi-quantitative scores, which makes it probably, as you will see later, a little bit prone to higher inter-rater variability. Then we have the Newcastle criteria and Leverance modification of these criteria, which is actually a bit of a, make it a bit more straightforward. And they do not so much assume a topographical progression, so you can have a kind of severe pathology in neocortical areas and only low pathology in brainstem regions. So that's helpful. They're straightforward. However, they have one disease, limbic and diffuse, correlates to dementia with Lewy bodies or Parkinson's disease dementia. But they have a problem. You can have cases, for example, if a case would have these semi-quantitative scores, you could actually really choose if you want to call it brainstem predominant or limbic. You could toss a coin. So that's a problem, and you can come up with the same case for between limbic and diffuse. So that's certainly not what we want, and that's why we were asked. Actually, Ian He'd asked us to come up to kind of update this criteria. So, and we have chosen an approach like Dietmar Thal did with his amyloid phases to be kind of a dichotomous approach. We say, is there pathology or is there no pathology? And as you can also see, if a case would have pathology in neocortical areas, it doesn't actually matter if there's pathology in other areas. We would call it neocortical. However, to be honest, there will be pathology in other areas, but we just didn't want to make it a conditio sine qua non. So yes, no topographical progression, and then this dichotomous approach. So if a region would be called sparse in the McKeith criteria or some in the paper by Irina Alafutsov, so the lowest amount of pathology, then we would call it present and otherwise absent. Unfortunately, in our publication, we had this picture, this image, which actually should just show what is a lesion and what it is not a lesion. It's not to score an area positive or negative. And we only have this image because the reviewer wanted this image, otherwise I wouldn't have come up with it. So it should just show this is actually a Lewy neurite, whereas this is just rubbish. This is nothing. This has nothing to do with the scoring. So, however, this introduced is a problem now because some people believe we say an area is positive if we find this little thingy here, which is not true. Please, we say it's positive if you find at least this amount of pathology. So if you would say mild in all the other systems. Okay. Yes, so that was our aims, that ideally all cases can be classified. Only one diagnosis per case is possible, low inter-rater variability, and actually we didn't want to have a lot of cases with neocortical Lewy body pathology, but no clinical symptoms. That were 35 cases, just Lewy body cases, and we loaded it on Apereo software. So 16 colleagues from 13 centers looked at that. And we provided semi-quantitative scores for all sections and then classified according to Prague, Newcastle, Beach, Unified Staging System, Leverance modification, and our proposed new criteria, and analyzed the data. And quite quickly, you see here the reliability. So the inter-rater variability was highest in Prague stages and Beach staging. And this is not surprising because these are the stages that rely mostly on the semi-quantitative scoring, and the most subjective, more subjectivity you introduce, the higher the likelihood that people will disagree. And was better for McKeith, Leverance, and our proposed staging system. Non-classifiable cases, again, in Prague staging was that was the highest, because if you take the Prague stages by the book, you have to say, okay, I have a case with a lot of pathology in the neocortex, but very little in the dorsal motor nucleus. I have to say I cannot classify it because it has to be 3. Of course, in the past, neuropathologists would kind of look over that and just say, well, I call it Prague stage 6 anyway, but it's not what really wants. So, and here people were asked to do it according to the book. And same with McKeith, I showed you before, you have cases that can be fall either in this category, in another category. So if you go by the book, you have to say, I cannot classify it. And was better with, we could actually, all cases could be classified with our new approach. Yes. And then, I mean, we did a few other things, but I do not want to bore you with that. But just we then, John Toledo and myself, we looked at our old cases. We didn't look at the cases. We just took the reports with the semi-quantitative scores, just to see if we find kind of cases that would now be new cortical Lewy body disease, but clinically controls. And there was just actually in our cohort, there was really one case, but this was also in the Prague stage. It would be Prague stage 6, and also in our staging would be a neocortical case. So maybe there was something wrong with the clinical information. I don't know. But by and large, all these criteria fit well with the clinical findings. Okay, so we had a low inter-rater variability. All cases were classifiable, and most importantly, these criteria are really straightforward to apply. And that's actually all that matters. Our idea is that even if someone is relatively new to the field, looks at post-mortem brains and says this is neocortical Lewy body disease, that it is really neocortical Lewy body disease. And this is not a nice picture from a publication. And you should look at olfactory bulb, ideally, if you have it, amygdala, dorsal motor nucleus of vagus nerve and substantia nigra, medial temporal cortex, cingulate, frontal and parietal cortex. But it's enough if you have frontal or parietal cortex positive or medial temporal or cingulate to call it kind of limbic or neocortical respectively. So much to the criteria, I think. Now, shift gears, completely different. Forget about diseases or anything, just think about old brain and prevalence of pathology. This is important. So here you have tau pathology, A beta plaques, TDP43 pathology as seen in limbic age-associated TDP43 encephalopathy, and alpha-synuclein. You see that virtually everyone, the majority of people above 60 years of age have at least some tau pathology, and virtually everyone over 80 years of age. Most will have just very low tau pathology, Prague stages 1, 2, but quite a few have higher Prague stages. Only 80% in this cohort had A beta pathology, 80% this type of TDP43 pathology, and around 50% alpha-synuclein pathology. And now, if you talk about co-pathologies, ask yourself the question, if you fall into this group, for example, here, dementia with Lewy bodies, why on earth would that prevent you from being in that group as well? It doesn't. So it goes without saying that we have co-pathologies. It goes without saying that every old brain has tau pathology. It is inevitable that it's question is just how much. And this is also something that a lot of these talks, when I hear about co-pathologies, we have to differentiate between tau pathology, Prague stage 1, 2, 3, 4, and 5, 6. This is a difference. It's not the same. And sometimes these things get mixed up. And if I wonder if people that are new to the field, if they hear that, they have no clue what's going on. It seems everyone has everything, but only a few are demented. And some people are not demented, have older pathology, which is not the case. If you bring clarity into that, it's actually not so confusing as it seems at first. Now, one of the first papers that made me aware was by the group of the late John Trojanowski in 2017, where they looked at, I mean, that was not their main question, but I found that over 200 patients with Lewy body disease, 30% had high-level Alzheimer's disease neuropathology. This is important, high-level Alzheimer's disease neuropathology. And we, in the so-called Brains for Dementia research cohort, is a nationwide cohort across the UK from Bristol, King's College in London, Newcastle, Oxford, Manchester. We looked at all sorts of diagnoses, and these are the main diagnoses where 31% were neuropathological diagnoses. These are full-blown Alzheimer's disease. When I say AD, I always mean Prague stage 5, 6, Tal phase 4, 5. Nearly 10% Lewy body disease, and 11.2% mixed AD DLB. And by that, I mean full-blown Alzheimer's disease and full-blown dementia with Lewy bodies, neocortical Lewy body disease, okay? So that's important. These are what we call mixed AD DLB. And now, if I take the LBD cases, we have 66% with Alzheimer's disease pathology, 41 low, 24 intermediate, and then an additional 23 with late and Alzheimer's disease pathology. but this does not include the ones with high Alzheimer's disease pathology because these are the mixed cases. So if you have the mixed cases and the 65 LVD cases, that gives us 140 cases with some degree of Lewy body pathology, of which over half of them have full-blown Alzheimer's disease pathology as well. But this is our cohort. I'm not saying that this is everywhere, but you have a selection bias all the time. Nearly 20% intermediate, 23 low, and 3.5 no AD pathology. And if you now compare this with this from before, you see that actually, apparently, if you fall into this group, you are actually more likely to have A beta in your brain than if you have no alpha-synuclein pathology, because you should, in that age group, about 60 to 80% have A beta pathology, but here nearly everyone has A beta pathology. Now the question is, I don't think that the alpha-synuclein pathology causes A beta. I think it's the other way around. A beta triggers alpha-synuclein pathology in dementia with Lewy bodies because the PDD cases, 67% had low, 33 intermediate AD pathology, but so they had a lot as well, but there was no high AD pathology in the PDD cases. And that brings me, I think, to that slide. Yeah, this is another kind of a little bit of an aside. This is just what I think, I cannot prove that. But what my looking at the thousands of post-mortem brains suggests to me is that PDD is basically an alpha-synuclein disease where the pathology starts in the medulla oblongata, maybe or maybe not coming from the gut, and then progresses to the neocortex. These cases will have, because they are old, will have some degree of A beta and tau, mild, moderate degrees. On the other hand, DLB probably starts somewhere here, limbic system, maybe in the amygdala, and then goes in both directions. And here they always have A beta and tau. This is always present, so must play a role in the disease. And for me, this is actually sufficient to say that this is not the same disease. But I know this is, of course, very controversial. But that's, as I say, this is my view after looking at so many post-mortem brains. I can tell you, PDD is a synucleinopathy. That's just the main thing. But usually you have a lot of A beta and tau and DLB as well. Okay, I'm nearly finished. Just so this additional pathologies, and I mean, this is just I heard in the morning. I personally think we shouldn't speak about DLB, PD, AD anymore. We should speak about patients with that and that pathology in the brain. This makes everything much clearer. And so I usually give a talk about multimorbidity in general. Today, I kind of twisted it to multimorbidity or multiple pathologies in DLB. So if you have a trial, therapeutic trial, imaging study, biomarker study, and you look at a clinical DLB cohort, you will have some of them will have alpha-synuclein and low tau A beta, as you've seen now. Some have intermediate pathology, some will have high pathology, then there will be cases with vascular disease, with TDP-43 pathology, but you have no clue what you're looking at, actually. You think it's a homogeneous cohort. That's how you think and how you interpret your findings, your CSF markers, what have you. So what you would obviously need, you would need postmortem assessment, because then this homogeneous, so-called homogeneous cohort, you would see the heterogeneity, and that could feed back then into your clinical data, and that probably would make much more sense. And in the end, we all know that. Yes, and you would really be able to see what's going on. However, the problem is, as we all, it's impossible to do that with neuropathology because we need that on a large scale. So, and this is an idea that actually Seth Love, some of you may know him, famous neuropathologist, I think he's retired now, but he had this idea maybe 10 years ago, and we wrote a grant for the MRC because the MRC asked us, but then they didn't fund it, of course. Anyway, so, but the idea was that someone dies, comes to the mortuary, and not even a pathologist, probably a mortuary technician, takes maybe the brain cap off, takes a few samples, probably biochemically assays, and then you get a readout. It's not the same accuracy, there's not the same detail as a full neuropathological assessment, but that would be doable. However, if you do that, it should be, the method has to be really bulletproof. because otherwise it would even introduce more kind of confusion in the whole field. But I think that would be really what we should, I mean, beside all these futuristic things and image analysis and artificial intelligence, I mean, we should not forget about the basics and maybe increase, because humans are not transgenic animals. And that's why we are really, take amyloid angiopathy. Most of cases with amyloid in the brain have amyloid angiopathy, but not all of them. Some have nothing, and some have a lot of amyloid angiopathy, but no amyloid in the brain. So what I'm saying is it's so heterogeneous, and we really should have a good readout so that all the clinical data make kind of imaging data, biomarker studies really play to their full potential, so that in the end, sometimes we won't need neuropathology anymore. That would be the best. Okay, thank you very much.
Trying to move forward here. Oh yeah, the PDF to the PowerPoint. No, I'll give you a talk. Oh, there we go. Thank you. Well, I want to thank the organizers, Nina and Deb, for giving me the opportunity to speak today. So I'll talk about using proteomics and integrated proteomics to nominate biomarkers for Alzheimer's disease and LBD. So over the past decade or so, my team has been involved in the Accelerated Medicine Partnership for Alzheimer's disease. So when we were enlisted into this program, we were really tasked to do unbiased tissue-based proteomics of postmortem brain tissue. And we did this using mass spectrometry. And I think the challenge was actually taking this data and making knowledge from it. And each of the samples was about 10,000 proteins deep, and everyone says this is a great fishing expedition. And how do you actually convert what you're measuring from the brain into actionable therapeutic targets and biomarkers? So we did one way we do this is using data reductionist approach that Melissa talked about earlier, using network-based proteomics, where we're able to collapse these 10,000 proteins into 40 or so protein modules. And then we're able to integrate other omic data sets to essentially assign them biological function and ontology. And one of the greatest drivers of protein co-expression, even at the in the brain, is really cell type changes. And this would be loss of synapses, increases of microglia. And of course, once you have these modules, you can look at their aggregated protein expression profiles and see how they change across the continuum of Alzheimer's disease, from this control pathological free state to this preclinical or asymptomatic state into a symptomatic state of disease. And then we want to take these and say, can we actually nominate therapeutic targets? And I'll talk about today is actually how do we integrate spinal fluid data into this postmortem data to come up with novel panels that reflect this diversity of pathological changes that are seen in AD beyond the amyloid and tau. So this is a study that was led by Lenora back in 2020, where we took a network-based approach in Alzheimer's and control cases, built these modules, and then we looked at the overlap at the protein level between patients' cerebral spinal fluid from the Embry-Gosweda Alzheimer's Disease Research Center from control and AD. So it's about 9,000 proteins at the network level from the brain and about 2,500 proteins from the spinal fluid. And what was nice to see, about 70% of the proteins that we detect in the spinal fluid overlap in the brains, supporting that hypothesis that the CSF is a window into the brain. And then what Lenora was able to do is then map to those modules and say, well, are these CSF proteins related to synaptic changes? Are they related to vascular, immune, metabolic myelination? And we were able to come up with then more discrete panels, going from a more unbiased to a more panel-based metric, where we would have these 5 core panels being synaptic, vascular, myelination, glia immunity, and metabolism, and then correlate them to neuropathological measures of amyloid tau in the CSF. We were able to replicate this in over 500 independent CSF samples. And then we were able to go away from the discovery base and come up with data-driven peptide selection to really scale these assays, because it took a lot of time, a lot of effort to run these individual samples at 10,000 proteins. We were able to come up with a targeted assay where we can run 100 samples per day and then come up with prognostic panels. Could we use the information that we gathered from this brain overlap to come up with panels that we could predict dementia, or we could predict amyloid and tau status. So what we did is that, and this is a panel paper that was published a couple years ago, or I guess last year by Rafi and the group, where we took our 48 protein panel and the ADNI cohorts, a little over 700 individual CSF samples, and everyone had amyloid and tau measured in their CSF. And our panel of 48 proteins that represented these diverse pathophysiology did not have amyloid and tau on it, but it was able to predict the amyloid tau positivity status with a 0.97 AUC, with some of the proteins getting up to 0.9 AUC or greater. So we said, oh, that's a great example of how you use that. And I'll talk about how we would like to use a protein panel to predict SAA positivity in the DLB cohorts. So what about dementia? Can we predict dementia? And if you use the canonical biomarkers of A, beta, and tau in gray, they have an ability to predict cognitive dementia at first visit at a 0.9 AUC. The protein panel slightly outperformed it at 0.94, but when you combine it together, you can get an AUC of 0.96, which was really remarkable. And I think it's because some of the proteins we measure are synaptic proteins themselves, like neuropentraxin-2, neuropentraxin receptor, and VGF. And these proteins in the brain are some of the most correlated to your slope of cognitive decline in life. We know that from longitudinal cohort studies like the Religious Order study and the Memory and Aging Project, is that these proteins, the higher the amount of these proteins you had in your brain, the slower the slope of your decline in life. So these are great markers of cognitive decline in the spinal fluid. So we wanted to see if we could take a similar page out of the playbook, and we applied for a U01 grant in the PDBP. And our goal here was to develop protein biomarkers of LBD in blood and CSF using this brain biofluid integration. It's a study led by myself, Alan Lewy, and Lenora Higginbotham that you heard about earlier today, where she discussed the first aim of the project was to take this unbiased approach to brain network proteomics to get at differences and divergent changes between Alzheimer's disease and Lewy body diseases. And I'm going to talk about aim 3 now, which is really to integrate those and see if we can actually see if there's differences at a biomarker level between Alzheimer's disease and LBD. So just a quick snapshot of what Lenora showed earlier is one of the main findings in her paper was that the synaptic proteome, in particular, there's presynaptic changes within LBD across PD, PDD, and DLB. Many of these presynaptic changes were increased in the postmortem dorsolateral prefrontal cortex. And that those same changes, when we've looked at least 2,000 Alzheimer's cases, these same proteomic or synaptic changes are decreased in the brains of Alzheimer's cases. So there's already a divergence there at the postmortem level. Now we wanted to ask if we actually could capture some of those divergent changes in the CSF. So we did apply and got 685 individual PDBP CSF samples. There were 476 unique individuals, 86 controls, 178 PD, and 185 DLB cases. There are 204 cases that have paired longitudinal CSF. We have both their baseline and we have 24 months later. We don't have that data to share today, but we will be sharing that soon on using the proteomic platforms that I'll describe. These cohorts are predominantly heavily enriched with male over female, and about 81 of the Parkinson's disease cases had MoCA scores below 26. So we reclassify those as PD, MCI, or PDD. Also, there's a group of these individuals that have alpha-synuclein seed amplification assay, and we'll be looking at stratification of that group within the DLB participants, the 185, in which we had 92 that were positive, 38 that were negative. So we ran cross-platform proteomics on all of these samples. We ran the new LISA assay, which I'll describe. They have a CNS panel that actually takes a lot of the hallmark amyloid tau and neurodegeneration markers, and we'll show that data today. We ran a high throughput data independent mass spectrometry assay. We can run this at 100 samples per day, and that gets about 1,200 individual proteins. And then we also ran this deeper tandem mass tag based proteomics, which gets us 2,500 proteins. And I just learned this morning that that data is now complete. So I won't share that today, but that gives us another layer of proteomics. And for those not familiar with the new LISA assay, it's a proximity extension assay. So it's paired antibodies against a single antigen. There is a nucleic acid bridge, and then you're able to amplify that because that's nucleic acid. You can use next generation sequencing. You can multiplex that. You can do 120 individual analytes at the same time. Collectively, when you look at the proteomic cross-platform numbers, there's actually only about 40 of the targets that are shared across all three platforms, and there are 2,700 unique proteins that you can measure across all of them. And of course, as I mentioned, the CNS disease panel will measure beta amyloid, both 38, 40, and 42, total tau, the p-tau species that we're very familiar with from the Alzheimer's field, 217, 231, and 181, GFAP, neurofilament, phospho-TDP, as well as alpha-synuclein. So this is the, as we now break it out between control, PD, MCI, and DLB, we wanted to take a first look and say, how did the ATN biomarkers that we used to stage Alzheimer's disease progression, how did that look across this LBD continuum? And you can basically see that as you go from control, PD, MCI to DLB, you see lower levels of A beta 42 in the cerebral spinal fluid. And this is indicative of cortical plaque or plaque deposition in the brain. And conversely, you'll see an increase in MAP tau and the phospho-tau species. And again, seeing this almost spike in the DLB cases, and we just heard about the higher number and the degree of comorbidity in the DLB population. This group of individuals will have both synuclein pathology, Lewy body pathology, as well as Alzheimer's pathology. Neurofilament light chain, marker of neurodegeneration, right? Up in PD, MCI, and DLB. So there's neurodegeneration occurring across all the clinical groups. However, the amyloid and the tau pathology seems to be predominantly enriched in the DLB group. Neuropentraxin 1, 2 are very much correlated to slope of cognitive decline. And you would see that the group that has the most cognitive impairment, the DLB group, have the lowest level of those in the CSF. And this ubiquitin carboxylase UCHL1, which is increased in both AD, also sees an increase in the DLB group. So we wanted to ask a separate question here, is that could we now use the SAA biomarker positivity, which is a binary score, it's a yes or no, could we substratify within that and get at protein biomarkers that could distinguish between SAA positive DLB cases from SAA negative DLB cases versus the control? And if you look at SAA positive versus control, and then SAA negative DLB versus control, they're very similar in their direction of change. You see a lot of Alzheimer's biomarkers. But if you look at DLB within the group, DLB SAA positive versus DLB SAA negative, there's only 9 that are up and 8 that are down. And it was sort of interesting to us is that when we looked at A beta 42 and the phospho-tau species, despite them being higher in the DLB or lower for A beta, they didn't significantly differ between the SAA positive DLB versus the SAA negative DLB, suggesting that there are other markers that would discriminate those two classes or those two groups. What was interesting is that A beta 38 and A beta 40 were both lower in the SAA positive DLB cases compared to the SAA negative DLB cases. And I was reading up on A beta 38. I mean, the lower the levels of A beta 38, the more rapid your cognitive decline is. So this could be a prognostic change and sort of indicative of that idea. If you have co-pathologies, amyloid, synuclein, and tau, you may have a more rapid decline. A beta 40 is more linked to cerebral amyloid angiopathy or vascular amyloid, and that is lower in the DLB positive versus negative, but A beta 42 is not. Synuclein is lower, but we see this spike in the SAA negative, which suggests there may be some dynamic changes that Melissa was talking about, oligomeric changes in amyloid. Why that would, it's not significant. Why that would spike in the SAA negative versus the controls is interesting, but it is a significant difference. And then neurogranin levels are significantly lower between those two groups. And I wanted to point out neurogranin in the Alzheimer's biomarker space, neurogranin is always increased in cerebral spinal fluid. On the right, we show neurogranin in 168 samples from the Emory ADRC, and this is run on the Neulisa. It's significantly increased in the AD versus control, but in PD, MCI, and DLB, you have lower levels of neurogranin. So here's a divergence between the synaptic markers that we saw in the brain that may be now manifesting in the cerebral spinal fluid, that the neurogranin levels would be different between LBD or Lewy body diseases versus Alzheimer's diseases. Or one of the cool things about having cross platforms is that you can immediately benchmark these changes on a different proteomic assay. So you can now go on to the mass spec assay and ask, how does the neuropentraxin 2, the FABP3, and the UCHL1 levels correlate? Not all of them look this good. I'm putting up really nice ones. There's some really bad ones. Yeah, so next time I can show you a lot of ones that don't correlate, but it gives you added bit of confidence. And I think this is when you go into the peer review space and you go and you want to be confident in your measurement. These particular biomarkers and these particular proteins and neuropatraxin, FABP3 and UCH1 are nicely and robustly changing across both platforms. Whereas, if you look at FABP3, it's up in positive and negative SAA, whereas UCHL1 was one of those proteins that was starting to discriminate within the DLB group, the SAA positivity versus the SAA negative group. So where do we want to go, right? I mean, I heard a little bit about how challenging it is to run these SAA assays. Could we come up with a really high throughput, 100 sample per day, and be able to predict SAA positivity in our clinical samples at first visit? And if we could do that, could we start to predict whether you'll be more rapid progressor or more stable in your course of disease? And I think this is this is simple logistic regression. This is not any SVM fancy machine learning yet, but if you can get a 0.84, 0.83 in the top 5 to 10 biomarkers by DIA, multimodal going across the platforms, we would like to see this get above a 0.9. It would add some confidence in our ability to screen out very quickly without having to do the more binary assay of the SAA. So last couple of slides, just moving forward, is what we want to do is how they change in the postmortem brain. This is us now mapping the changes that the DIA mass spec gave us about 1,200 proteins. We can then now overlap these into this synuclein hub network that Lenora talked about and see, can we detect some of those proteins? And the idea is, yes, we can see them. And many of them do actually, despite there being some divergence in the brain, there is consistency, but we are starting to pinpoint like BASP1. Here's a protein, BASP1, that's always increased in Alzheimer's disease, yet is significantly lower in PD, MCI, and DLB. So I think as we get the deeper TMT data and we start to really cross-reference those, we will see this synaptic divergence that we saw in the brain for a subset of these biomarkers that are in the spinal fluid of these LBD folks. So really conclusions and future directions. We are starting to see some divergent trends in the spinal fluid that are concordant to what we saw in the brain. We would like to predict cognitive progression at baseline, and we have that ability with the longitudinal data. We want to look at disease severity. We would like to use any of the phenotypes that are available for neuroimaging to see if we can relate these to data imaging or what we have available for the PDBP. And what I'm showing on the right is this idea of getting away from the pathological and clinical construct, is that we took 483 CSF samples from the Emory ADRC, and we molecularly subtyped them based on their proteomic signatures. And this is very much aligned to what Betty Times has done at Amsterdam, and that can you just stratify individuals based on proteomics and then look at their clinical and pathological hallmarks. And we can see that there are subtypes related, and it's very similar to what Betty saw with, related to blood-brain barrier dysfunction and there's at least 3 different type of AD subtypes that differ in their synaptic profiles. Would any of these individuals in the Emory ADRC have underlying synuclein pathology? Probably. Could we use the information from the PDBP now to predict that going back into our Alzheimer's data sets? That would be the goal. And then the last thing is that we have paired plasma from each of these. So we will then be able to go back now and say, well, any of the diagnostic or prognostic markers that we come up with, can we take that information and can we now measure that in blood? And can we use this as a point of care even? Can we actually come up and say, or can we better get you to a clinician faster who would help you diagnose this and hopefully get you on the right track? So with that, I just want to thank my group, of course, the NINDS for the funding, and looking forward to serving on the panel later. Thank you very, very much.
So good afternoon, everybody. I hope my slides are going to come up soon. My name is Sonja Scholz, and it's a tough act to follow these great talks. And I hope you're still mentally there to hear a lecture about genomics. I'll keep the biobabble, to a simple level right now, because what I really want to do is I want to highlight a couple of interesting insights on what we have learned in the last couple of years just by going after the genomics of LBD, but also I really want to showcase that genomics is not just an intellectual exercise for us in the lab. It really has a lot of translational opportunities, and it's very powerful if we double down on our genomic research efforts. So here are just my disclosures. And so some simple things that I want to introduce is, genomics, but also functional genomics is kind of a given, that you not only look at the genetic information, but you also look how does the genetic information inform us about transcriptional changes, proteomic changes, metabolic changes. Kind of, it's one thing are really advancing very rapidly and are giving us very crucial insights into the pathophysiology of LBD, but of neurodegenerative diseases more generally. I'm going to highlight a couple of specific insights that we have gained, and then really also highlight some translational opportunities and how we've already leveraged that knowledge. And so as geneticists, we always we like to think about the complex disease model where we have some patients who have a family history, where we like to look at linkage analysis, segregation of disease-causing mutations, which certainly applies to a small subset of our LBD patients. But for the most part, when we're talking about genetics, we really talk about association studies, so genome-wide association studies or burden tests. And then in reality, that immediately now is being linked to other types of omic data. So we're pretty good on the linking genetic information to transcriptomic data. But increasingly, as more and more foundational data sets are being made publicly available, we can link it to other omics, proteomics in particular, is very exciting as well, and apply more of a systems biology framework. And so you can really go from a genetic variant or a genetic locus to zooming in, what is the likely functional variant, what's the likely gene, and in some cases we can even tell what the potential mechanism is, so really kind of shortening some of the discovery pipeline there. And so we've already heard a lot about Lewy body dementia. It's a complex disease, clinically complex, it's pathologically heterogeneous. We know that the co-pathology is actually the norm rather than the exception. And we do see interesting family histories again and again when we apply more liberal criteria and ask our patients, do you have a first or second degree relative with Parkinsonism or dementia? But 30% of patients actually report that they have that. So it's not that it doesn't exist. It's just in reality, we're dealing with a lot of risk variants and a lot of mutations or variants that have decreased penetrance, and it's very difficult to tease it apart unless you have large numbers. And that's really was the major impetus for the LBD genome sequencing initiative that my lab was leading. And so the idea was to generate a foundational data set that we can share very broadly. And we went through all the brain donation programs that we knew about. We collaborated with most of the people in the room anyway, and across North America and Europe, and had about 2,600 LBD cases. More than 2/3 were path confirmed, and the clinically diagnosed subset were actually clinically probable cases. So we wanted to have really well-characterized cases where we had diagnostic accuracy. We did all the heavy lifting, the genome sequencing, the alignment, the data harmonization, etc. And then we applied a range of different analysis. I'm going to just highlight a few of them, but importantly, we wanted to, make these data available. And so they are public, and it's the summary statistics, the raw data, etc. And the idea is to really stimulate and accelerate discoveries across the board. It's been already quite successful. And the good news is we are doubling the sample size. So genome sequencing is essentially done. We just have to now assemble the data. So really, it's a numbers game, and we are learning more with every iteration of the analysis. And so in the first phase, we did a GWAS analysis on the common variants, and we identified 5 different risk loci, some of that which we kind of already knew based on candidate gene work. So ApoE was very well known, SNCA, where you can see sometimes mutations that cause a familial form of the disease, but also, general variation in that locus, which encodes the alpha-synuclein protein, is also clearly associated. GBA is a big one, very common, very prevalent, not just the severe mutations, but also milder variants are really prevalent. And so you can pick them up in a GWAS that's by genomic standards still modestly powered, actually. But the other thing that we noticed were two other genes that hadn't been implicated at that time. One was BIN1, a known Alzheimer's disease risk locus, and TMEM175, a Parkinson's disease risk locus. And so kind of just by looking at the loci and knowing the genetic architectures of Lewy body dementia, Alzheimer's, and Parkinson's disease, you kind of see where Lewy body dementia really sits. It partially intersects with all of them, but not in every individual case. And so there's a lot of heterogeneity just based on the genetics itself. And then, I'm going to just showcase how we could leverage some of the, transcriptomic data. So basically, when we are looking at the SNCA locus, which encodes the alpha-synuclein protein, the main signal that we're seeing is actually at this 5' end, which overlaps a non-coding transcript called SNCA AS1. And this is different from where we see the predominant Parkinson's disease GWAS signal. Based on the transcriptomic data and the data integration that we did, we could essentially pinpoint that the most likely functional variant in this locus is actually a variant that naturally occurs in the SNCA AS1 non-coding transcript, which regulates the expression of the alpha-synuclein protein. So if you happen to have more of this SNCA AS1 gene, you have lower levels of alpha-synuclein, so you're relatively protected, your risk is lower. And it essentially indicates that SNCA targeting strategies or synuclein lowering strategies may have real therapeutic potential there. And this is just, in silico work. This is without touching the patient, but it really highlights this is an interesting target and we need to continue to work on that. We've also been able to show more broadly that there's overlap in the genetic architecture, so we can use so-called genetic risk scores where we see that LBD patients have a higher genetic risk for Alzheimer's disease, even if you exclude ApoE and some of the big genes. And the same is true also for Parkinson's disease. And we see certain pathways that are coming up again and again. And some of the bigger ones, are really protein related to protein degradation, but also in the lysosomal function, et cetera, and really highlights that there's a lot of overlap, molecularly speaking, across the neurodegenerative diseases spectrum. But once you have genomes, you can also look at rare variants. So those are more high impactful mutations. And GBA is certainly one that actually even shows up on a rare variant analysis, where we can see a whole host of different mutations, missense mutation, loss of function mutations that are actually present. When you sum it up, the common variants and the rare variants, they're really prevalent in the LBD patient population. So in our European ancestry cohort, we can see it in 13% of our patients. And so it's a great target for therapeutic interventions. There's a lot of work happening in Parkinson's disease already, and I think it would obviously immediately apply to the Lewy body dementia patient population based on its importance. But we have a lot of fun analyzing genome data. It's a massive data set. And there's a lot of genetic variation that is not as easily mapped. And so one class of genetic variants are so-called structural variants. So those are deletions, duplications, inversions, translocations. They're harder to map, but we're getting better now computationally to actually pin them down. And so what we did here was essentially use these data sets and perform a structural variant analysis. And lo and behold, we found a significantly associated deletion in the gene called TPCN1, which is actually quite common in the LBD patient population, has a sizable odds ratio by genetic standards. It's also interesting because it has been suggested in Alzheimer's disease, and our genetic data, when we compared our GWAS signals to the Belengas et al. GWAS, we could clearly show this is correlated, even the same haplotype that is coming up. And so this is a nice example where actually studying a rarer form of dementia, it really informs the broader dementia spectrum. So we've really shown that it's an important Alzheimer's and Lewy body dementia risk locus. But interestingly, it is not associated with Parkinson's disease, which is shown on the right side here. And so some themes that are clearly emerging is that some of the risk genes that we're picking up are really implicating that there is shared biology. And that is actually good news because it highlights that there are real opportunities for drug repurposing. There's certain drugs that are developed in the Alzheimer's disease and the Parkinson's disease field that could be really relevant to the Lewy body dementia patient population. But how else can we use genomic data? And then this is where it gets really exciting. So I'm going to show you a study that started out with an epidemiological approach, trying to look for drugs that are protective for Lewy body dementia. So we used the Medicare claims database and basically pulled out patients who have been diagnosed with Lewy body dementia and age sex matched controls. And we then looked at the 3 years before they got the diagnosis of Lewy body dementia. We wanted to go into the prodromal phase. That's the phase where we really want to intervene ideally. Composition was pretty great by LBD standards. We always struggle with diversity in our cohorts. So I was really proud that about 20% of the patients were actually non-European white individuals. And then we performed a very broadly adjusted logistic regression analysis, asking which of the 1,017 prescription drugs are associated with a lower risk of Lewy body dementia. And so one theme that very clearly emerged is that drugs that are important for cardiovascular disease management are associated by and large very clearly with decreased risk for Lewy body dementia. There were a few exceptions, which we interpret as reverse causality. So there's propranolol, which we often give in patients who develop a tremor, etc. There's also some of the insulins, which I think some of the people are getting when they develop some mild cognitive changes. As we optimize the diabetes care, that can give rise to false positives. Across the board, we see a really clear protective effect. Now, this is a messy, Medicare claims database. This is not a research database, but the numbers are really phenomenal. In order to really tell something whether something that is associated could also be really molecularly driven, we went to our genetic data. And this is where, genetic resources are really very important. So in essence, we wanted to ask, is there a genetic relationship between Lewy body dementia and cardiovascular traits? And it's actually quite straightforward to do these kind of analysis. So you can use summary statistics, use our GWAS from the LBD case control cohort, and we use summary statistics from cardiovascular traits, hypertension, hyperlipidemia, LDL cholesterol levels. And then what we do is we ask, well, is there an actual correlation between those? Is there genetic overlap based on that? And lo and behold, we see a clear positive genetic correlation between cardiovascular traits and the genetic architecture of Lewy body dementia. We can do additional modeling where we basically do analysis asking, well, is your risk of Lewy body dementia increased conditioned that you have type 2 diabetes, conditioned on having hypertension? Regardless of how you model it, how conservative you are, there's always a positive correlation. It always deviates from the null hypothesis, which is the diagonal line. And so that's kind of the fingerprint of a causal relationship. And what's the exciting thing is, now this is where we are linking, real potentially modifiable risk factors to the pathophysiology of LBD. So it's not just epidemiological data. This is now molecular data that really corroborates what we found in the Medicare database. And so increasingly, our mindset is that, the genomics can really inform drug discoveries. There are multiple examples already that are coming from oncology, cardiovascular diseases. But now, as we're building up these larger cohorts, we can really refine what we do also in the neurological disease space. And there's good reason to be optimistic, because it's more likely to get a clinical trial that is successful and get FDA approval if you have molecularly anchored, data. And so we hope that, we will soon also get toward genuine disease modification for a lot of the neurodegenerative diseases. Now, there are many challenges ahead of us, so we still have a lot of work to do, and it's a great field for anybody considering entering the field. So we need larger cohorts. We can do a lot of great computational modeling, but the more the better. We need more ancestrally diverse patient populations. And a lot of the foundational data resources need to be shared publicly, easily accessible, etc. So many of the the discoveries in the latest years have really leveraged our data, and then we hope that we continue to build up those cohorts to really be a driver for disease modification in the future. And so this is where we're hopefully going. So we can, we're trying to really anchor our knowledge in the genetic information. It gives us a lot of information about the pathophysiology so that we ultimately get to the right patient, right time with the right kind of drugs. Let me see, now it's stuck or not. I think I'm stuck. Okay, I think we're stuck here. Okay, so I'm wrapping up. So, so there have been rapid advances in our understanding of the molecular genetics, Lewy body dementia, but also of neurodegeneration more generally. I could fill hours to talk about it, but I hope I was able to showcase that the genetic architecture is really interesting. It's very complex with common variants, with rare variants, with overlaps between Alzheimer's and Parkinson's disease, but we can increasingly use our genomic knowledge as an anchor to, look at relationships, molecular relationship, look at subtypes, etc. And that gives us unique new opportunities for drug repurposing, but also for disease modifying therapeutic interventions. So with that, I'm going to just highlight a few of the main, collaborators. I cannot fit them all on a page. So for those of you who don't see your name on it, I'm very grateful. For those of you who want LBD samples genome sequence, please reach out. We are driving the numbers up as much as possible. With that, I'm going to stop here. Thank you.
Right. Good afternoon, everyone. Thank you for sticking around to the last minute and the last talk. It's been a great day, lots of information. So thank you to the organizers. Thank you to Nina and Deb for the invitation to present today. And I was charged with talking about cell culture models for preclinical studies and what the state of the field is and what are the opportunities we have for perhaps creating better model systems. So the question I'm posing here is what type of Lewy pathology should we be modeling? So we know from this slide, this is just one of these progressive pipelines you see where we know alpha-synuclein is natively unfolded protein, but it can become misfolded and form oligomers and protofibrils, eventually fibrils, and then deposits as a Lewy body intracellularly in the brain. But we know that a Lewy body is not just alpha-synuclein now. Yes, alpha-synuclein is a major component of Lewy bodies, but there's other proteins, there's autophagosomes, there's lipid membrane fragments, mitochondria, vesicles, other proteinaceous aggregates, as well as cytoskeletal elements. And so the question then becomes, what is the Lewy body doing here? Does the Lewy body serve a function? Is it actually the Lewy body that is damaging the cell and causing the cell to die? Or is it just a trash can that's really sequestering all of these other things in the cells where things have gone awry in the disease process? And so we don't really have an answer to that question. I'm personally on the trash can side of things a little bit because I just can't get my brain around what else it would be doing in a cell. But when we look at the cellular models that we have at our disposal, there's really a whole range of them, right? We've gone from yeast models back 10, 15 years ago when Sue Lindquist was modeling in yeast. We also have immortalized non-neuronal cell lines that we use. We use a lot of primary rodent neuronal cultures from rats or mice. We then have these other immortalized cell lines that can be differentiated into neuronal-like cells. And then we now have the access to the patient-derived material, so we can grow neurons in a dish, we can grow brain organoids in a dish, and those offers, I think, many more opportunities nowadays as well. So I'm going to take you back. This is actually a real blast for the past for me. So this was one of my early postdoctoral papers in 2001 when I was working with Brad Hyman at MGH. And he charged, actually, I joined his lab in 1997, which was when the first mutations in alpha-synuclein were identified. And he charged me with, go and study alpha-synuclein. I was like, okay. And so we cloned it, we put in a vector, you know, and we thought, oh, we'll put it in some cells, overexpress it, see what it does, expected it to do lots of different things. So the first thing we did though, is because at that point, there was really no good antibodies available. And so we took the synuclein and we threw a GFP tag on the end. So synuclein's 140 amino acids. GFP is 243 amino acids. So you're putting a large tag on a relatively small protein. But when we overexpressed it, and these are mouse primary neurons cultures, when you look at the GFP signal, it just looked diffuse. There was nothing really remarkable about it. It filled the cell, it filled the nucleus as well. However, when we went in confirming our fusion protein, we immunostained with an antibody for alpha-synuclein, and then we saw this. And so what we after trial and error and biochemistry and all that, what we figured out was happening is when we overexpressed this full-length synuclein EGFP C-terminal tagged protein, it was getting truncated from the C-terminus. And so it was leaving a little portion of GFP, but so it wasn't fluorescent. You couldn't see these aggregates, but whatever that synuclein with the small tag on it was now had a propensity to aggregate. And we saw this in about 5% of the neurons in a dish. If we added a proteasome inhibitor, we now saw it in about 50% of the cells in the dish. So it was some sort of proteasomal sensitive aggregation of alpha-synuclein. We thought perhaps driven by putting a tag on the C-terminus of alpha-synuclein. Weren't really sure. But what we did though is we kind of harnessed this. We made an artificial synuclein with a 93 amino acid tag on it, 93 base pair tag, which was supposedly mimicking the truncated form of the synuclein. And we found out when we overexpressed it this is in a human neuroglioma cell line, if we co-expressed it with synphilin 1, we got all these nice intracellular inclusions containing alpha-synuclein and synphilin 1. Also contain a lot of chaperone proteins as well. And it somewhat mimics a Lewy body in a dish, but it's very artificial. I'm sure you'll all agree there. It's a tagged synuclein. We're overexpressing it in a cell. So it's really not ideal. But moving on, we continued to tag synuclein because there's limited ways you can study these proteins in a living cell system if you don't have some sort of reporter to measure what you want to measure. So we also developed these these bimolecular fluorescent and luminescent protein complementation assays, where if you take a GFP or a luciferase sequence and you split it in half and you tag the N-terminal or C-terminal half to a synuclein, if synuclein-synuclein interactions occur, the two halves will come together and you will get a reconstitution of either the fluorescence or the bioluminescence. And we have both flavors here where we generated the venous YFP split synuclein assay and also the luciferase split synuclein assay. The thing about the venous YFP assay is that it's supposedly irreversible. So when the two halves of the YFP come together and reconstitute and the cells fluoresce, you cannot break it apart again. So you can't use it to, let's say, look for things that can disaggregate synuclein aggregation. However, the luciferase assay is much more sensitive as well as being transient. And so it can potentially be used for a screening tool if you want to do drug discovery and look for perhaps drugs that could interfere with the aggregation process or disaggregate aggregates. All right, moving on to other cell models that are available out there is these are the FRET biosensor cell lines that were developed by Mark Diamond's group. And so what Mark did here is these are cells, these are human embryonic kidney cells, which stably express synuclein tagged with a YFP or synuclein tagged with a CFP. And so again, when you get synuclein interactions in the cell, the two tags come close together. You can then take advantage of fluorescence resonance energy transfer to measure the FRET signal as a measurement of synuclein interactions. The thing about this cell line is it also has macroscopic aggregates that can be seen as well. And so if you look in the picture on the top right here, if you look carefully, you can see little puncta of YFP showing up as well. But really for a very sensitive readout, you have to do a flow cytometry readout to get the synuclein interactions down to the oligomeric level. So we're looking at soluble synuclein oligomers and not insoluble synuclein aggregates. Melissa did a really nice job of introducing you to proximity ligation assay, but it's another way that we can harness the models, cell models, to look at synuclein oligomerization. And so you can do this by, if you have a cell that's expressing alpha-synuclein and you use this PLA, what it will show you is each of these little red dots is representing a synuclein oligomer. And so it's a way of seeing synuclein oligomers that are not insoluble. They're still in a soluble form. However, they're not macroscopic. You can't see them just by looking down the microscope unless you fluorescently label them with the proximity ligation assay. And then with Dr. Sakia joining Dennis Dixon's group, we've actually moved this proximity ligation assay into these are a synuclein transgenic mouse, but it expresses the whole of the alpha-synuclein gene. It's the SNCA OVX mice that were developed by Richard Wade Martins. And what we can see in these mice is at 6 months, so they don't have Lewy bodies, they don't get gross aggregates, but at 6 months, if you do a proximity ligation assay, you can see all these oligomers of alpha-synuclein that can be detected. And then we actually have an intervention that we think can lower alpha-synuclein levels. And now if we look at the mice after the intervention, you can see there's drastically reduced oligomeric alpha-synuclein there. And so these techniques, while they're not perfect because you're using antibodies tagged to or reporter proteins, they all give us some information. And I think we just have to be very careful to choose the correct models that we want for the questions that we want to ask in the lab. So with the onset of we have access to the human-induced pluripotent stem cells, which we can differentiate into neurons. And we have done this in our lab. We've taken advantage of Michael Ward's NGN2, where we can you incorporate and integrate NGN2, and then with the addition of doxycycline, you can go straight from the IPS to cortical type neurons, glutamatergic neurons. And so we can take advantage of that now to model neurons in a dish. And we've been able to do that successfully to grow these beautiful neurons. And here you can just see that they're neurofilament positive, they're synaptophysin positive. And they're really, I think it gives, they've really brought a lot of advantages to the field because they are more physiologically relevant. We're looking at the endogenous proteins here. We're not looking at reporter genes, and we can potentially use those. I think that going forward, these are going to be certainly the way to go to make it have a more translational preclinical models. But what we also know is that in these IPS cells, we can induce synuclein pathology if we want to consider phosphoalpha-synuclein, phosphoserine 129 alpha-synuclein pathology, if you consider that pathology. So if you treat these iPSC neurons with human PFFs, you can induce phosphoserine 129 pathology in the dish. And now we can also do this with these AMP-LB preformed fibrils. So these are fibrils that we generated from using human brain seeds and using that as a substrate to generate the fibrils. And they form slightly different species. You'll see that in the cells, in the iPS cells. The AMP-LB, which are derived from the brain seeds, tend to form larger inclusions. They tend to be more in the cell body, perhaps more Lewy body-like. Whereas the PFF treated cells, they're very much punked out throughout the whole, all the cells throughout the processes with less, and it looks, it doesn't look like a Lewy pathology as you would traditionally think. Nonetheless, I think these are models that are just that, they're models, but they're also powerful models for doing preclinical testing, drug discovery, other interventions that you may want to do. And then just finally on the modeling side of things, we can actually now make these, the the iPSC-based brain organoids. And Na Zhao has just published a paper recently where they made organoids from the synuclein patient SNCA triplication, and showing that there's really no gross difference in the size or physiology of the organoids, whether they came from a triplication patient or a control patient. However, you can also see there's a drastic increase in the synuclein levels in the brain organoids that were derived from the triplication patient. And so I think, again, this gives us a lot of opportunities of what to study in a dish. And what they did in this paper, I'm not going to go into any detail here, but they actually used the organoids for drug discovery, and were able to show that they could identify drugs that could alter synuclein levels using the brain organoid model. And then not a cell model per se, a cell-free model, which I know we're going to hear a lot about tomorrow, so I won't spend any time, but obviously we have the seed amplification assays now. And so I think those also afford us a lot of opportunities. We can take cell lysates and we can run a seed amplification assay. We can take brain homogenate and run a seed amplification assay. We can take our iPS cells that have been treated with preformed fibrils, and they will give a positive amplification on a seed amplification assay. So then can you use that as a readout to modify the aggregates that you're seeing in the cells with whatever intervention you're interested in? So I think there's certainly a lot of excitement and a lot of opportunity surrounding the seed amplification assays. But I think if we want to create better models, we're going to have to understand the aggregation process better. And I don't think we do understand the aggregation process. And I don't have the answer here, but we do know that obviously alpha-synuclein, I don't even know if I doubt myself whether alpha-synuclein actually exists as a monomer at all in the cell. I think it's naturally a dimer or an oligomer. But we don't know what the processes are that cause alpha-synuclein to become insoluble and to aggregate in the cells. And I think to understand this process, we might need to look to things like proteomics and other things to try and discover the cofactors that are really involved in the aggregation process. And we've been doing a little bit of this in the lab, and I'm just going to touch on it briefly, is that we've been using proximity proteomics to try and understand the aggregation process. So what we have here is we have synuclein that's tagged with a promiscuous biotin ligase, but we also made a split biotin ligase as well, along the same lines as the other split proteins I mentioned earlier. And so by using these, we were hoping perhaps we could identify interactors that would interact with anything so this will only biotinylate. The way this works, sorry, back up. The way this works is that you have synuclein that's fused to a biotin ligase, promiscuous biotin ligase. It's got a mutation in it that makes it promiscuous. And basically any proteins in the cell that are within 10 nanometers of that fusion protein will be biotinylated. And you can then pull out those biotinylated proteins, do mass spec, identify the proteins. We did this with the split bioarray as well, in the hope that obviously we will never detect anything that's interacting with a monomer, because any monomer will only have an inactive fragment of the array attached to it. And so we would only see proteins that interact with a dimer and above. And so just to show that this in theory works, is we made various iterations of this. So we have cell lines expressing either of the inactive halves. We have the full length BAR-A, we have a split BAR-A. And here what you can see is this is just showing cells that are expressing the alpha-synuclein BAR-A constructs. And when either the full length or the split, when you add biotin, you can see all the biotinylated proteins here, whereas in just the halves, we don't get any biotinylated proteins. So the system works. And we've kind of done a little bit of a tweak on that, where we actually then took the BAR-A and thought, well, we can induce aggregation here, maybe see what proteins are involved in the aggregation process for alpha-synuclein. And so the two questions we can ask with these cell lines is what's monomer versus oligomer interactors, or what's quote unquote physiological conditions versus pathological conditions, and what would be the interactors that we pull out from that. And this is just showing you when we add PFFs to these immortalized cells expressing the synuclein BAR-A, we can induce aggregates containing alpha-synuclein and phospho-alpha-synuclein in the cells. And so I'm not going to go into any detail, but basically this has been done in our cell lines so far. And we've pulled out, I think we got about 1,000 proteins that we pulled out, but after some tweaking and somebody who knows what they're doing their magic with the data, which is not my forte. You know, we can say that perhaps there are some proteins here which maybe only interact with monomeric alpha-synuclein rather than dimeric or oligomeric alpha-synuclein. There's a lot of proteins that you pull out with both, which is what you would expect. And then maybe some that are, you know, specifically interacting with multimeric alpha-synuclein. It's very early days. We haven't validated any of these hits that I'm putting up here. And these are just a selection. There's no prioritization here right now. In terms of inducing aggregation using alpha-synuclein seeds, we also pull out proteins that seem to be unique to having the seeded aggregation process ongoing versus not. And so again, it gives us targets that we can pursue and we can look. The caveat here is that they're not necessarily interacting with alpha-synuclein. They're in proximity to alpha-synuclein, but that doesn't mean they interact. But they maybe do have something to do with the aggregation process, which is what, and if we can discover proteins that are involved in the aggregation process, you know, perhaps we can model that better in a cell in a dish. So then just to summarize then, my take home question is, so I haven't mentioned co-pathologies because we don't have models in a dish of co-pathologies. We haven't got that far yet. Do we need that? Probably. How do we get it? I'm not sure. But you know, we're asking monogenic questions really, because we've got synuclein in a dish that we can look at. But so I think the take home message is, you know, you choose the best model that you have, whether it's a transgenic mouse you want, or whether it's a cell culture model, you choose the best model that's there to ask for the questions that you want to ask. And we know that proximity proteomics can identify some proteins that may be associating with different alpha-synuclein species. And that hopefully that might reveal modulators of the alpha-synuclein aggregation process. As I said, they're not necessarily interacting with alpha-synuclein. They may be just proximal to alpha-synuclein, or they may be interacting with another protein that is interacting with alpha-synuclein. Limitations, this study so far, it's in immortalized cell lines. We're doing the same thing in iPSC cells in the hope that that would be more physiological and we'd be able to do that. Although, of course, we have to have a tagged protein because we have to have the biotin ligase in there to be able to pull anything out. And who knows, maybe putting a beret tag on an alpha-synuclein messes up its normal subcellular localization. And then the one other caveat is you're not going to pull out anything without a lysine. So yes, there's a lot of proteins that have lysines, but there's probably some that don't as well. So I'll just stop there. I would like to thank everyone who has in my lab who does all the work, and to my funders, thank you very much, and to all the donors for brain tissue that we utilize in our daily work. Thank you.
We're supposed to take charge. Are we going to take a break now? I would think people might need a break. So 15 minutes, 4:45, we can have our panel. Please come back. All right. So I'm going to be very challenged to pull everything together into one sort of total construct, although I think there's some really cool what was discussed earlier. And I'm going to start by asking some questions more related to, and maybe this is redundant, but I think one theme here is heterogeneity of not only pathobiology, but clinical syndrome, and how they don't always fit together as you start to pull together some of the underlying biology. And maybe, I don't know if that's a question really, but, and I think maybe we start from this side, but so you, Pam, you can have a discussion, think about what you're going to say, because you already kind of addressed the difficulty with managing multiple pathology in a cellular model, but I think that's ultimately, we would like to know pathobiologically how they're interacting. So you're up.
It happens to be my favorite topic, heterogeneity. And I really think about this a lot because of the biology has the clues out there. The lived experiences of each individual patient tells us something more about that particular brain structure that might have been more affected. And so from a neuropathologic standpoint, I think investigating the heterogeneity will really uncover some of the hidden clues. We haven't had the opportunity, but until now, we really needed to have people sort of unified in order to get at it and get the momentum. I mean, look at all the incredible people in this room and how many people are still on Zoom this late into the day. And so I think heterogeneity is actually a huge focus that really needs to be undertaken.
Yeah, I think that's probably one of the major challenges in the fields. I think in Alzheimer's disease too, there's going to be a big emphasis on subtyping. And essentially what I showed today was clinical subtyping. And then you have pathological subtyping. And then if you saw that there's so much overlap in the tau, when you look at tau levels on the clinical subtypes, could you take a more agnostic approach to just stratification on a molecular subtype? And then understand how those differ in terms of their disease progression and then underlying pathology and also clinical score. So yeah, I think that's going to be the major opportunity. Can we actually find subtypes of individual who'd be more responsive to specific therapies, to specific drugs? And then we haven't even touched upon the genetics. I think will be another major thing too, is that will they have different genetic backgrounds that you would actually be able to predict those subtypes a priori, which would be great.
Yes, of course, the clinical heterogeneity is, I mean, is what we see in the brain is also heterogeneous, but I think, to be honest, before we clinically aim to look for different subtypes of, say, Alzheimer's disease, it would be, the first step would be that we know clinically what pathologies in general, simply speaking, A-beta tau, alpha-synuclein, TDP-43 are present in an individual's brain. That is the first step. And this is before we think about all this science fiction stuff. I think that would be, no, but it's true. I mean, we, on the one hand, but on the one hand, you talk AI and what have you. But the simplest thing we don't even know yet. We cannot now see if a patient comes to clinic with memory problems, we have no clear means to say, okay, you have this, you have tau pathology that stage, tau amyloid that stage, so much alpha-synuclein, so much TDP-43, or only this. That is the first step. And then when we know that, then we can think about clinically subtyping amounts of tau in that and that area. But that's the first step. And also to get in our brains, which is my brain since 20 years, that it's not AD, DLB, or it's a brain with age-associated pathologies. And if it's a lot of A-beta and a lot of tau, we call that Alzheimer's disease. That does not preclude having alpha-synuclein as well, or TDP-43. And this is a different thinking. And I always, I pity young colleagues that come into the field, because it must be so confusing if they read, okay, this is Alzheimer's Lewy body variant and a little, and then also not to really, it's not yes or no, it's not A-beta or tau, yes or no, it's how much and where. This is the next thing, very basic. Neurodegeneration is not like cancer, where you have cancer if you have one single malignant cell. I mean, of course, the bigger, the worse, but it's already the disease. If you have Braak stage 1 or 2 tau pathology, this is not a disease, this is normal. So this is a concept how we should approach the whole thing first, and then get to your fancy subtypes. But you have to understand that first. Okay.
Yeah, we think about that a lot. How can we possibly explain heterogeneity? And so there's clearly a lot of open questions still, but we already see certain themes emerge. So we see associations of, for example, a high polygenic risk score for Alzheimer's disease is really associated with a much more rapid disease course. So there's a genetic component to it. We see that patients with a high polygenic risk score for Parkinson's disease are more likely male, more likely have motor phenotypes. So there are some interesting, themes emerging, but we also see interesting relationships to the pathologies. And so if we just look at the high risk allele, ApoE4 allele versus GBA, we see very clear different subtypes. So the ApoE4 allele carriers, they nearly all have Alzheimer's disease co-pathology, whereas the GBA1 carriers often don't have much Alzheimer's disease. So there's a real difference between those two. And again, we see a clear sex difference. Very commonly, it's the males with the GBA1 carriers and much less Alzheimer's disease co-pathology. So we're scraping the surface. We can get better with larger cohorts to improve our polygenic risk scores. And I think it can really, elevate our ways to substratify the patient cohorts and perhaps think differently on how we do, clinical trials, really, subdivide them into those with certain risk profiles versus none. It's exciting field.
What was the question again?
We addressed it to some degree already.
So I think it will be important once we can take, we hope we'll have things we can take. There are things in clinical trials that are directed towards lowering synuclein levels, but it might be interesting to see how those eventually affect the co-pathologies that are in the brain as well, and whether altering one affects the others, the A beta and the tau and whatever. And these are all questions that we're not going to know the answer to for quite a while, but I think it's really interesting to think about. Maybe in a model system or a mouse model, you could potentially look at that. Problem is there are really no models that have all the salient features that you need right now.
Just add to the model. Yeah, thank you. So because this is always the question, it's such a pity that we don't have a model that really recapitulates the human. But no, you probably know Matthias Jucker, this famous mouse guy from Germany. And he said, that's not true because we don't want a model that recapitulates the human condition, because then it would be as confusing as the human brain. The model is only here to answer one very specific question. And it would be good if we at last answer the question, what does A beta 2 do to tau that it makes the pathology work? So I don't think that we need a cellular model models are to answer one tiny bit, but not to, and it's impossible to recapitulate our brain, a model.
I can't help myself. And one bit of a extension in the human brain from the heterogeneity standpoint is actually by having those individual questions and focusing on certain structures of interest, we can grow from there. So we've heard a lot today about neurotransmitter systems. And interestingly, both noradrenergic and cholinergic are greatly affected in Alzheimer's disease and dementia with Lewy bodies, but yet we get these different phenomenon as an end result. And the nuance of studying one tiny structure cannot go understated, because if we can understand the beginning or the end, the anterior or posterior extent, we might also uncover some of those heterogeneous clues. And so I think that individual questions, ironically, in the context of heterogeneity, may really help uncover some of the unknowns.
I was curious about your discussion about agnostic approach to therapeutics, which is you don't worry about the pathology, you worry about the AI congregation of components that tells you what person, how they're going to respond. Is there a commonality? Everybody's pretty excited about the idea. We can't measure some aggregated proteins correctly clinically now, and I know Kajal's going to have the aggregated synuclein imaging any day now. Maybe tomorrow. Maybe tomorrow. Are there commonalities there? Should we be looking for what is it that's underlying all these aggregated proteins happening together? And are there thoughts about that from the group?
Start with your
Yeah, some of the signals coming out of spinal fluid now, some shared pathway would be ubiquitination and proteasome dysfunction, sort of a commonality between what we see in synucleinopathies and Alzheimer's disease would be one shared common pathway. Metabolism is another one that you see, energy metabolism changes. I know our team and Oscar Hansen's team has seen strong, robust changes in energy metabolism linked to tau pathology. Is that also going to be seen with synucleinopathies is another question that remains to be addressed. And I think we can now address that, at least in the spinal fluid. Just related to, science fiction, I think if anyone in the room 20 years ago thought we could predict underlying brain pathology in the blood, I think that would have been a science fiction type question, right? And I think, it's remarkable what has happened with the blood-based biomarker work, that in Alzheimer's disease, you can now measure phosphorylated tau species in blood and predict underlying pathology in the brain. And I think that's where we need to go with LBD and synucleinopathy. And I think if we invest in it, it's only a matter of time.
And so we often will begin at the end to inform the beginning. So we'll reverse engineer. But I think to your question of thinking about what are the experiences of the individual where we saw stratification based on either seeding amplification or otherwise, I think it's going to be important at some point to be agnostic to the underlying pathophysiology. As much as I love looking down the microscope, we're not there yet. But as we've already gone through this renaissance of seeing clinical syndromes and recognizing that there are underlying pathologies that allow for this mismatch, one day I think we'll too see these certain underlying contributors that just happen to form the morphologies that we now know of as neurodegenerative diseases. How we're going to get there, I don't know. That's going to be the exciting part.
Yeah. So I think there's also an element of neuroinflammation that is shared across the neurodegenerative disease field, which is interesting from a potential, modifiable angle. The other thing, we see again and again is impaired protein homeostasis and energy metabolism. And so, this is something that seems to affect neuronal health or brain cell health in general. So potentially we could really think about multi-target therapeutic intervention. So one that really targets the protein and one that targets the disease process more generally, be it, cardiovascular co-pathology or be it neuroinflammation more generally. And, I think we're in many ways, it feels like we're being in the same situation where the cancer field has been like, 25, 30 years ago, that we start to see the different pathophysiological processes and we recognize attacking one may not be enough. We may have to really individualize it much more and also to the disease stage of the patient.
I'll be super interested to see what the genomics pulls out from infection too. More we're learning about how infections might incur the sort of rapidity of a disease process. It'll be interesting if some individuals can withstand certain things or inflammation that might help tease out why there are some of these nuanced differences.
Right, that's quite all right. I was looking for what my other question was. We got off on the agnostic approach. And I guess I was actually going to ask Sonia, do you see genetic links to this commonality of co-aggregated proteins? Are there links that we're seeing, or with the proteomic side? Because you talked about ubiquitination and in those pathways that tell us something about why most of my Alzheimer patients, 50% have Lewy bodies, probably 50% have TDP-43 pathology, probably 25% have all three pathologies, not addition. So is there something there that we're missing or that we need to look at that might be a common pathway from a therapeutic point of view?
Yeah, it's hard to pinpoint it to a common pathway, but we do see clear pathways that are affected. Big one, but also amyloid pathway. There is a link between amyloid and synuclein somehow. I don't understand. And a lot of the risk genes and even the familial genes, they have a mixture of fulminant Lewy body and Alzheimer pathology. But interestingly, even in some cases, you can see some links to TDP-43 pathology. Progranulin mutation carriers practically always have Lewy bodies, and it probably is because of lysosomal dysfunction, but other things. But it tells us something about bottlenecks in the cellular machinery that are very commonly affected in neurodegeneration. Maybe the proteinopathy that we end up is just one of the bystanders. It just points that there is a dyshomeostasis in protein metabolism more generally.
Please go ahead.
So we have some online questions that were directed at specific speakers. So I think this one is for Johannes. It might have made more sense in the context of your talk, but it was, what about MSA?
What about it? I mean, it's a very rare disease that has synuclein in glial cells. But you cannot even, it comes nowhere. It's like Pick's disease or PSP. They are so much rarer than these big diseases, you know. And that's also why they probably don't have as much co-pathologies as other, because they are also younger. At least from my experience, MSA cases may have a little bit of tau pathology, but not relevant. And the same goes for PSP and CBD and Pick's disease.
I think it may have been at the end when you were disaggregating things in MSA.
Oh, no. I don't think that we will have a Lewy body cohort with MSA cases in that, unless there was some clinical misdiagnosis. But this is, I mean, this is really such a small percentage that I think it matters for the individual, of course, but it doesn't matter if you look at the bigger picture.
And next question was for Nick. Has the new LISA assay or DIA-MS panel been tested in other fluids or tissues, for example, plasma, skin, submandibular gland, postmortem brain, etc.?
So that's a great question, as we will be running the new LISA on paired plasma, and it was actually developed for plasma. So I think it will perform pretty well there. I don't know if it's been used in postmortem tissue or cell lysates. I think they're probably starting to pilot that. And I think that would be really exciting, because if you have paired postmortem tissue and antemortem biofluids, you can start to correlate the signals in the periphery to the central nervous system and brain region, specific regions too, right? So we can start to address some of those gaps there. And I think, the DIA can be run and will be run on the plasma, and it can be run in tissues as well as the TMT assay. I haven't done any skin biopsy work, but I've heard that they're doing some of that in the PD field. So I would think the mass spec could be run, but I'm not sure about the new LISA.
And a last one, although I think it was sort of addressed, so you all can decide whether it counts as addressed or not. Could our panelists weigh in on the biology of PDD versus DLB, especially given that the proposed biologic definition of neuronal alpha-synuclein disease lumps PDD and DLB together?
Yes, I mean, I made my view very clear in my talk. For me, this is, I mean, yes, you have in both diseases, you have this alpha-synuclein, but it behaves differently. The clinical symptoms are different. The pathological picture is different. If you need to call it one disease, well, yeah, be my guest, but I don't believe it. I just, it's not what we see. It's different. But in the end, I think these discussions are completely useless, to be honest. I mean, we all know what it is, and if some want to call it one disease, well, then they should call it. It's a little bit like semantics, and I don't understand why we waste so much energy on questions like this. And I know there's a lot of energy and important and replies and discussion. And I think, well, what does it matter actually for the patient? But maybe I don't, there must be some reason that is beyond me, probably. Yeah, okay.
I mean, once you start looking at the extreme ends of the spectrum, the very pure PDD cases, they're often male, they're often younger in onset, they have, obviously more motor symptoms versus the ones that are on the other end, very cognitively predominant, more female. You do see some shifts in the average genetic architecture, but it's not that you can tell them apart. So it's still part of a spectrum. And I'm, I'd like to keep them together when I look at them molecularly. I know there are subtypes that we may have to, depending on the clinical trials where we target them. but I find it hard to really completely, keep them separate. There's a lot of overlap, and we can learn a lot from studying the broader spectrum, and, we can do sub-analysis. We're pretty good at that.
I think it matters to the patients, at least the individuals that I've spoken with. I think that we heard earlier today, it was quite beautiful. Can I just have a diagnosis to the disease that's robbing me? And I know when I lost my grandma, we had an indication that it was Alzheimer's and we had her brain donated. And I tell you, having that answer was incredibly important. And so I study Alzheimer's disease on a spectrum, and it is Alzheimer's disease, but we've learned a lot from understanding hippocampal sparing versus limbic predominant. And I think the phenotypes are telling us something. And I agree. I don't know. We have these discussions a lot. I don't think that I think it was premature. I think I was speaking with somebody else about the biological criteria, but I think it's still very important for us to figure it out before we lump everybody together.
Yeah.
Statement?
Maybe we can talk about that concept over dinner, because we're going to need a good hour. But could I ask a question to the neuropathologists on the panel, and maybe a follow-up question? Is there a consistent clinical phenotype associated with amygdala predominant Lewy body disease? Or maybe another way to say this, is there any patient with amygdala predominant Lewy body disease that had a clinical phenotype other than normal?
No.
Okay.
So the amygdala shows a lot of pathologies, TDP43, tau, A beta, and alpha-synuclein. But for some reason, if you only have it in amygdala, I don't know any case that had any clinical symptom.
We have, so at least in our series, the amygdala predominant Lewy body cases occur in the context of advanced Alzheimer's disease. And Tanis Furman has diagnosed many dementia Lewy body cases, of course, in collaboration with our neurologist. And many of our DLB patients actually neuropathologically presented with amygdala predominant Lewy bodies, but it's not always synonymous, but we can see that.
Okay.
I don't know that I've ever seen amygdala predominant without.
Well, but with clinical Alzheimer's disease?
With pathological Alzheimer's disease.
Well, I mean, like Braxage 5-6.
Yeah,
I've seen a lot of cases. Yes, of course. We often have in control cases, yes, tons. Lewy bodies in amygdala.
Yeah, I haven't seen it, but
yeah.
maybe I don't have a large.
But I mean, this is what I mentioned. We need actually our case numbers are low, even if it's thousands, it's still low. We would, given this heterogeneity, we would actually really ideally need not neuropathology is not possible on that scale, but a large scale post-mortem readout for what's basically what's going on in the brain. Because I don't think that we know it from the blood yet. That would be great if we get there. I mean, if we, as I said, if we could make the post-mortem neuropathology redundant because we know it during life, that would be great. But in order to get there, we need a big, large-scale readouts. Yeah.
Follow-up to that question then is, if it's largely seen in advanced Alzheimer's disease, how are we going to interpret RT-QuIC in the CSF along the whole spectrum of disease? Because the past studies have already shown a significant minority of amygdala predominant Lewy body disease cases are RT-QuIC positive. And so if that doesn't have a clinical syndrome, we're not sure if it's going to spread and lead to a phenotype, and it's more closely associated with advanced Alzheimer's disease. Is it Lewy body disease, and should it be treated anyway along the spectrum? And I've never been in a context where we thought this through, and maybe others have, but
I have, but I don't know. I'm moderating.
No, chair's prerogative.
you have the prerogative.
All right, I'll go ahead. It's a good question. I think, and this kind of leads to one of the questions I was going to ask.
Are you going to combine them?
I'm going to combine
okay.
them. That was the idea.
Yeah.
So, right, some of your amygdala predominants are negative, and the synuclein is pretty much limited to the amygdala, right? Some of them are positive CSF, and this kind of gets to some of this, I don't know if it quite fits the proximity ligation assays, but when we start to look at other brain regions, we can start to maybe pick up aggregated protein that isn't histologically detectable yet, but we can see it biochemically, or whatever you want to call that. You can get RT-quick positivity. And so that may differentiate those cases, but how we do that clinically, maybe the positive CSF RT-quick is a way to differentiate those. At least that's my thinking, for what that's worth.
That's very good thinking. We often, when we think about amygdala predominant Lewy bodies, and for those who are as used to it, this is often we find it in the context of advanced Alzheimer's disease, where we see this focal involvement of Lewy body pathology in the amygdala. And we don't classify them as a Lewy body disease per se. So I think they do represent this very unique entity, though I really like this almost an anticipation. If we did the seeding assays, an anticipation in cortical or brainstem structures, but we see it stay relatively confined to the amygdala and must have something about it that doesn't either allow quote unquote spread or cofactors to kind of involve. But I think it also suggests that there's a stress response in the amygdala that's likely could be both tau and amyloid that's driving synuclein. And so what else could be driving synuclein in other places? Fun.
It's not so much a question as a comment about this question on subtypes. So on the one hand, there might be different subtypes or subdiseases or endophenotypes. On the other hand, isn't it possible that it's the same disease, but what differs are the host factors, and that it is really a matter of selective vulnerability? And, maybe, for the amygdala, it takes a whole lot of hits with a whole lot of different pathways, but in fact, PDD versus DLB might just be a vulnerability factor in different areas of the brain. Is that not also a possibility?
Lots of nodding in there for those if we're not on camera. I think it's a very important point. And I think we like to think about vulnerability, but it's also exciting to think about these individuals who may have protective factors in certain places, and maybe that falls into play with the temporal incidence. And I know we often go back and forth on the 1-year rule, but as far as the guidance per se, but I think that's a very important statement. Mm-hmm.
I was also going to ask you about selective vulnerability. We've tried to get people to look at what it is about different brain regions that invites different pathologies, and we don't get very far. And certainly, people do proteomics and single nucleus transcriptomics in different regions, but I don't think we have a really good answer to why you tend to see alpha-synuclein here, and you see tau, well, pretty much everywhere, and you see TDP-43. What is it about these cells? And we talk about dopaminergic neurons and all that, but how do we really start getting at that question of selective vulnerability?
Yeah, I mean, that's really true. Why is tau? I mean, tau is not pretty much everywhere, I'm afraid, but it starts in the entorhinal cortex. I mean, in every brain. Why there? I mean, hippocampus, entorhinal. Why does it spread? That we really have no idea. But coming back to the synuclein, I don't think that is really different vulnerability. I think it's really a different trigger, because you have these PD cases that have where the but it really starts in the medulla oblongata, whereas the other one doesn't start there. So the other one, DLB, seems to be really kind of triggered also by A beta. So this is a difference, I think. Or in other words, for PD, you don't need A beta, but apparently for DLB, you need it. Like you need A beta for tau pathology progressing from Braak stage 4 to 5 and 6. And that's, I mean, in the end, it's probably all a little bit of vulnerability, and I mean, genes and environment and all that together. But yeah.
So again, the challenge, this is a great opportunity. So to challenge that point, coming back to REM sleep behavior disorder, the largest prospective series, almost 1,300 people followed with REM sleep behavior disorder over time. Over 12 years, about half developed, half of the people that phenoconverted, half developed Parkinson's, half developed dementia, which argues it's ascending. It's ascending. So if RBD is starting, it's in the brainstem, and why it goes to more of a PD phenotype versus a DLB phenotype, we don't know. But I just can't see that there's surely going to be some outliers, but it just seems like most people have an ascending route of neurodegeneration.
As opposed to top down, like
Opposed to limbic
as opposed to limbic centric out or.
Yeah, but why do they not develop Parkinsonism before they develop dementia?
Because it's the NIGRA, it has not hit a threshold.
But
or
it
is
marches,
skipped.
so you really think it marches through the NIGRA? And
not necessarily.
But the point is, if it starts always in the medulla oblongata, ascending, as you say, and then you develop dementia before you even develop Parkinsonism.
But they already have REM sleep behavior disorder.
So what?
They have RBD.
Yeah,
So the
okay.
brain steps hit. And it maybe starts in age 50, and they don't develop dementia until 70. And so the NIGRA is somehow relatively spared.
Have you post-mortem of all of these? Maybe.
Yeah.
Of all these? What is it?
And just because, just because they don't, so there is a certain amount of cell loss. A lot of our patients, even those that do not have Parkinsonism, have brainstem, have midbrain synuclein, they have nigral cell loss. They do have, I can think of several patients just off the top of my head, they did have pathology, Melissa can attest, but didn't have clinical Parkinsonism. So I know, I wish Dennis was here because, but this is something that we've certainly seen.
What about their AD pathology?
I'm sorry, what?
How was their AD-related pathology? Those cases that didn't have Parkinsonism, but dementia.
Sorts. We have patients who have some with AD, some with no AD. We have patients who most certainly have no Alzheimer's.
So you have DLB patients pathologically, clinically without Alzheimer's disease pathology?
Yes, absolutely, absolutely. Yes, yes.
How many? I mean, percentage-wise?
Brain bank of how many?
So they'll still have amyloid, like.
Oh, yeah,
right?
okay,
But,
good,
but,
okay,
But they
that's-
won't have extensive
Diffuse
tau pathology,
amyloid.
like
Yeah.
very minimal, like. If,
Yeah, but they have amyloid. They have amyloid.
But I mean, to some extent, I mean, maybe we should be thinking about co-pathology, like a complex biology of dementia with Lewy bodies, and that synuclein and amyloid may be key contributors, just as tau and amyloid and Alzheimer's. Like 97% of our Lewy body disease brains have amyloid.
Yeah.
But it doesn't necessarily need to be thought of as Alzheimer's pathology in this context. If potentially it's a part of the disease mechanism, I think it's still unknown. Most of it's diffuse plaque pathology, so I'm not as much in line with thinking of it as the Alzheimer's type plaque pathology, but we could still say there is Alzheimer's pathology from the amyloid perspective.
It would be important it would be important to really exactly know how big the percentage is, because it's in most cohorts, you have DLB cases, at least 30% have full-blown AD pathology, and the other ones at least moderate. So if you tell me now we have only 5% have full-blown, and most, that would be really something different, but this is not the data I know. That's all I can say.
It's my fault.
I guess I'm including you in this panel now. But, that assumes that all Lewy body disease cases start with RBD.
Point. So if
within that cohort.
Good epi studies have shown about a 1% prevalence of RBD in middle-aged and older people. So that suggests we have over 30 million people with RBD in the US. Not near all of them develop dementia or Parkinsonism. But of those people followed prospectively, most of them, if you follow them long enough, will develop PD, DLB, or a small percentage MSA. And so if we're gearing up for prevention or disease modification, it seems like a reasonable, relatively prevalent cohort to follow and treat. And it just makes sense that it's, again, it's an ascending, if you follow that line of thought, it's an ascending degree of neurodegeneration.
I think my point was more not that that is extremely important. It's the only way we have, right, to look at prodromal or even pre-symptomatic disease. But do all DLB cases, ultimately dementia cases, end up, did they have RBD?
No,
Does it
no,
go back
no,
that way?
no.
So it's one way to approach that, but yeah, that's just a question. Doug.
We also have olfactory loss.
Right.
And as a connectomic problem, can somebody on the panel please tell me how the olfactory neurons relate to the brainstem that we can possibly
Yes, yeah. So his question is, we also have the olfactory changes that we see clinically, as well as we see lots of synuclein pathology in the olfactory bulb. There's no doubt about that. Where does that sit in this pathway of ascending pathway or amygdala pathway? I guess you could argue.
Well, in my view, it doesn't sit in that pathway. Very simple. So there's no connection. And I agree. So that's again, my, it's not always this ascending. And by the way, we don't only have, we not only have alpha-synuclein pathology there, we have also the same with Bragg stages, tau pathology. If I look at olfactory bulbs since 15 years on nearly every brain, I can actually predict the Bragg stage when I look in the olfactory bulb. So the tau Bragg stage, not the alpha-synuclein. Little alpha-synuclein, A-beta very little, interestingly, but alpha-synuclein, tau a lot. And TDP43, not that much either. So, yeah.
And speaking of the heterogeneity we talked about earlier, what's interesting with its earlier phenomenon as far as, and I think that was part of Doug's hope, was to talk about how can we utilize this as prodromal, and then it appears later in Alzheimer's disease. And so once again, these neurodegenerative diseases that may lie along some axis, I think could be informative. Of course, it makes it a little bit more difficult that we're in the COVID era because there can be an olfactory impairment, but I think it's something worthwhile.
So we're down to our last five minutes. And so, JP's allowed to ask a question.
Sit quietly. So there's a little bit of conflation here between neurodegeneration and pathology. And in my simplistic mind, the clinical phenotypes are driven by cell loss, synaptic dysfunction, cellular dysfunction. So your neurons aren't working well, and that leads to a clinical phenotype. But what I'd like the panel to do is to just unpick then the pathology, how that then drives this cellular dysfunction or cell death. And because I think that is not immediately clear. I mean, we've had some arguments about Lewy bodies, which are there, and we're going, hey, they're really pathology. They may be bad, but they might be the good guys, of course, as well, the trash cans, etc. So it's really to just understand that a little bit more. How have we got that clarity between the links between the pathology in relation to the cell loss and death and dysfunction? Just to really sort of understand that relationship.
Start with Pam.
Honest.
No.
Start limping.
Let's start with the trash can.
I mean, yeah, there's a lot of thought out there, right, that it's oligomeric synuclein, oligomeric A beta, oligomeric tau that is actually causing the cellular dysfunction, and not the gross pathology necessarily. So, I mean, I don't know what that means for removing amyloid from the brain when you're removing. I don't know the answer to this question because I haven't followed it closely enough. I don't know if the amyloid immunotherapies actually reduce A beta oligomers as well, or do they just remove the amyloid deposits from the brain? I don't know. But I think that's where you're getting at, right? Is whether the pathology is just a hallmark of cellular dysfunction that's happened already, or whether it's actually driving the cellular dysfunction. Now Johannes can talk.
Yes, exactly. I mean, oh, so. But it would fit very well now.
Well, I guess you should.
Yeah, so because it's exactly how you finish that. We don't know if it really causes that, or it's just a bystander. So that's, I see the pathology we see is a surrogate for something has happened. I cannot say if that's the cause. And if you think in particular in tau, it's very obvious. So you know that animals like the Arctic ground squirrel, when they hibernate, they hyperphosphorylate their tau. And that's certainly not a bad thing. So, and if tau is always phosphorylated, dephosphorylated, kind of is ATP dependent process. So it could well be that the neuron shuts down. That's why tau doesn't need to be phosphorylated, dephosphorylated. So it hangs around in a hyperphosphorylated state. And as we know now, this hyperphosphorylation can then kind of induce hyperphosphorylation in other neurons, like in a prion-like mechanism. So, but of course, is this a consequence or is it a cause? I don't know, but it seems with A-beta that really does something. And for alpha-synuclein, I mean, there are people that say alpha Lewy bodies are protective. So as you say, I don't know, but we know if you have a lot of these things in your brain, you will have clinical symptoms. That's what
I don't think protective is the right word, though. I think it's more a sequestration of things that have gone wrong with the cell. I wouldn't say that a Lewy body is protecting the cell. That's just when you're looking at it neuropathologically, you're looking at a snapshot in time, and that's the cell that's still perhaps alive and it has a Lewy body. Now, if you were to have that patient a year later, would that cell no longer be there and the Lewy body would be gone? We don't know that. I mean,
Yeah, it just came in. Does the panel expect that anti-aggregation or anti-misfolding therapeutics, as in the ongoing orchestra trial, will work on DLB as well as PD?
Yeah, I think it's probably gonna be much harder in DLB, just because we know co-pathologies are the norm. You're only gonna hit one protein, but a lot of the other processes you're not gonna attack. Maybe it's gonna be easier in pure Parkinson's disease, where there is much less co-pathology going on. So I would expect that DLB will probably not gonna be as successful. I think we need to think broader and in the DLB patient community.
So much for, is it the same disease?
Quick last, this is a gaps meeting, right? So, and you each have like 1 or 2 sentences in our last 30 seconds to say, what's our gaps that we need to address?
I think the critical gap in knowledge is the spatial biology of actually hitting in on what JP was just bringing up, is understanding what we're seeing with regard to the pathology, the cellular health, and the microenvironment surrounding.
Yeah, I would think a potential gap is a more holistic view, multimodal view of the disease. I think we can aggregate the data across imaging and clinical and pathological metrics that would be really strong in being able to maybe better subtype or classify the disease.
Diagnosing patients according to the pathologies that are present in their brain while they are still alive, and making post-mortem neuropathology redundant.
We really lack a lot of prospective longitudinal cohorts. We're very good about doing the genomics, but the data is only as good as what you put in. So we can do a lot of great, fantastic modeling and very well characterized cohorts. So that's what we really need to double down on.
And I'll just say, I think there's still a lot of gaps in mechanism that we don't know. We don't know how the different proteins influence different mechanisms. And so I think there's still a lot of basic science that can be done that will inform the translation going forward.
So thanks to the panel and for all the great questions and interactions, and let's go have dinner. All right.